and remover of obstacles. I now invite Mr. Krishna Suradkar to recite Ganesh Vandana in his melodious voice.
तुझ नमो तुझ नमो ओंकार स्वरूपा सद्गुरु समर्था ओंकार स्वरूपा सद्गुरु समर्था अनाथांच्या नाथा तुझ नमो तुझ नमो तुझ नमो तुझ नमो तुझ नमो नमो माय बापा गुरु कृपाधना नमो माय बापा गुरु कृपाधना तोडिया बंधना माया मोहा मोहजाळ माझे कोण निरशील मोहजाळ माझे कोण निरशील तुझ बिन दयाळा सद्गुरुराया तुझ नमो 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 एका जनार्दनी गुरु परब्रह्म एका जनार्दनी गुरु परब्रह्म तयाचे पैना सदामुखी एका जनार्दनी गुरु परब्रह्म तयाचे पैना सदामुखी तयाचे पैना सदामुखी तुझ नमो 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 ओंकार स्वरूपा सद्गुरु समर्था अनाथांच्या नाथा तुझ नमो तुझ नमो तुझ नमो तुझ नमो तुझ नमो
Thank you, Krishna, for that beautiful invocation. It is our tradition to seek blessings and divine grace, ensuring a successful and inspiring event. We will commence with the ceremonial lighting of the lamp, symbolizing the dispelling of darkness and the ushering in of knowledge and wisdom. I would now like to invite the dignitaries to join us in lighting the lamp.
Thank you, everyone.
We now request to welcome our dignitaries with a bouquet.
Moving further, we request the Director IITM to felicitate the dignitaries with a memento. Dr. Nico Caltabiano. Now requesting to felicitate Dr. Hindumati Palanisamy.
Thank you, sir. Moving ahead, we now invite Dr. R. Krishnan, Director IITM, to deliver the welcome address.
Message. Respected esteemed dignitaries, today's chief guest, Dr. M. Ravichandran, Secretary, Ministry of Earth Sciences, Government of India, who has sent his video recorded message. Our guest of honor, Dr. Mrutyunjay Mahapatra, Director General of Meteorology, IMD, who has joined online. Dr. Yali Luo, Nanjing University, Professor Yali Luo, Nanjing University of Information Science and Technology, New IST, co-chair of the IWM8, who is also joining online. Dr. Nico Caltabiano, Scientific Officer, World Weather Research Program, WWRP. Dr. Hindumati Palanisamy, Scientific Officer, World Climate Research Program, WCRP. Dr. E.N. Rajagopal, Executive Head, International Monsoons Project Office, IMPO. The IWM International Scientific Committee, ISC. The International Organizing Group, IOG, National Organizing Committee of IWM NOC, and the Local Organizing Committee, LOC, of the IWM8, and the galaxy of distinguished delegates, participants, early career scientists, and senior scientists like Professor Mohanty, Dr. Rupa Kumar, Professor Elena, and so many of them, Dr. Kriplani, so many of them. It's my great and early career researchers. It is my great pleasure and honor to extend a very warm welcome to all of you on this important occasion of the 8th WMO International Workshop on Monsoons, IWM8, which is being organized at our institute, Indian Institute of Tropical Meteorology, IITM Pune, during 17 to 21st March 2025. Welcome to all of you. The IWM is a prominent quadrennial workshop series under the World Weather Research Program WWRP of the World Meteorological Organization. The eighth workshop in this series, that is IWM8, is being organized jointly by IITM Pune, the Ministry of Earth Sciences, Government of India, the WWRP's Working Group on Tropical Meteorology Research, WGTMR, and the WCRP's Clivar-Juvex Monsoon Panel in coordination with the India Meteorological Department, and the International Monsoons Project Office, IMPO, located here in IITM Pune. The topic of IWM8 is advancing the understanding and prediction of monsoons and their impacts in a changing climate. The monsoon systems of the world are a dominant aspect of the Earth's climate, characterized by seasonal reversals of prevailing winds and along with seasonal shifts in precipitation, and they constitute a vital source of freshwater supply in some of the most densely populated areas of the globe that are heavily dependent on monsoon rainfall for agriculture, water resources, industry, transport, energy, infrastructure, and several socio-economic activities. Multi-scale weather and climate processes, as well as human-induced climate change, are known to influence the global and regional monsoons on different timescales, including high-impact weather and extreme events. Enhancing observing systems, improving our knowledge, theory, and understanding of the regional monsoon processes and their representation in weather and climate models are essential for reliable and skillful monsoon predictions and for transforming research to operations and societal services. Keeping this in view, IWM has been centered around 5 key themes. The first one on regional monsoons of the world and their multi-scale processes. Second, on the field experiments and multi-platform measurements of precipitation over monsoon regions. Simulation and prediction of monsoons, including extremes. Monsoons in a changing climate. Research to operations and operations to services transitions and communication. I'm happy to inform that IWM8 also includes a dedicated session for early career researchers, ECR, in which over 70 ECRs are expected to participate. I'm also happy to note that IWM8 has received overwhelming response with nearly 300 abstract submissions. The workshop features 29 invited talks, 53 oral presentations, and 225 poster presentations. Around 250 participants, including 4 international scientists, will be attending the workshop in person, and there are 29 online talks. I extend my sincere thanks to all the participants, especially many of them who have traveled long distances to engage and contribute to the scientific discussions and interactions during IWM8. I am looking forward to a very productive and enriching outcomes from the scientific deliberations of IWM8. You can all be assured that my colleagues in the local organizing committee will provide any kind of assistance in case of any difficulties or practical issues that you may have. Without taking much time, I welcome all of you once again to this very important monsoon event in our institute. Thank you all.
Thank you, Dr. Krishnan. We are delighted to hear your inspiring and encouraging words. Your vision and leadership has been instrumental in bringing this event to fruition. Ladies and gentlemen, our chief guest is Honorable Secretary, Ministry of Earth Science, Government of India, Dr. M. Ravichandran. With great pleasure, I introduce Dr. Ravichandran, who has held several prominent responsibilities, including the Director NCPOR Goa, where he played an instrumental role in execution and implementation of polar science activities of India. He has been in charge of coordinating several of the India's scientific missions to Antarctica and the Arctic. An avid researcher himself, he continues to motivate the climate science community. A well-recognized name to this fraternity, he has been a guiding force for the MOES family, driving forward our mission to foster scientific innovation. Today, for this event, he has sent his inaugural address through a video message. I now request to play the message from our chief guest.
Government of India. It is a very good morning to all of you. I am Ravichandran, Secretary, Ministry of Earth Sciences, Government of India. It is my privilege to welcome you all participants to the International Workshop on Monsoons, a prestigious quadrennial workshop series under the World Weather Research Program of the WMO. My apologies that I could not present physically there due to some other pressing tasks here in Delhi. I understand that this marks the 8th workshop in this series, and it is being organized by the Indian Institute of Tropical Meteorology, Pune, Ministry of Earth Sciences, World Weather Research Program Working Group on Tropical Meteorological Research, and the WCRP's CLIWA and GVEX Monsoon Panel, in cooperation with the India Meteorological Department and the International Monsoon Project Office. I am proud to note that the International Scientific Committee of these workshops include esteemed members from various countries, and with Professor Yali Luo and Dr. Krishnan, who act as co-chairs. The theme for this workshop is advancing the understanding and prediction of monsoons and their impact in a changing climate. The objectives set for this gathering are critically important: to discuss the recent developments in our understanding of monsoons, as well as their modeling and predictive methodologies. We aim to explore cutting-edge technologies and tools for predicting extreme monsoon events, and will delve into the utility of field experiments and new monsoon prediction tools to derive societal benefits. One of the workshop key priorities is to comprehend how monsoons are changing both spatially and temporally across diverse time scales, whether it is intra-seasonal or seasonal, decadal, and beyond. Identifying areas that require enhanced observations, both from satellite and in situ, and both from the ocean atmospheric realm, it is crucial for understanding and improving monsoon forecast. Furthermore, it is important to discuss on how we can enhance forecast accuracy at various scales, with application potential extending beyond the Indian monsoon to affect various regional systems, especially African, Australian, Asian monsoon, how it evolves. The global climate scenario demands that we also analyze teleconnection with polar regions, tropospheric component, providing insights into how these connections might influence extreme weather patterns in various regions. Specifically, we aim to study changes in the Indian monsoon, including shift in onset and withdrawal dates and alterations in the spatial distribution of rainfall is an important considerations. As I understand that, the workshop centered around 5 important scientific themes: regional monsoons of the world and other multi-scale processes, field experiments and multi-platform measurements of prediction over monsoon regions, simulation and prediction of monsoons, including extremes, monsoons in a changing climate, and finally, research to operations and operations to service, transitions and communications. The workshop seems to have garnered significant interest, receiving nearly 300 abstract submissions. It is structured to include 29 talks, 53 oral presentations, and 225 poster sessions, demonstrating a comprehensive approach to sharing knowledge. I am particularly impressed by the dedicated early career research session, focusing on global connections, monsoon research around the world for ECRs. It is encouraging to note that the participation of ECR members and international scientists with an impeccable attendance. I have no doubt that this workshop will be tremendous success. I am confident that by the end, all attendees will leave with enriched knowledge and fresh ideas that will fuel future research in monsoon systems. The insights and innovations shared here will undoubtedly contribute to enhancing our monsoon systems and ultimately our ability to serve society better. I wish you all a productive and enlightening workshop. Thank you, one and all. Very good morning to all of you. I am Ravichandran, Secretary, Ministry of Earth Sciences.
Thank you very much, sir, for your encouraging address, extending your cordial wishes and support to IWM8. Ladies and gentlemen, we have our guest of honor, Dr. Mrityunjay Mohapatra, with us online. Dr. Mohapatra is the Director General of Meteorology, India Meteorological Department. He has made outstanding contributions to the improvement of early warning services of IMD and has several awards and recognitions to his name. Dr. Mohapatra has been an expert member of several national and international committees. He is a permanent representative of India to WMO and the third Vice President of WMO. Thank you, sir, for joining us today. May I now request Dr. Mohapatra to address this gathering. Sir, you may kindly unmute yourself.
Namaskar, good morning to all of you. Respected Secretary, Minister of Earth Sciences, Dr. M. Ravichandran, Dr. R. Krishnan, Director, Indian Institute of Tropical Meteorology, Dr. Rajgopal, Dr. Nico, Scientific Officer, WRP, Dr. Hindumati, Scientific Officer, WCRP, distinguished guests, delegates, ladies and gentlemen. At the outset, I extend a warm welcome to all the distinguished participants, especially the delegates from other countries for this IWM8 workshop. It is very heartening that Indian Institute of Tropical Meteorology, Pune, which was established for the purpose of monsoon research, is organizing this 8th workshop of International Forum on this occasion. If you look at the development of the monsoon research, it is a proud privilege of India that we started this research long back towards the end of 1800s or 18th centuries. The first discovery came from India, telling that Indian summer monsoon is related to the Himalayan snow cover. And based on that, in 1886, the first long-range forecast was issued by India Meteorological Department. Thereafter, the search went on and the research and development took place globally. And under the leadership of Sir Gilbert Parker, we could establish the relationship between the pressure at Tahiti and Darwin after searching a number of parameters globally. At that time, therefore, we could define an index called as Southern Oscillation Index. And based on Southern Oscillation Index, the long-range forecast of monsoon in India was further modified. Not only that, that research led to discovery of North Atlantic oscillations and many other oscillations globally. So therefore, why I told this history, it is because that the people from the very beginning have started with curiosity to find out the various aspects of monsoon, including the various types of monitoring tools and the prediction tools. But still, today, if you just look at, there are still challenges and gaps in understanding with respect to the observations and also with respect to the predictions. As all of us know that monsoon is the most important source of the fresh water. And if you consider especially the South Asia, about 70 to 90% of the rainfall occurs during the monsoon season. Therefore, monsoon is considered as life. If there is a failure of monsoon in terms of either excess rainfall or the deficient rainfall, it either leads to droughts or it leads to the floods. And hence, it impacts the life and livelihood in every part of the globe. So considering this, there has been a significant development from India and also different countries in the globe to enhance the observational systems. As all of us know that monsoon is a cross-equatorial flow, and hence there is a need for enhanced observations over the oceanic areas apart from the land mass. That is the most important hindrance to enhance the observational systems. But over the globe period of time, globally we have been able to exchange the satellite data. Therefore, the satellite data was able to take the observations remotely. At the same time, there's been deployment of buoys and ships globally to continuously monitor the various aspects. Apart from that, there has been various international collaborations to exchange the data, exchange the research products, and organize such colloquium or the workshop to exchange the knowledge, experience, and expertise. So by that way, if you take into consideration the humble beginning of discovery of Himalayan snow cover relationship for the Southern Oscillation Index, we came up with various other global features and regional features related with monsoon. And then, beginning with 1950s, globally, the numerical modeling system developed. And at present, we have got a coupled forecasting system for various aspects of monsoon globally. And in India also, with a joint effort by Indian Institute of Tropical Meteorology, National Center for Meteorological Forecasting, and IMD, INCOIS, and many others, there has been development of the coupled models for climate forecasting. And at present, India Meteorology Department is utilizing the multimodal ensemble of the best climate forecast systems available globally. And with that, we are now providing the forecast for each and every part of the country and also the South Asia. This development has helped not only India, but also all the countries in the South Asian region and also the Bay of Bengal and Arabian Sea region. So what we find that even though there has been spatial and temporal evolution in providing the services to the people, still we have to improve our forecast accuracy. And also we have to improve our spatial resolutions. We therefore need the research and development to better understand and also to better utilize the modeling system. I am sure in this IWM8, with the participation of all the experts and students and researchers and also the practitioners, will come up with very good recommendations to further understand the interseasonal variability, interannual variability, the teleconnections, regional aspects, and the global aspects of monsoon and their predictions. Apart from that, I am sure the recommendations will address the requirements for converting the science into services for the people. And finally, all aspects of socioeconomic conditions of the people are affected because of the variation in the monsoonal features. So whatever understanding we have got, we have to convert it into the wisdom so that it can be utilized by the common man, disaster managers, policymakers, and the decision makers across the globe. So with these few words, I express my deep gratitude to the organizers for giving me an opportunity to speak on this occasion, and I wish the IWM8 a grand success. Thank you.
Thank you, sir, for your remarks. Moving forward, we are privileged to have Dr. Hindumati Palanisamy with us. Dr. Palanisamy is an oceanographer specialized in space-based and in situ ocean observations with a PhD in space oceanography from the University of Toulouse and French Space Agency in France. Prior to joining WCRP Secretariat, she was a senior research uh, scientist at the Center for Climate Research, Singapore, where she focused on developing regional sea level research expertise in the Southeast Asian region. Earlier, she worked for the European Space Agency's Climate Change Initiative, that is Sea Level Budget Closure Project in Toulouse, France. At the WCRP Secretariat, she is responsible for supporting three of the WCRP's core projects that include CLIVAR, GVEX, and SPARK. In addition, she also provides support to other activities of the new WCRP and closely works with the WCRP Secretariat staff. Ladies and gentlemen, we are honored to have Dr. Palanisamy with us, who brings a wealth of knowledge, experience, and insights. Without further ado, let's welcome her to address this gathering.
Distinguished guests, dear colleagues and friends, it is a privilege today to join you here at the 8th WMO International Workshop on Monsoons. On behalf of the World Climate Research Program, I extend my sincere gratitude to the Indian Ministry of Earth Sciences, Indian Meteorological Department, Indian Institute of Tropical Meteorology, International Monsoons Project Office, and my sibling program, World Weather Research Program, for convening this important gathering of experts dedicated to advancing monsoon science. From our past speakers, Dr. Krishnan, Dr. Ravichandran, and Dr. Mohapatra, we heard the importance of monsoons research. Dr. Mohapatra recently spoke about the history of monsoons research internationally and also in India. At the World Climate Research Program, monsoons are a key scientific priority with significant efforts driven by various of our core activities. The CLIVAR GVEX Monsoons Panel plays a crucial role in coordinating international research on monsoon system. The panel leads research on monsoon variability, prediction, and long-term changes, integrating atmospheric, oceanic, and land surface expertise. This workshop is key to advancing monsoon science, offering a platform to explore monsoon variability, enhancing prediction, assessing climate change impacts, and most importantly, to be able to strengthen research to operations collaboration. The research presented here will not only advance WCRP's scientific priorities, but also contribute to global initiatives across multiple international programs. As we engage in this week's discussions, let's focus on not only advancing monsoon science, but also making sure we strengthen partnership and deliver knowledge that supports resilience in monsoon-affected regions. Thank you to the organizers and participants for your dedication. I would like to specifically thank Dr. Krishnan, Dr. Rajagopal, and Professor Yali for their tremendous work in organizing this workshop. I look forward to the insights and collaborations that will emerge from this workshop. Wishing all of us a productive and inspiring event. Thank you.
Great thanks to you, ma'am, for your insightful address. We are glad to have Dr. Nico Caltabiano, Scientific Officer from WWRP, here with us today. Dr. Caltabiano is an oceanographer with a master's degree in ocean remote sensing and PhD in oceanography at the University of Southampton, UK. His responsibilities for the WWRP include support for the new WWRP core projects on sub-seasonal to seasonal application for agriculture and environment, polar coupled analysis and prediction for services, and integrating prediction for precipitation and hydrology for early action, and is supporting multiple working groups. He is working closely with WCRP and Global Atmospheric Watch colleagues in many activities. Earlier, he was the part of WCRP Secretariat and also served as Deputy Executive Director of the International Climate Project Office and Project Manager of Climapolis Laboratory and EQ Watch project at Max Planck Institute of Meteorology in Hamburg, Germany. With this brief introduction, I invite Dr. Caltabiano to kindly address the gathering. Sir, you may please begin your address.
Distinguished guests, dear colleagues, my friends here, Krishnan, Hindumati, Hajagopal. I'm delighted to once again be here in Pune, here at IITM. This is my third time here, so it's always good to see many of colleagues and friends that I made here. This time, I'm here to join all of you, at the 8th WMO International Workshop on Monsoons. On behalf of the World Weather Research Program, I also extend my gratitude to the Indian Ministry of Earth Science and the Indian Meteorological Department for their strong support to the event. To the Indian Institute of Tropical Meteorology, IITM, for generously hosting us, and the IMPO, particularly Dr. Hajagopal, for its key role in the organization. I also want to acknowledge the World Climate Research Program for working alongside the WWRP, and particularly Hindumati, and many other partners to advance the global research agenda on monsoons. And last but not least, a special thanks for Dr. Krishnan and Dr. Yali Lu for their leadership in organizing an outstanding program for the week ahead. I don't need to repeat what Hindumati has mentioned about the importance of monsoons. You all know how important it is in doing the research that we are doing. The World Weather Research Program, particularly through the coordinated work done by the Working Group on Tropical Meteorology Research, also plays a critical role in advancing our understanding of monsoons. And with the launch of the new projects under the latest implementation plan, WWRP is committed to work hard towards this knowledge being translated into actionable services for communities and decision makers worldwide. This commitment is especially significant as we celebrate this year the 75th anniversary of the World Meteorological Organization, a milestone that highlights decades of progress in weather, climate, hydrological, and related environmental services. The theme, Science for Action, highlights WMO's dedication to transforming research into real-world solutions that protect lives, strengthen economies, and build resilient societies. Throughout this week, our discussions will give us a better understanding of key aspects of monsoons, but also the gaps, challenges, and opportunities to advance the science, leveraging innovation and emerging technologies to improve prediction capabilities. A deeper understanding of monsoons' impacts will, in turn, help translate scientific insights into more effective policies. I encourage everyone to engage in meaningful discussions, share knowledge, and explore new collaborations and partnerships that will drive monsoon research forward. Once again, I extend my sincere appreciation to all the organizers, particularly Dr. Krishnan and Professor Lu, for their dedication in shaping an excellent program. If I was in Brazil, for those who know me, I'm originally from Brazil, I would make a statement about football, but I am in the nation of cricket. So let's play a captain's knock and send it to the stands. Let's make IWM8 a rewarding and insightful event. Thank you all.
Thank you, Dr. Nico Caltabiano, once again for sharing your valuable remarks and for taking the time to be here with us. It is now time for the official e-release of the abstract proceedings, which encapsulate the essence of the research and discussions that will take place over the course of this event.
To mark this important occasion, I would like to request our dignitaries to release the abstract proceeding of the workshop. I request Dr. Krishnan to do the honor of e-release.
Workshop has received an overwhelming response with over 300 plus abstracts from national and international participants. I think that is a big achievement. The abstract proceedings are a testament to the hard work and dedication of all the participants and contributors.
So I thank you everyone for unveiling the abstract volume. With this, now I request Dr. E. N. Rajagopal, Executive Head IMPO and convener of IWM8, to please come and propose a vote of thanks. Sir, please.
Good morning to you all, and welcome delegates to IWM8 and IITM. So I have the duty of proposing the vote of thanks. I start with, would like to first thank Secretary MOES, Dr. M. Ravichandran, for his inaugural address and for all the support and approvals for organizing this workshop at IITM. And our thanks are also due to Dr. M. Mahapatra, Director General of Meteorology and Permanent Representative of India with WMO, for his online address as guest of honor, and also for all the support for organizing this workshop at IITM. Next, I would like to thank Dr. I.A. Krishnan, Director IITM, Co-Chair IIS International Workshop on Monsoons 8th Series International Scientific Committee, for his inspiring welcome address. He's agreeing to host IWM8 IITM, and his unwavering support in organization of IWM8 to me as well as to the whole LOC. Thank you. Next, I would like to thank Dr. Hindumati Palaniswamy, Scientific Officer, WCRP, for her address to the IWM8 delegates. We are also grateful to her for her constant attention, suggestions, and support in the organization of the workshop during last 1 year. I would like to thank Dr. Nico Caltabenio, Scientific Officer, WWRP, for his address to the delegates. We are also grateful for his constant attention, persuasion, suggestions, and support in organization of the workshop. And he was also instrumental in suggesting that we should be taking a registration fee for this IWM8, which is for the first time it's happening. Thank you, Nico. So our finances are better. So I would like to thank the program division of MOES, especially Dr. Kamaljeet Ray and Shika John, for pursuing and obtaining timely approvals and clearances from Finance Division, Ministry of External Affairs, and Honorable Minister of Earth Sciences, Government of India, for organization. We are greatly indebted to the co-chairs, Professor Yali Lu and Dr. Krishnan, and members of the IAC of IWM8 for the great support in finalizing the scientific themes of IWM8, abstract evaluation, scientific program of the workshop. I would also like to thank the identified chairs, rapporteurs, for the smooth conduct of the sessions during the course of the workshop. And would like to thank all the participants who submitted abstract to the workshop and are participating in the workshop on-site as well as online. I would like to thank all the LOC members for extending their wholehearted support in the various organizational aspects of IWM8. I would like to especially thank the various IWM subcommittees and IITM for their great efforts in coordinating this major event. We'd like to also thank sponsors of IWM8. Currently, we have only one, ISGS and Vaisala, for sponsoring and supporting us. We'd like to thank the members of the media and press for the presence and coverage of the event. We'd like to thank all members of all divisions of and sections of IITM for extending their support, including transport, accounts, finance, establishment, electrical, computer, IT, library, and security. Finally, thank one and all who are supported in the organization of IWM, and if I missed out anybody, please pardon me. And I wish all the delegates a wonderful stay in Pune and a productive and useful workshop. Thank you.
Thank you, Dr. Rajagopal, for your cordial vote of thanks. With this, we have now concluded the inaugural session of this workshop. May I now request our dignitaries to take their reserved seats in the front row? Thank you once again for your presence and support. Your participation is greatly appreciated and adds immense value to our workshop. Moving ahead, it is time for a keynote talk by Dr. Chris Davis, Chair, Scientific Steering Committee of World Weather Research Program, who is also serving as the Associate Director, National Science Foundation's National Center for Atmospheric Research, NCAR. He is joining us online and would be talking on West African monsoon and African easterly wave dynamics investigated through moisture sensitivity calculations. Dr. David?
Yes, I'm here. Can you hear me?
Yeah, we can hear you.
Okay.
Just a couple of
Am I
minutes.
sharing my slides?
Yes.
I'm sharing my screen. Okay.
Yeah.
Does that look okay?
Yes. Yes.
All right. Thank you very much. And thank you for the opportunity to give a presentation to this distinguished group. I sincerely wish that I could be there in person to join you, but circumstances prevented my travel. I see many dear colleagues of mine there, so I wish you a very productive and interesting conference, and I will be interested to participate in the conference from afar in this case. I'm used to giving a number of talks about WWRP in general. This time I'm giving a science presentation that highlights the work of a close colleague of mine, Dr. Kelly Nunez Ocasio, who is an assistant professor at Texas A&M University in the United States. And really, this topic touches on many aspects of WWRP because it reaches from the continental scale, the monsoon circulation, to the synoptic scale, the African easterly waves, to the mesoscale that is instrumental in the organized convection, and all the way down to the convective scale. So it cuts across many of the important scales that our science is trying to address, and does it in this interesting and interconnected complex system. And I must also include the human scale, because the societal implications for the monsoon in West Africa, as in other parts of the world, are profound in terms of rainfall, the associated uses for agriculture, water supply, hydroelectric power, and the implications for health are all quite significant. I want to take this moment to also mention that we have a number of projects in WWRP, and my colleague Nico Caltabiano mentioned some of these, and I think it's very exciting. In this context, the monsoons, we have our new SAGE project that is spinning up, which is looking at S2S following on the very successful S2S project in WWRP and WCRP that ended a couple of years ago. So many things going on. I'd like to move into the rest of the presentation now and give you a little bit of an overview of the West African monsoon. The West African monsoon is a seasonal circulation system. We often talk about the warm phase of the monsoon, or the warm season component of the monsoon, and that is depicted, the surface winds at the bottom left, where the Sahara Desert to the north of the Sahelian region, which is the gradient region, gets very hot. The air flows in from the Eastern Atlantic, Gulf of Guinea, onto the continent, and creates a very strong boundary between moist air to the south, just north of the equator, and dry air in the subtropical latitudes. In the winter, of course, it's the reverse circulation with strong northeasterly winds, extremely dry conditions, all the way down to fairly low latitudes. Unlike the Asian monsoon, it is a little bit warmer, I would say. The cold air does not penetrate as far south, but it is nonetheless quite dry. We'll be focusing more on the warm season part of this monsoon circulation. And in association with that, if I take a zonal cross-section of averaged flow features, the prominent flow feature you can see in the plane of the cross-section is the poleward flowing cool air that represents the moist monsoon flow entering the continent. That flow turns to the right because of the Coriolis force, and we end up with low-level westerlies, monsoon westerlies, in this warm season phase. Above that, we have a region of deep convection that spans roughly 5 to 10 or even further north, 15 degrees north. And in conjunction with that, we have the African easterly jet, which often reaches speeds of 15 meters per second or greater, and in the time average is depicted here at about 10 to 12 meters per second. And above that is the tropical easterly jet in the upper troposphere. This fairly complex system is what I'm going to be focusing on. And one of the aspects of this system is it's susceptible to African easterly waves, which grow on the African easterly jet. And they feed off of baroclinic and barotropic dynamics, but also the availability of moisture and deep convection that helps to also fuel the circulation of the wave. And one of the reasons we are interested in the entire life cycle of these weather systems is that once they reach the Atlantic Ocean, they can turn into tropical cyclones, which we call hurricanes in the Atlantic Basin. And these can become quite intense and have profound impacts for many areas of North America. So it's important to understand how these African easterly waves develop and how different changes in their environment may affect the dynamics in this very complex and interconnected region. And so in this talk, I will briefly summarize I have briefly summarized some aspects of the West African monsoon system, the interconnected land-atmosphere interaction, the deep moist convection, the mesoscale systems, easterly waves, and monsoons across scales. And in all these scales, water vapor is an essential aspect of the interconnectedness. And so a logical question is perhaps how does the system behave when water vapor is perturbed? And in a substantial way, as you will see we do in this presentation. And what can we learn about the multi-scale dynamics through this lens? We're going to take a simulation approach in this talk, and we're going to be using the model for prediction across scales, MPAS. That is a global model by design, but it also has a regional model capability. And this is very useful for perturbing lateral boundary conditions. We aren't going to run this model for a long time. It's only going to be roughly a 5-day simulation. You can think of this as a case study. And we're going to introduce significant moisture perturbations, drying the entire domain as much as 50% and moistening as much as 20%. The other novel thing about this simulation setup is its variable resolution. Even though it is a regional model, it starts out at a 15-kilometer mesh near the boundaries, denoted by that red rectangle, and transitions gradually to a 3-kilometer grid spacing over most of the West African continent, where we can explicitly represent deep moist convection. We also run a small ensemble just to make sure that we're not attributing undue significance to any one particular simulation. And we're going to look at a period prior to Hurricane Helene in 2006. So this is our simulation setup. And when we run it for 5 days, you can see the different precipitation amounts. By design, the dry simulation produces very little precipitation. It's not strictly zero, but it's very small. And so we get to examine the dry dynamics in this monsoon system. It's still a monsoon system, but without moist convection, it's very different. We have our control simulation on the top, and we have a moist simulation in the middle, which, as you might expect, with increased moisture, we see more precipitation. But the story of moisture in this presentation is actually going to be more complicated than you might imagine. A lot of the diagnostics we're going to be doing are over that red box. That's our continental box. So when we look at properties of the African easterly waves, it'll be over that continental region there outlined in the box. But I'm also going to spend a little bit of time talking about what happens to the waves as they move offshore over the Atlantic. Now, in this kind of region and in other regions, it's convenient to use what's called Hofmüller diagrams, which are time longitude diagrams, where the averaging is in the latitudinal direction over roughly 5 to 15 degrees north, which is basically centered on the easterly wave maximum amplitude. And the easterly wave cyclonic circulation or easterly wave trough positions in this time longitude space are denoted by the small blue circles that you can see, and I'll try to indicate that with my cursor here. Hopefully you can see that. This is the easterly wave track. They're westward moving waves. And within those waves, there are organized convective systems. You can see here in the iMerge data, and you can see perhaps better organized systems in the control simulation propagating fairly rapidly to the west, where faster than the wave. You note that the convection is all represented by the rainfall. The convection is all to the west side of the wave, that's downstream of the wave, that's leading the wave in this particular case. Once the system moves offshore, which is the coastline here, is denoted by this vertical line, the convection becomes a little bit more in phase with the wave trough, and this is one of the factors that contributes to tropical cyclone formation. Now, in the moist and dry simulation, what happens is, let's look at the dry simulation first. The dry wave actually propagates faster to the west. It reaches minus 35 degrees west sooner than in any other simulation. The moist simulation wave propagates more slowly. It still exhibits a number of the convective features that you see in the control simulation, but the wave moves notably more slowly, especially after it moves offshore. And we're going to examine why that is in just a minute. Well, one of the important factors to consider is what is moisture and moist convection doing to the zonal mean flow over this region? And this is a plot of the zonal mean zonal wind averaged over the time of the simulation. And on the left is the climatology from the ERA5. And it shows the African easterly jet around 700 to 600 millibars, and the tropical easterly jet around 250 millibars, just like we saw in the previous climatology that I showed. And we can see the control simulation does a pretty good job in representing that. Now, when we add moisture, these easterly jets become more intense, as does the monsoon westerly flow down here between 5 and 10 north. When we take away the moisture, the sharpness of the easterly jet diminishes. The jet becomes very spread out. It weakens. The tropical easterly jet almost disappears. Well, not disappears, but it weakens substantially and lowers. This is because we've pretty much eliminated the effects of moist convection. And we can see here that moist convection is also important for establishing the monsoon and moving it poleward. We see the profound effects of moisture on the mean flow in this case. And when we look at vertical profiles of that zonal mean wind over the region where the African easterly wave persists, you can see that the easterly jet is weaker in the simulation with more moisture. And when we look at the phase speed of the wave plotted against the zonal flow speed, the X's represent a layer average between 500 and 700 millibars. And we can see that the waves in the moisture simulation travel more slowly because the zonal mean flow is diminished. It's not so much an aspect of the convection and the wave structure, although there are small effects there that we can look at. It is mainly an effect of the mean flow. So the mean flow changes, the wave speed changes. What about the wave intensity? Well, the easterly waves, important factor in the intensity of easterly waves in this environment is the way the convection interacts with the wave. You can see here, however, that in these vertical mass flux profiles, the region with the strongest upward mass flux, which is where most of the convection is, resides in the northerly flow. It is roughly in quadrature with the wave trough over here, where there isn't a whole lot of deep convection in the trough itself. This is a situation where the wave would be propagated faster to the west. And we can see that in the control simulation, the vorticity stretching inferred because of this vertical mass flux would be a bit stronger than in the moist simulation and act to propagate the wave a little faster as well. So these two factors combine, with the mean flow change being larger, the propagation tendency being smaller, to move the wave in the control simulation a bit faster to the west. And the convection in this case, because it's out of phase with the wave, is not really intensifying over the continent, intensifying the wave. Now, what happens when the wave moves offshore? So this is a time series of the wave-centered relative vorticity averaged over a roughly 5 degree by 5 degree latitude longitude region. And we can see that the dry wave is weaker. There is very little convection. Convection is helping to fuel the wave to some extent, although remember I said the convection for the most part is not strongly amplifying the wave. It really serves to amplify the wave only in this initial phase, and then the wave amplitude is relatively constant over the African continent. Here's where it reaches the coast, and then you see a profound difference between the two simulations. The moist simulation, maybe surprisingly, produces a weaker system as it moves over the Atlantic. And we can begin to understand some aspects of that by looking back at the Hofmüller diagrams. Now, the Hofmüller diagram here is a zoomed-in version of what I showed earlier for the control simulation. And it will show that the area of the wave trough, as it moves to the west, you see the convection is persistently to the west of the wave trough. But what happens in the simulation with moisture is that as the wave reaches the coast around this time here, a lot of the convection ends up on the east side of the wave trough. That's because the wave is passing the Guinea Highlands, and in the simulation with increased moisture, the convection actually becomes it loses its intermittence, it loses its diurnal cycle. It actually lasts for almost 2 days in general. You can see the vertical streak here on this Hofmüller diagram. So the convection becomes quasi-stationary, the wave passes through, and you end up with an unfavorable relationship spatially between where the convection is and where the wave trough is. Instead of being in the trough or downstream of the trough, the convection is upstream of the trough. That actually slows the wave down, and it actually contributes to weakening the wave as the wave moves offshore, because now you've disrupted the phase relationship between convection and the wave. So this is an interesting aspect of the simulation we'd like to look into a little bit more to see if this kind of thing happens more generally. And let me just here wrap up with a summary slide, maybe time for a couple of questions. So one thing I'd like to note is that moisture perturbations do have a large effect on different spatial scales in the West African monsoon on a time scale of only a few diurnal cycles. So this is more of a weather type simulation where we're looking at short range prediction effects. And of course, these perturbations are quite large, I might add. So we expect to see some significant effects, but it nonetheless gives us maybe some insight as to what's going on in this system. The zonal mean state changes markedly in response to moisture. The African easterly jet does push northward as the whole monsoon itself pushes further north. That leads to a number of changes. One is that the easterly waves slow down by a couple of meters per second, and it's quite noticeable, even over the continent. And upon reaching the West African coast, with greater moisture, we have persistent convection over the Guinea Highlands while the wave passes through. This makes the wave go slower. It actually weakens the wave because of a increasingly poor phase relation between convection and the wave, and this may have implications for tropical cyclone formation. I would hasten to add that this is really looking at one case. And so the question that naturally comes up is whether there's evidence of this kind of effect in other environments and in other cases. And we have yet to look at that, but that is an activity for the future, as well as looking at longer integrations with more, I would say, climate change relevant types of perturbations. And that's an active area of research that we're pursuing now. That's all I have. I want to thank you for your attention and welcome any questions. Thank you.
So it is now time for question answer session. If we have any quick questions, we can take it now. Hello.
Thank you, Chris. That was an excellent talk. I just wanted to know how you perturb the moisture in your experiment, the moist experiment.
Thank you, Dr. Krishnan. What we do in this experiment is we perturb the initial and boundary conditions of water vapor. Everywhere in the domain, we add an amount of water vapor equivalent to either a plus 20% humidity perturbation or a minus 50%. We, of course, have to bound those perturbations because we cannot achieve supersaturation, nor can the water vapor become negative. And so within those constraints, we come up with a perturbed water vapor, and that implies also hydrostatically changes in the pressure field that are also accounted for in the model.
But you don't change the other parameters, like circulation parameters.
We don't change anything else, right? That's right.
Thank you.
Thank you, Krish, for the nice talk. I just want to know that whether African easterly waves or the westerly monsoon winds, which will be the more significant to bring the rains for the African region? It's the dynamics of the wave or the wind?
So I think one way to think about it is the easterly waves modulate the monsoon rainfall. So without the waves, you would have a more widespread contiguous rainfall along an ITCZ, an intertropical convergence zone. But the waves propagate through, and you have enhanced and suppressed phases of the wave with respect to convection. So the two really work. I'm not so sure I would say they work in tandem, but the easterly waves will modulate the monsoon. And of course, the monsoon provides the mean flow in the environment for the easterly wave.
Do you have any other questions? If not, can we check it online? Have we got any questions there? Okay. So in that case, let us thank Dr. Davis for an interesting and engaging talk. Thank you very much, Dr. Davis. Now, before we break for a high tea, I have few quick announcements. So from this hall, we'll first gather for a photo session outside of this auditorium. And media personals could gather in the front row for interactions. And following the photo session, we will proceed for the high tea, which has been arranged at the basement of this auditorium. And participants can complete their registration formalities during the high tea. Also, those who are having their talks, they can upload their presentations here during the tea break. And foreign nationals who have not filled the MEA verification form may do it at the registration desk, which is there at the reception of this auditorium. And posters of the participants are being displayed in the Riturang first floor for everyone to view at their own convenience. So our volunteers are there who will guide you to the Riturang Hall and for any other issues you might face. So our volunteers are wearing this kind of maroon colored tags. So you can contact them for any help you might need. Again, thank you one and all for joining. Please assemble here at sharp 10:50 IST, Indian Standard Local Time, for the first scientific session of this workshop. We'll now break for the high tea. Thank you. Yes, yes, group photo first.
Requesting everyone to please assemble here. We will be resuming the session shortly. Okay. Yeah, is it?
Attention, please. We are resuming this session shortly, and we request our presenters to kindly upload their presentations here, or if you have already done that, then you may ignore this.
Molto bene.
Welcome back, everyone. I hope you all are feeling refreshed and ready to dive into the next session. We'll now begin with the first scientific session of the day. The theme of the session is regional monsoons of the world and their multi-scale processes. I request Professor Yuki to chair and conduct this session. Can you come on the dais? And rapporteurs for this session are Dr. Rashmi Kakatkar and Yashas Tirumurthy.
Okay, very good afternoon, very good morning to everyone. So now this is our first session. So without delay, because we have already delayed by 10 minutes or so. So I invite our first invited talk from Madam Liu. And the talk is on a global view on microphysical discrimination between heavier and lighter convective rainfall.
Okay, can you hear me?
Yeah.
Are you looking at my screen? Is my screen show okay?
Yeah.
Okay.
Yes, we can hear nothing.
Okay. Okay. Sorry for not being able to meet you this time. And I wish IWM8 a very productive conference. And also, I appreciate the opportunity for me to give this talk entitled A Global View on Microphysical Discriminations Between Heavier and Lighter Convective Rainfall. And this is a collaborated work with my colleague at NUIST, Dr. Ritz Shi. Two previous studies have examined the overlapping fraction between extreme precipitation and very intense convection worldwide. And they both used the extreme data, but one of the studies found quite a small fraction, mostly below 30% over the land. And the other one, in contrast, they found a much larger fraction exceeding 60%. Although their results differ quantitatively, they both indicate that extreme rainfall can be produced not only by the very intense convection, but also by convection with moderate or even weak convective intensity. A more recent study by Xu et al. Also used the extreme data. They pointed out the weak and strong convection contributes about equally 30% respectively to the global extreme precipitation events. Our study for the coast area of South China found the intense convection tends to increase with more extreme rainfall, while the weak convection tends to decrease with the more extreme rainfall. All these studies and probably many other studies have shown convection can produce both high and low rain rates, regardless of their convective intensity. But it's still not very clear, especially from a global view, what happened in convective clouds that results in disparate surface rain rates. Therefore, in this study, we try to identify the microphysical distinctions between heavier and lighter rainfall in convective precipitation events worldwide, and also try to explore the key atmospheric conditions driving these microphysical differences. We also use the trim data and the GPM data from the satellites and the ERA5 reanalysis from ECMWF. We define a convective precipitation event, CPE, as a three-dimensional precipitation region composed of at least 4 convective precipitation pixels, which means the area is at least 80 to 100 kilometers squared. Each CPE is classified by the rain rates. If the maximum rain rate of a CPE is above 60 millimeter per hour, it is considered as a high ring producing CPE. If the run rate is below 30 millimeter per hour, it is considered as a low ring producing CPE. Otherwise, it is a medium ring producing CPE. Meanwhile, each CPE is also classified by the convective intensity, which is measured using the maximum height of 30 dBz radar reflectivity. If this height is above 9 kilometers, this CPE is considered as very intense convection, intense CPE. If this altitude, this height is below 5.5 kilometer, it is considered as a weak CPE. Otherwise, it is a moderate CPE. We also use Cloud Model 1, CM1 developed at NCAR to do some cloud permitting ensemble simulations for 3 selected cases. Case 1 represents high ring producing intense CPE. Case 2 represents low ring to medium ring producing intense CPE. Case 3 represents high ring producing weak to moderate CPE. For each case, we conducted ensemble simulations by perturbing the initial state a little bit in order to get more robust results. Now let's first look at the spatial distribution of the CPEs. Clearly, the intense CPE are mostly land-based, while the moderate CPE and the weak CPEs are mainly in the ITCZ and monsoon regions. There are 6 convective hotspots on the land. They are Southern North America, the Amazon, the Central Africa, South Asia, Southeastern China, and the Maritime Continent islands. Over these regions, the intense CPE produce high ring or low ring events in roughly equal proportion, about 30 to 50%. As the convection weakens from intense to moderate and further to weak, we found that the proportion of high ring events decreases, while the proportion of low ring events increases substantially. So this means that the intense CPE have a much higher probability to produce the high ring rate. The vertical profile of run rate further suggests that those intense CPE can also produce much more extreme rainfall near the surface. For the intense CPEs, we further compare those producing high rain with those producing lower rain rates. We found that over the global land, the intense CPE producing high rain rate tended to have even stronger convective intensity than the intense CPE producing lower rain rate. So for the intense CPE, what are the major macrophysical processes that different between the high rain and the low rain events? We found that the high rain producing intense CPE show faster increase in rain rate, reflectivity, and ice water content from about 7 kilometer to 5 kilometer altitudes. This indicates stronger rhyming process. This results in higher liquid water content just below the melting level, which is about at the 5 kilometer altitude. This can enhance raindrop coalescence downward and intensify surface rainfall. And the difference between red and the blue lines become larger with decreasing height. This indicates the importance of liquid phase microphysics in determining the near surface rain rates. For the weak CPE events, we also found that the differences between high rain and low rain events become more pronounced with decreasing height below the melting level. So the liquid phase microphysical processes play a crucial role in determining the surface rain rate for both intense CPE and weak CPE. And then we examine the liquid phase microphysical processes. Firstly, in the intense CPE, we found that we discussed this using this type of figures. This shows the changes in mass-weighted mean diameter, and this is changes in the radar reflectivity from 3 kilometer to 1 kilometer height. So compared to the low rain intense CPE, the high rain intense CPE show a higher combined fraction of coalescence and coalescence breakup balance, and a lower fraction of raindrop break, and a much larger increase in the maximum reflectivity from 3 kilometer to 1 kilometer altitude. This indicates more active the coalescence. For the intense CPE to produce high rain rates, strong ramming aloft alone is not sufficient. It requires support of warm rain processes, is specifically more coalescence and less breakup. For the weak CPE, we also found that compared to the low rain producing events, the high rain producing events have a much larger fraction of coalescence and coalescence breakup balance combined, and a much smaller fraction of raindrop breakup. During the raindrops descent, we found the increase in the mass-weighted mean diameter and also in the maximum reflectivity are significantly larger, indicating more active coalescence for the high rain production. And our Cloud Model 1 simulations strongly support the satellite data observation results. Case 1 represents high rain producing intense CPE. Case 2 represents also intense CPE, but only produce low to medium rain rates. We found that in case 1, the coalescence and the coalescence breakup balance rise from 28% to 52%, while the breakup drops from 54% to 25%, also with much smaller reduction in the mass-weighted mean diameter in the high rain producing intense CPE. For case 3 that produce high rain rate, but only with weak to moderate convective intensity events, we found the coalescence almost dominates. It contributes, accounting for 92% with very minimum breakup. Now we'll look at the features of the raindrop size distribution at 1 kilometer. So for CPEs with the same convective intensity, the key difference between the HR to the right and the LR to the left is a significantly higher raindrop concentration in the high rain producing events. For the high rain producing intense CPE, we found that it is relatively located closer to the continental region compared to the maritime region, but it has higher concentration and a larger size than the continental region. For the high rain producing weak CPEs, it is very close to the maritime region. It has the highest concentration, far above the high rain producing intense CPE. And this maritime-like characteristic, it's located in the upper portion of this maritime region, so which means the raindrop concentration is really high. So in order to find out the important environmental conditions for the high rain rate production, we calculated lifting condensation level of free convection, difference between temperature and the dew point temperature at 600 hPar and also at 850 hPar. We found that compared to the LR, low rain producing CPEs, the high rain producing CPEs have much lower level lifting condensation level, which means lower cloud bases and thicker warm cloud layers. And also we found more humid mid-troposphere and lower troposphere for the high rain producing CPEs. And compared to the high rain producing intense CPEs, the high rain producing weak CPEs feature even lower cloud bases, and which means thicker warm cloud layers, and even more humid mid-troposphere. All these conditions facilitate more active and efficient raindrop coalescence, which could compensate for the absence of mixed phase microphysical processes for the high rain producing weak CPE events. The other atmospheric parameters we examined, such as CAPE, SIN, and vertical wind shear, do not show significant differences between the high rain and the low rain producing events. I think this is at least partially due to the limitations of the real analysis data. Then the vertically integrated moisture flux and its convergence are examined, not only for all the CPE means, but also for the anomaly. of each type of CPE. We found that for the three monsoon regions, the Amazon and the South Asia, and the maritime continent islands, when there is a high rain producing intense CPE, the monsoon flow from the ocean intensifies compared to all the CPE mean, which enhances the moisture flux convergence. At the low rain producing intense CPE moments, the monsoon flow relatively weakens with reduced moisture flux convergence. For the high rain producing weak CPEs, the monsoon flow is even stronger than that with the high rain producing intense CPE. For the CPEs over Southeast China, we also found that when there is a high rain producing intense CPE, an anticyclonic moisture flux anomaly appears over the Philippine Sea, while the low rain producing intense CPE is accompanied by a cyclonic anomaly. So this leading to stronger and weaker moisture convergence in the high rain and low rain intensity respectively. With the high rain producing weak CPE over Southeast China, we found that this region experiences a cyclonic moisture flux anomaly, resulting in even stronger moisture convergence than the high rain producing intense CPE. For the South and North America, if there is a high rain producing intense CPE, an anti-cyclonic moisture flux anomaly off Mexico's west off coast and the southerly flow anomaly over the Gulf strengthen the moisture flux convergence, which is also aided somehow by the anomalous northerly transport from the northwest Atlantic. The LR, low rain producing intensity, just shows the opposite. For the high rain producing weak CPEs, anomalous westerly moisture transport from the tropical eastern Pacific forms a cyclonic anomaly over the Gulf, intensifying the moisture convergence. So to conclude our major findings, firstly, the intense convection involves vigorous mixed-phase microfluidic processes with stronger rhyming, leading to larger rain rates at and above the melting level compared to weak convection, and possibly more extreme rainfall at the surface. Warming processes are important in determining the rain rates. Intense CPEs are dominated by raindrop breakup, and weak CPEs are dominated by coalescence. With comparable convective intensity, the high rain producing CPEs correspond to much enhanced coalescence and reduced breakup and substantially larger raindrop concentration. The higher rain rates result from more humid mid-troposphere and lower troposphere and thicker warm cloud layers due to significant variations in the water vapor channels. The high rain producing weak CPEs at the convective hotspots on land are accompanied by the strongest large-scale moisture flux convergence among the various CPEs. Thank you very much for your attention. That's all I have.
Thank you very much for presenting in time. So we have time for a quick 2-3 questions from our esteemed audience.
Yeah, any question?
Any question from anyone?
Okay, do we have any online questions? Can you check it?
Yeah, is there an online question?
No.
Yeah, that's a good talk. I just want to know that as a mixed phase you mentioned. So what is the role of orography in making these heavy rains? Have you done any work on that?
I'm sorry, I beg your pardon? So your question is?
Because like Southeast Asia, most of the rainfall we get in the West Coast due to orography effects. So whether you have examined the role of orography in your big space warm rainfall?
Oh, so far we just compared the composite fields for each, type of the convective precipitation events. So yeah, we can do more analysis. Actually, we are doing more analysis by conducting more numerical simulations and make more deeper calculations for the macrophysical processes. Yeah. But I may not answer your question very well.
Yeah, because you said in South Asia, maximum rain we get due to orographic lifting, either
Yeah.
west or northeast India.
Yeah, I'll be very happy to discuss with you, later in the future,
Sure.
Okay.
Any other questions,
Okay.
comments, suggestions? It's a very excellent talk. So
Yeah, we can discuss later.
yeah, one more question is there.
Thank you for a very interesting talk. So I have some question about you divided some different types of the convections, create high rainfall and low rainfall, and sometimes very low and very high. And so in this sense, do you have any good information about the in what season, in which region, so in which some specific type of rainfall convection prevailing? So such a location and seasonal wise distribution, if you have any question, any information about that, I can ask you about that. So it is my question.
Oh, yeah, in this talk, I just show you the warm season, for all the land regions, warm season. So in this talk, I didn't talk about, like sub-regional variations or in sub-seasonal variations, but I know there are many, such informations. Yeah, I'm open to communicate with you later about those questions. Okay, thank you.
Okay, thank you.
Okay. Okay. Thank you.
So thank you very much. So we'll now go to our second invited talk. It will give you by Dr. Suryachandra Rao from IITM.
To may present about the monsoons panel activities in this workshop. As you know, monsoons panel is also one of the organizers of this workshop. So here, what we are trying to present is that what are the monsoon panel recent activities that have been taking place, so that to sensitize all the people who are here, and also to develop cross collaborations with monsoons panel. That is the whole idea of this presentation. So here we have two co-chairs. One is Professor Laila from USA and myself, Suryachandra Rao from India. We both are leading monsoons panel activities. Actually, monsoons panel is a both Clever and GX combined working panel, and these both communities are contributes to for memberships, funding, everything. So, and also you can see that we have websites that are listed there so that you can go and check that. So this came into existence with this form since 2014 after GX conference. So prior to that, there used to be individual panel, particularly on Asian Australian monsoon panel that used to be there. But after 2014, all these different monsoons, American monsoons and African monsoons, Asian Australian monsoons are combined together and made a single monsoons panel. So the overall, the panel objectives is, this is the overarching goal, advancing understanding of monsoon variability and improving its prediction. If you look at IWM8 focus is exactly matching with monsoon panels overarching goal. So it is mostly understand the variability and improve the predictions. That is the overarching goal of monsoons panel. And how do we do it? We try to bridge links between different scales from synaptics to large scale and in intermediate scales, and what are the physical processes that are involved in improving the skill. That is the most important part that we are trying to address in the panel. And also we started looking at different new methods to enhance monitoring and advance diagnostics and improve models. So as you know, AML is becoming part and parcel of each and every research activity that is being taken place, and Monsoons panel is also not an exception. We also start using AML methods in our activities as well. So we also have a more elaborate process studies coordinated with modeling activities, and also most importantly, empowering the next generation of scientists around the world to advance our knowledge of monsoon systems in key regions of interest. So we have a strong human resource development activities also part of Monsoons panel activities. So the panels, as I said, these are the major activities that we have taken place. For example, when we look at linkage across scales and physical process, what you notice is that most of the current generation operational models have a problem that we have identified, that both the ENSO and monsoon correlation is very, very strong in the models. And we have tried to understand why this is the case. So what we have noticed is that the synaptic scale variability in the models is underestimated significantly. So that is one of the reasons why this relation between ENSO and monsoon is becoming very, very strong in the models. So actually that is the one aspect that is actually limiting the prediction skill of monsoons. Once you improve the synaptic scale variability within the couple models, these are all, this is not a single model is used here. All operational models across NSAP, ECMWF, UKMet Office, IITM, all these models are used to establish this fact that all these models have very strong. So whenever you see a strong ENSO in the tropical first week, your monsoon is going to be below normal. So this is what is noticed in almost all models. So it is like monsoon becomes slave to ENSO. That is what happens. This is happening because if we look at Asian national monsoon, particularly Asian monsoon, the monsoon low pressure systems are not well represented in the couple models. So that synaptic activity is missing in the models. So that is one of the key findings from the Monsoons panel activities that has been now being recognized worldwide, and people are working towards improving the synaptic variability by increasing either the resolution or the physical process or the parameter schemes. So coming to the next new methods to enhance monitoring, advanced improving the models. So we have added several modules to understand how to improve the small scale variability from diurnal to seasonal and various aspects of spatial as well, even the small scale it is in the oceans and in the atmosphere as well. And also we have implemented weekly coupled data simulation. There are 3-4 centers which are now generating weekly coupled data simulation on a regular basis, and we have assessed the skill of this weekly coupled data simulation on monsoon prediction skills. And we are very happy that when you couple it, weekly couple it, at least that is working very well for the predictions, rather than using the standalone analysis that is generated by either ocean and atmosphere separately. Once you couple them, the data simulation is really helping to improve the prediction skill. So this is another contribution from Monsoons panel. So if you look at 2022 or 2023 monsoons, particularly South Asian monsoon, what you notice is that normally monsoon rainfall is very high in the monsoon core region. But these 2 years, even though these years monsoon activity is very normal, but you do get much decreased rainfall over this monsoon core zone. So it has been looked at in detail, and most probably one of our Monsoons panel member will be making a detailed presentation on this. Tia's presentation, that is fourth talk in the same session. She may be talking about more details about this. She shows it is beyond lake connections that is responsible for this. So empowering the next generation of scientists, we have organized several webinars And also we are get involved in different regional climate outlook forums to make the stakeholders to understand what are the limitations of the models and how best you can utilize these products. That is one of the most important activity of research to operations. That is one of the very important activity. I think within the Clever and GX, this is one of the panel that really takes off R2 very seriously. And it actually talks directly to the stakeholders and implements this activity very seriously. So now at present, we are looking at these problems to understand different other challenges, particularly in monsoons panel. At present, we are mostly focusing on the modeling part because observations is very expensive thing to do it. And there have been several experiments which have been already done on experimental side, but very few studies have focused on modeling aspects. So the present focus of monsoons panel is mostly on model skill development or how improve the process understanding. All those things are the most important focus of the present panel. And as I told you before, so we are trying to see the how well the skill of the models is improving with different state-of-the-art models with the different generations, by whether by increasing the resolution or by increasing the more component system components. Now you know that now seasonal prediction started with a standalone AGCM, then it became coupled GCM. Now we are even looking at ESM to be used for seasonal prediction aspects. So there is this paradigm shift that is happening at all different scales. Even for NWP, coupled NWP is becoming a norm for making new weather predictions. So we are trying to assess the skill of those different flavors of these models to see how well coupled NWBs and ESMs are doing in doing short range and seasonal prediction scales. That is what is one of the most important focus of the panel now. So all other activities I have already touched upon. Particularly, we also promote early career scientists in the working groups. So I will give you more details in the next slides. So basically what we do is we have one panel, monsoons panel, that is directly supervised by Clever and GX, SSGs, scientific steering groups. They look at the activities of monsoons panel, but we do have freedom in deciding how the working groups are Asian national monsoon or American monsoon or African monsoon. So that freedom is left to monsoons panel, and we can decide what are the problems to be addressed, what is the composition of that working groups, everything will be decided by this panel itself. So basically the working groups are given to identify the priority areas in different monsoons, regional monsoons. So you can see that there are more than 60 members folks in monsoons panel activities, if you put them together. I didn't give number of members in American monsoons because it is now going through a revamping of the whole working group of American monsoons. But African monsoon and Asian monsoon are working seriously for quite some time. So if you look at the working groups itself, they have some focused research activities. So the first one, the top right panel shows that working group on Asian monsoons activities. So that subgroup has 3 different subgroups. So one is monsoon process and teleconditions group. That is one which is looking at how the skill of the models is improving in recent generation of the models, and what are the bottlenecks and what are the teleconnections, how the teleconnections are changing. That subgroup looks at that part. And there's the R2O component. As I said, R2O is very important component that is being pursued by monsoons panel. So there is a research to operations component for monsoon seasons in Southeast Asia. Actually, there is no onset definition for Southeast Asia monsoon region. So monsoons panel came up with some ideas about how to define that monsoon onset index for Southeast Asian monsoon. And that is one of the very important activities. And there is another subgroup activity that is high impact weather events. This group looks at how the models are capturing the high impact weather events and what are the bottlenecks and what processes are missing in that models. So just like the previous presentation, this group also looks at all these aspects and try to understand and improve the models in getting these extreme events very well in the models. So there is another regional working group on African monsoons. So in fact, they work in 3 different geographical regions. One is South and East Asia African monsoon, Central African monsoons, and another one is West African monsoons. So there is some controversy whether some of these sub-regions has monsoon or not, but the group believes that it is yet to be identified, and they are pursuing it further in identifying these monsoon conditions at different regional. So this is the composition of the group, and you can see that there are about 12 members and 2 co-chairs, and it is well distributed geographically. Not only geographically, gender balance is also very well maintained in these groups. So both regional and gender balance is maintained very well in this monsoons panel. So thanks to WCRP project office, Hindumati and Usan, who have really helped us to put up some series of webinars organized as an activity of WCRP academic activity. So we have conducted 4 different webinars, and you can see that they are very well appreciated by world over. So one is on global monsoons, another one is national monsoon, third one is African monsoons, and fourth one is African monsoons. So you can see that they are very well received, and the number of views are increasing. As of today, these are the number of views. After attendees, this many views happened on YouTube, so that people are more than 1,500 people have gone through these webinars and getting more and more knowledge. So our next generation scientists getting training is very well seriously taken in the monsoons panel activities. So we also conduct several workshops like this. So in the same room, there was a STIPMEX workshop that was conducted, was one of the part of APARC and monsoons panel. And we have done, it's done in the same hall. And the theme was observational modeling aspects of the stratosphere, troposphere, coupling process, and extreme weather events associated with Asian summer monsoon. And GX Open Science Conference, the monsoon session was organized by again monsoons panel. So monsoons panel is very, very active group, and it has a lot of activities that are going on each and every year. So African climate change and variability and the AMS workshop and African Initiative workshop in UCAR, all these activities have been taken up by this. So this single slide tells you the importance of monsoons panel across different panels or lighted activities across WCRP, different activities. So we have a strong collaboration with Indian Ocean Regional Panel, IORP, that is top. So what we are doing there is that we are trying to conduct OSSC experiments to identify the observational network that is required in the oceans to improve the monsoon forecast, at least in the Indian Ocean region. So that is one good activity that is going on at present. And GPEX scientific report was prepared for monsoons side by monsoons panel. They contributed significantly. And one of the monsoons panel member is co-chair of GPEX now, SSG co-chair. And we also contribute to WMO's operational climate prediction system, and also different lighthouse activities of WCRP. APARC, as I showed you earlier, we have a strong collaboration. CLIC, we have trying to establish a strong relation between that group and ours by understanding the teleconnections between polar caps and monsoons. So that work is going on. And there is one program of WCRP that is Q-Windows. So how the observations in the Indian Ocean can influence the monsoon prediction at different scales. So that is very important experiment that is going on. And that actually gives us what are the importance of different observations at different locations. That work is going on. And there is a climate dynamics panel and he is also here. Satyabhanu, he is the coordinating between Monsoons panel and climate dynamics panel activities. So this single slide tells you that how the monsoon panel is going across different panels, and actually we are hands are now full and cannot take any more new activities at this moment. So these are the details. I don't want to read all those details. So I gave you just a brief about each and every activity in the previous slide itself. So lighthouse activities also, we are contributing to different high impact weather events, understanding high risk events of the lighthouse activities. As I showed you earlier, the Asian Australian Working Group also has a strong working group, subgroup that is focused on this activity. And safe landing climate, the African monsoon is working with them. And analysis church is co-chair of GPEX, and Eastern Africa subgroup, WJFM is EP, ESC, LHS. So there is a lot of cross-panel activities that are happening everywhere in this group. So just to give you the gist of what are the activities, R2O, monsoon season in Southeast Asia, that is what I have informed you before. This subgroup meets quasi-monthly and has been exploring wind-based definition of our monsoon season in South Asia. So this is well received by the regional climate outlook firms, and they are actually the stakeholders looking for this information and trying to get an objective-based monsoon season definition so that the stakeholders can use that information in different models. So not only that, they also have started looking at monsoon progression index. And so these are the R2O activities that are happening in Southeast Asian region at this moment. Beyond this, also the SASCOF, from panel, somebody else always goes to the these climate outlook firms and tell them these are the model skills and this is the biases, these are the problems. So better use it carefully, or you can use it with confidence. So that is the information that we always provide them. So high impact weather event group is contributing significantly to different cross-panel activities also now. So with this, I'll stop my presentation. And we are one panel that is very fortunate to have a dedicated project office, that is International Monsoon Project Office. Dr. Rajgopal, who is the coordinator of this workshop, is actually really helping to coordinate the monsoon panel activities, and we sincerely acknowledge his support for this monsoon panel activities. Without him, we cannot organize all these many activities of monsoon panel. So thank you for your attention. I will take you any questions. This is not a focused scientific talk. It is just a marketing talk to give you about the idea of monsoon panel activities and welcome you to monsoon panel. However, getting membership is also very tough these days. Only 50% members will come across, and others we always reject. Okay, thank you.
Thank you, Dr. Surya. Very, very good information about monsoon mission program.
Yeah. You are not supposed to ask the question. You are one of the.
Yeah, let the youngsters ask questions. If you have any additional information.
Sorry. Yeah. No, youngster must ask, but I'm just asking on, on first few slides, you mentioned some science. Okay. So it's very good to hear that, sometime back we identified that the synoptic scale variance is very low in coupled model. And it's good that monsoon panel is recognizing it as one of the highlight. But my concern is different. That I did not so far read any paper, okay, where this hypothesis that you said that if synoptic scale variance is improved, this overdoing of ENSO will reduce. Is there any targeted experiment done? If not, whether monsoon panel is suggesting any, any numerical experiment to establish this? Number 3 is synoptic scale is basically what even Chris said or Yali said and all this. It is basically embedded in the lap of Mother Nature, right? It's the mean flow. So time scale is completely different. Synoptic scale 2 to 10 days, and ENSO is the web number 1, and so on. So how they interact? One pathway may be energetics. Okay, is there any other pathway that have been found? So if you can highlight, it will benefit everyone, I believe.
So
Thank
coming
you.
to the first point, whether there are any model experiments to show that the improving the synaptic variability will improve the ENSO-monsoon relationship. So actually there are couple of papers have been written by the panel members, some of them, and it is getting published in Climate Dynamics in next couple of months. So what is that we have shown there is that if you somehow improve the low pressure systems. So how did we improve it? We have noticed that the SST gradients, there is a SST front in the Bay of Bengal. If you can get that SST front correctly in the models, then you can improve the monsoon low pressure systems. So once you improve that monsoon low pressure systems, then ENSO monsoon relation is getting better. So there is something that we have always missed is that the interactions of diurnal to intraseasonal, intraseasonal to seasonal. So it is well established in the observations, but in the models that relation is failing. So this is the maybe the reason how the scale interactions will impact the ENSO monsoon relation. So that experiment is still has to be carried out. Okay.
Okay, so I think we have running out of time. A quick question from experts.
I have a question actually. Thanks, Surya, for highlighting some of the activities you are doing. So my question is, AI and ML is developing, and I don't know, I didn't see any monsoon panel recommendations. What the activities are happening in the AI and ML? If not, so do you have any other plans, or do you think AI and ML can address some of the issues you are raising here?
So first and foremost, we should admit that we are not experts in AML. We are using AML as a tool at this moment. So we are not at a stage to recommend that these tools are better suited for this analysis or this forecast. So we are yet to evolve ourselves. So that analysis and all that we started, and it is an initiated that activity. So it is not yet full grown to so that we can give some recommendations to the community. That is not yet achieved.
Okay, thank you very much.
Sir, one more.
Sorry, just a question. Yeah, thanks for the nice marketing presentation. My question would be, so how does the monsoon panel look at the activities of kilometer scale global simulations, and especially the coupled kilometer scale global simulations? The point being, we would resolve these mesoscale activities and also hopefully the interaction between MCS and the large scale signals. So my question would be, look, in the future, so do you look at it as a positive development, and do you extend any collaborations with this community?
In fact,
Thanks.
I forgot to mention one of the activities of African Monsoons Working Group is to look at these kilometer scale models to understand how well they are able to capture the African monsoon. So similar activity will be taken up by the Asian Australian monsoon also. Somehow our American Monsoon Working Group is not yet accelerating its activities, but both Asian Australian and African monsoons they are really looking at all these simulations. So those results will come out in maybe in next 1 or 2 years.
Okay, any other question? If not, let us thank Dr. Surya for a very excellent marketing presentation.
I request the session chair to kindly felicitate our distinguished speaker, Dr. Surya Rao.
Now we move to some oral presentations. The first one in this is by Professor Toru Terao. So 15 minutes is the time allocated, and you can leave 1 to 2 minutes for the questions.
Good afternoon, everybody. So I'm now coming. I come from Japan and from Kagawa University. Sorry. So I come from southwestern part of Japan, and so I'd like to talk about something about the ASEAN region, ASEAN monsoon dynamics, and some of the interested in the how that the ASEAN monsoon is controlled by some dynamic effects. And so, and also, I'm somewhat interested in the global warming recently occurred in the global scale. Maybe you also know that in 2023 or 24, there is very high rising sea surface temperature in the global scale. So I'm also coming from one project as Apex, but it is presented tomorrow, so I will not talk about this today. And I talk about some heating process of the ASEAN monsoon, especially focusing on the Bay of Bengal region first. And my interest in this one, so the ASEAN monsoon is characterized by very wide range of regional temperature gradient reversal in the summer monsoon season. So this is because of the very strong heating in the higher latitudes, like 30 degree north, just south rim of Tibetan Plateau region, maybe due to that strong convection and its heating by the condensations. So this process is very important, and it is very northern part. So it indicates it very much strong Coriolis force is already very prevailing. So in this region, because of this, so that strong convection may make very specific circulation pattern in this region. And for evaluating that heating in this region, usually we use Q1 or Q2 perspectives. It's also very important, but I like to introduce some different method to do this type of heating evaluation. So in this region, as you know, so in the lower troposphere, here is very strong heated air mass, but not temperature, but it has lost very big moisture. And because of that, it has very big, high moisture static energy in the lower troposphere. And this air mass is transported to the upper troposphere to making the very big amount of highly heated air mass. It is the high dry static energy air mass. So this high moisture static energy air mass can transfer to the upper troposphere. It becomes high dry static energy air mass. This process is my interest. And so how these two things are in the lower troposphere, HMC, we see that high moisture static energy air mass, and the upper troposphere, high dry static energy air mass, is related with each other. This is my interest. And so in this region, this is the meridional section of the atmosphere by drawing by the potential temperature. We can see the upper troposphere, a high potential temperature air mass is accumulated and very much confined to the ASEAN monsoon region. It's making the very gigantic anticyclone circulation over this region. It is Tibetan high. And this high potential temperature air mass has to be supported by the injection of the high potential temperature air mass from the lower troposphere. And in the lower troposphere also, we can find a very big amount of high moisture static energy air mass. That is the equivalent potential temperature air mass, high equivalent potential temperature air mass in the lower troposphere. So we can define two different air mass. And just wait. So it is firstly in the lower troposphere, we can find the air mass with the equivalent potential temperature greater than some specific, for example, 355 kelvins. And in our upper troposphere, we can define that same using that potential temperature larger than 355 kelvins. So we can define these two different air mass, and we can compare this relationship. And we are very much interested in the lower tropospheric high moisture static energy air mass concentration and how it is generated. And this is for one example of the behavior of the high moisture static energy air mass in the lower troposphere. it indicates air mass, kilograms per square meters in each grid using the ERA5. And it is May, just the pre-monsoon to the monsoon transition phase. We can find very high amount of high moisture energy mass is concentrated in the landmass region in the India and the Tibetan, not Tibetan, Bengal plain. And so this is a one-day pattern. So there we can find very strong diurnal variation also can be found. So it indicates that for this accumulation, the surface impact is very large. And so we have to know about the process that at the land surface, how such a highly heated air mass is created. Anyway, so if we use this, and we can define one very interesting air mass diagnostic method. So in the upper troposphere, we can find this HDC, high dry static air mass it is a kind of a conservative value. So we can make it into one mass continuity equation like that over along this the layer. And if we diagnose that it's in conservative term, residual term, then we can find some extra source of such a highly heated air mass in this layer. And it can be divided into three parts. One is rainfall. It is, radiation. So radiation can cool down this highly accumulated air mass. And also, it is a convective input. So convection makes injection of the highly heated air mass. And this is residual. It may be very small. So we can divide into two different terms for this in conservative term. And for this, we can think about how much amount of air mass is injected by the convection and how much is reduced by the radiative cooling. And so this is the amount of high moisture static energy air mass and in these regions in global. And this is the volatile winter, volatile summer. So Asian monsoon, summer monsoon is like this. So we can see such a high moisture static energy air mass is so much found only in the northern hemisphere, in the Asian monsoon region, and also only in summer season. So it's a very interesting feature. And here is the globally average, not accumulated amount of globally integrated high moisture static energy air mass. It is air mass having the equivalent potential temperature larger than 360 Kelvin this time. And we can find only in the region from 10 degree north to 60 degree north, it indicates that the Asian monsoon region has a very big amount of accumulation. In other regions, no. So this is very important phenomena for explaining why such a strong monsoon developing in the Asian monsoon region. And it is the Asian monsoon onset phase, how such a HMC is increasing in which region. And we can find the first phase of the monsoon onset, we can find that the very highly accumulated high moisture static energy air mass can be found only in the Bay of Bengal region, at it flowing up to north to this Bengal plain, and it making the very strong convection in this region. It may be a very important source for that monsoon onset accumulation of the high dry static energy in the upper troposphere. And if we divide this, estimate that in conservative term of the upper tropospheric, the air mass continuation, we can find the extra source of the highly heated air mass in this region, and this region, this region. So we can divide such a heating in different regions, likewise, very interestingly. And also, this process can be evaluated by such a time series. And this is important. 3 times accumulation is occurred only over the this region. This region indicates the Bay of Bengal to Bengal Plain region. So the first accumulation phase of the Asian monsoon heated air mass is upper troposphere can be explained only by that the air mass injection in the lower troposphere from the lower troposphere in the Bay of Bengal to Bengal Plain region. So this is a very important result that in the monsoon onset phase, this region is very important anyway. And after that, different region can becoming very important, sometimes in the Tibetan Plateau region also. So such a change can be found. And also, this is the real observation and the calculation by the ERA5. And this is different sometimes, different regions. So in this region, in the northeastern part of India, it is highly underestimated by the ERA5. And the Bengal Plain region, so it is highly overestimated. So such a thing indicates that the process of the heating of the lower troposphere cannot be captured well by the ERA5. So we should clarify such a differences between the observation and the modeling. And how was that in the 2023 to 24 is like this. And this is accumulation of the upper tropospheric dry static energy air mass. It is very high in 2024 anyway. And the lower troposphere also is very high in 2024, maybe because of due to the heating of the sea surface temperatures in the global. And so 2024 is very special compared with other years. And this is the relations between the rainfall and such an accumulation of the high dry static energy air mass in the troposphere and the lower troposphere. And we can find these 3 peaks of the accumulation of high potential temperature air mass can be, it is correlated with the rainfall in this region in 3 peaks, this way. But if we compare the monsoon westerly, it's not clear. But we can find one pattern of the intra-season variability, and it is related with the accumulation of such a highly heated air mass. Such a relations can be found. And for internal variability, we can find that for the high dry static energy air mass can be almost completely controlled by high moisture static energy air mass. And for rainfall also, it has very good correlation between these 2 parameters. It indicates that the rainfall is very much related with such accumulation of the high potential temperature air mass in the lower troposphere and the upper troposphere. And this is the internal variability for each month. And we can find such a relationship can be found basically in July and August, and after some time like that. And in the pre-monsoon season, not so much. So such a relationship can be found. So that is my talk this time. Tomorrow we will have some other AsiaPlex program will be presented, but today like this. So please, if you have any questions, please give me. Thank you very much.
Yeah, Terasan. Yeah, nice talk.
Thank you.
I was just wondering, see, over this South Asian region, including India, you have data right from 1998 when we have GeoX Asian monsoon experiment, right? We have data of radiosonde every 4-hourly possibly. And then later on, we have very recently, year of maritime content, YMC, Asian monsoon. So huge data is already there available. Now, I am just wondering, is there any initiative anybody is planning using this data and using the latest machine learning and deep learning method? Can this underestimation and overestimation that you highlighted over, Northeast and Bay of Bengal, can it be quickly corrected rather than conducting again a huge experiment? It takes years of effort by you and many others, Jun Matsumo.
Yeah.
So can this latest technique be used? Because it is a very serious problem of underestimation, overestimation. So Is there any thought of in this direction?
So
Thank you.
it is not so much yet. So I will learn from you, and so we may use such much more
Not from
data
me.
set for this. That's it. Okay, so thank you very much for a good suggestion for me. Thank you. Well, so
So in West African monsoon region, HMCA is not July. Mostly it is high value in South Asia and East Asia. We don't see over West Africa. Correct?
Yes, not so much.
The next slide, can you go to the pre-monsoon? But here I am seeing in the pre-monsoon month, West Africa is having So I was thinking, why is it?
Thank you very much. It is noticed just now about that. So it may be very interested in this region for this specific phase of monsoon onset. So I think it can be very important for the monsoon onset in this region. Yes.
Okay. Thank you.
Okay, thank you very much. So now we'll move to our next presentation. Dr. Sarah.
Okay, so while they set up the presentation, I'm really happy to be here today on behalf of Ajaya, who is actually the lead author for this presentation, as well as my other co-authors. And I'll talk about the Asian summer monsoon variability during comparing 2022 and 2023. And the title is Beyond the Canonical Teleconnection Patterns. So this work actually started end of 2023. So during discussions in the Asian Australian Monsoons Working Group, which I'm also a member, we were talking and like sharing our different experiences between these two summer monsoon periods. And just to highlight in this group, in this working group, as Surya nicely introduced before, we combine not just researchers, but people that, like myself, that are more in touch with the operational side and stakeholders as well. And also from all different parts of the Asian monsoon region. So we all actually had different experiences, and it was a really nice, unique challenge to try to come together and try to say, like, can we say anything about comparing these two years as a whole for the monsoon region. So this work was published in the GWEX newsletter last year. So I'll just run through it pretty quickly now. So yeah, don't need to do the slide. Suri did a great job introducing the monsoon panel. Just to highlight as well. So this work was done by people from the Asian Australian Monsoons Working Group, as well as the panel as well, and involving both operations and researchers. Actually, and our previous speaker nicely introduced the Asian summer monsoon as well, but just to like make sure we're all on the same page here. So this is just showing the rainfall in June, July, August in the climatology period of 1991 to 2020, and showing you the rainfall amount in this time. And the black box is sort of outlining very roughly what we're going to call like the Asian monsoon area. It's a square box, it's not perfect. And you can see that indeed there's a lot of rainfall over parts of South Asia, East Asia, and parts of Southeast Asia as well. Also on top of this, we have the 850 hectopascal wind fields as well, showing, as you would expect, the westerlies, a little bit more southwesterly over Southeast Asia, and actually south of the equator, it's southeasterlies. Now, I know this is just JJA, so this is not the entire monsoon region, but as we also heard in the previous talk, the onset for many parts is much earlier than this, but this was sort of like the period that most of the region experiencing the summer monsoon, so we just try to simplify it down there. We talked about, in our title, it's beyond the canonical teleconnection patterns. So just to quickly refresh ourselves, this is from the IRI. It's a very simple global overview of the impacts during La Nina at the top and El Nino down the bottom of rainfall for the various areas. Of course, those working in the Asian monsoon area know there's a lot more information than just on these images here, but it's a nice summary. And you can see, generally speaking, for our region, we see green, which means more rainfall during La Nina in June to August. And then there's a few other little yellow bits sort of around where we see drier conditions, but this is actually outside of the June, July, August period. And then El Nino, it's not the exact opposite, but generally it is experiencing drier conditions. Okay, so that's, if you just had the ENSO outlook, this is what you perhaps would think if you had an El Nino or La Nina in a particular year. So now let's dive into those two monsoon seasons. So let's take ourselves back to 2022. So during this time, we were sort of just over midway through the triple dip La Nina. We had La Nina conditions all through this year. So if we're thinking about those like typical patterns, you expect wetter conditions. And we also had a negative Indian Ocean dipole that developed around the middle of 2022. Now, this here is showing the anomalies for JJA in 2022, and you do see, indeed, a lot of the region had above average rainfall in parts of Western India, Sri Lanka, and the maritime continent. We now see easterly anomalies as well, which means weaker monsoon westerlies over the Bay of Bengal into mainland Southeast Asia, and associated a little bit suppressed convection over there as well. Now, not captured in this figure, but just also to share, in this region, we had the onset for the monsoon, which happened before this time, was near average or earlier than average, okay? So this was a summary of 2022. Now let's look at 2023. So in 2023, finally, we were ended of those La Nina conditions, and we were all focusing on El Nino. So it actually, depending on how you define an El Nino, which is one of the challenges, it wasn't really until September that it became fully established. So this was after the period. Actually, we heard previously the talk about warm SSTs, and indeed, SSTs were just warm in the tropics in general for 2023. We also had a positive Indian Ocean dipole that developed in August towards the end of our period. And also during this time, there was a really prolonged, or prior to this time, there was a prolonged global heat wave as well. Also, weaker MJO and BCSO activity. So now let's look at our quick anomaly plot here. So if we look at the rainfall first, you can see that there were enhanced rainfall in the Western Pacific and East Asia, and less rainfall in sort of parts of India, including northeast of India, but really actually fewer notable anomalies in wind and rain compared to what we saw in 2022. And in terms of onset, there were some slight delays or around average as well. So if we were thinking, hey, El Nino versus La Nina, which is maybe when we were starting our conversation in the end of 2023, we were kind of, some people were, or some of us were a bit surprised at the sort of like looking at sort of a kind of meh picture, what we saw in 2023 compared to what we saw in 2022. But also just to highlight, one of the important things that were coming out from our discussions is often we do look at these seasonal averages, especially like for myself, it looks at more of the climate, timescale sort of things. But really, if you were sort of asking people from the operation side, they were also really focusing and remembering on these extreme events. And one of these extreme events, of course, was the Pakistan floods in 2022, where almost 14% of the population was affected, including 8 million people displaced from their homes. This was a major event, and it was actually kind of predicted as well. But we'll come on to that as well. So in a lot of minds from the operational side, 2022, we were thinking, flooding and other floods as well. If we think about extreme events from 2023, we were actually not so much thinking about floods. A lot of this was on temperature and heat waves. So this is actually looking at Vietnam. So we'll look at somewhere else now. And this is looking at, for their AWS stations, anything in red means that the AWS was recording temperatures for the month of May above its 99th percentile. So prior to this onset of the summer monsoon, there was actually a prolonged heat wave in April, May from Bangladesh and East India all the way to southern China and mainland Southeast Asia, including Vietnam as well. And actually within that monsoon period as well, there was actually very severe heat waves in northern China, and also Japan had its hottest summer on record. So we've talked about the general conditions in the monsoons. We talked about some extreme events, but actually in this group, we were like, okay, we were throwing out extreme events we remembered from these two different seasons, but let's like, okay, let's try to come together and put tables together for these 2 years to more objectively compare the impacts from the extreme cases. And what we came up with was this table here, and I don't have time to go through it all, but there were numerous hazards in both years in June, July, and August. There were actually floods in both years. I know, well, for many of us, we're remembering the floods in Pakistan, but there were floods also in 2023 in China, in India as well. And actually, there were heat waves in both years as well, even though this was sticking in the mind of 2023. That's something that was not included. I mean, there's other hazards as well. We have drought, we have landslides, we have tropical cyclones as well. And in 2023, something that was a bit notable was there was the lowest number of typhoon landfalls in the North Pacific since 1981. So a challenge that we sort of came up when we were putting up this table was actually, it's very difficult to, if we look at extreme events, especially if we're trying to look over the whole Asian monsoon or summer monsoon area, it's really hard to actually pick up all the covered events. We know the ones that maybe that are in the countries we live in or people that we're working with, but in terms of reporting, we don't know all of them. Also, in the study, it was raised when I talked about the heat waves as well. When we were focusing on JJA, maybe it sort of is masking some of the really severe things as well. So, for example, in Sri Lanka, it was quite dry for June, July, August in 2023, but then they got really heavy rainfall and flooding in September. So when they looked at their monsoon season overall, maybe it wasn't particularly anomalous, but within that season, very dry, then very wet, obviously had effect on the people living in there. I will briefly talk about the forecasts now. So this is actually now showing you, so these are the two plots that I showed earlier on the left-hand side, and then on the right is the from the IWM8 Lead Center, the multimodal ensemble forecast. And this is, they're not exactly apples and apples because the one on the right-hand side is the Trussell probability forecast and the other one is the anomalies. But you can see actually what Surya was saying before, very cleanly illustrated here, that if you remember what those typical patterns from ENSO are like, this is what the models were showing. Wet for parts of the maritime continent and sort of parts of India for La Nina, and then the opposite for El Nino. And it kind of matches for 2022, but not so much for 2023. So this could be due to the later development than El Nino than predicted, or also just sort of overestimating that impact of the El Nino in the models. Okay, so this is my final slide. So we had a lot of discussion, and it really is a complex issue. So the two challenges that we wanted to highlight at the end of this article was first, the challenges of understanding these monsoons and predicting and working and living in a world that is changing. Our climate is changing. As many of us are aware, 2024 was the warmest year on record globally. And this increases the chance of some extremes, notably heat waves, but other extremes as well. This can also influence the conventional teleconnection patterns for drivers such as ENSO, and also can affect the way we monitor them as well. Because, for example, warm SSTs everywhere is going to give you a warm 3.4 value. That's what people often use to monitor El Nino or La Nina. But if the whole tropics are warm, that doesn't really look like El Nino, right? That's just warm tropics, but you would have a positive value for that. The other challenge, as I'm sure everyone is aware here as well, is that predicting patterns within a season is quite challenging as well. And this is, if we want to talk about research to operations and operational use of this information, is that how do we convey this to the users and the stakeholders to not get caught up with, okay, the season looks like it's increased chance to be drier, but this doesn't mean that we can't have positive extremes in that and vice versa as well. Okay, so more information is available in the article that is listed here. And just to share, this was not a really deep science article. Rather, our goal was to further incentivize the wider community to look into this more. So it's great that everybody's here because really to address these challenges, really it requires coordinated diagnostic and modeling activities from among researchers, but also through the forecasting community and using international resources as well. So thank you very much.
Thank you very much for such an excellent presentation. So now floor is open for questions. And I especially invite the youngsters. Here they have any queries and any questions. Very interesting talk.
Also, feel free to approach me after if you have questions or any of the other authors that are not all listed here, but yes, from the working group as well. Hopefully you can take this in and just use it for a little bit of inspiration. Oh, yes, thank you.
Hello, ma'am. Nice talk. Last challenging one slide you were saying that coordinated diagnostics. What do you mean? Is it like it's a kind of a common metrics to evaluate the models, or do you have any process-oriented diagnostics for common platform to make a kind of a metrics for evaluating the models? Is that what you meant by the coordinated diagnostics for different modeling groups?
Yeah, I think it's both between modeling groups, but also have a very nicely ties into the question that's here that I quickly read, which is about index you use for monsoons. So it's about between the modeling groups to be using similar diagnostics, but also talking about the same thing. So for the onset of the monsoon, actually that statement just came from everybody sharing what they use for onset of monsoon. So it's not necessarily the same thing. Yeah. So actually I'll have another talk on Friday that will talk about what we're trying to do in Southeast Asia on this part as well. Because it is really important, because if you're using something else to onset of the monsoon, maybe you're picking at different things. Yeah, so I try to address that. Yeah. Yes. Yeah, I think. Yeah, so we did actually say earlier onset for 2022. So that is in line with the person's, thanks for the question, for their comment here. So this is what we did see in 2022 was an earlier onset, but it does, at least in Southeast Asia, depend on the region that you're talking about as well. But it does, I'm not sure if this is quite what the person's getting at, but it is how you define your rainfall or how you define your onset as well. Because if your onset is defined by rainfall and you have a TC bringing rainfall, is that really the onset of the monsoon, or is it something else? So I think, yeah, thanks for sharing that question. Hopefully we'll be able to have a look at the link, even if we're attending in person and not able to access it online. Thanks.
Questions or queries?
Thanks, that was a really nice talk. The question I keep coming back to with any of the sort of seasonal forecastings, and this monsoons included, is the fact that the baseline is shifting so much, and then you can try to get anomalies and to try and what the signal might be. To what extent do you think we actually need to change how we do this to actually understand the signals that the models are giving us if you're going to express it as an anomaly?
Yeah, I think that's a really, really good question. And I think it's so, especially for temperature, it's a really important question. So as an operational center, you may want to keep the old baseline, because then you have the climate change signal go, yeah, it's going to be warmer. The high chance it's going to be warmer. We know that anyway with the long-term warming trend. So I think this really is a challenge, but the issue when you start getting smaller climatologies is that all of a sudden you're going to be dominated by, say, the last couple of years you had, like, say we had that triple La Nina, right? So you're going to have 3 years where La Nina was the base state. And so I think it's really from a operations point of view, it depends on what the users are using it for. So quite often these simple, like, seasonal outlooks can be thought of as a way to get people's attention. Like, here's something easy. We can do it around the world. We know it has skill, but it's to get people's attention, and then it's to develop more tailored products with them. So then you're doing something that's useful for the user as well. But I think it is also really important for us creating these outlooks to understand where the skill is coming from, because if it is just the long-term trend, then we don't necessarily need the models, right? We need the models to get better, to bring up more information. So yeah, it's a really good point. Thank you very much.
Yeah, very wonderful talk. Just continuing on the last question, previous question. So 2022, you are getting that wind anomaly and rainfall anomaly. We have forecast.
Yeah.
2010 also had a very similar type of situation. If you remember, it was also a La Nina flooding. The entire circulation pattern had shifted west. So I was thinking whether you have done any forecasting for the 2010 event.
Yeah, we definitely need to look at more cases. And this is something in the working group that we're talking about. We should continue doing this every year. We haven't looked at 2010, but in our group, because all of us joined this group in 2022 only. But I think it's really useful to also look at past cases. Again, as you mentioned, there was that La Nina that was occurring. So it would be interesting to compare with that, because we all know two La Ninas or two El Ninos are the same. So it is also important to compare with the past events as well. Thanks.
Thank you very much. Next talk is by Dr. Sorry.
All right, hello everyone. Just 1 second, let me check my mic. Okay, so today I'm going to talk about the role of mid-latitude dry air during the withdrawal of the Indian summer monsoon. This is something that I've done in collaboration with my colleagues at Reading and the Met Office, especially Professor Andy Turner at Reading, Dr. Ambrosio Volonti at Reading as well, and Dr. Aarti Menon, who is from the Met Office, and she's going to talk this afternoon about diurnal cycle and rainfall modes over different parts of India in the Met UM. I don't need to tell you how important the Indian summer monsoon is, but if I have to tell you using a single picture, this is what I would do. This is a picture that's taken somewhere outside Hyderabad. And on the left, you see what happens before the monsoon arrives. It's totally dry. The same photograph taken when the monsoon is there, you can see it's lush green. So to put in one word, the monsoon is just the lifeline of India. It provides water. It's very important for everyone. We all know how the monsoon onset progresses over India, but just to quickly tell what happens. So this picture shows the onset progression of the monsoon in the top row. This is showing rainfall in terms of millimeters per day for different pentards. So you have got pentard centered on the 15th of May, 1st of June, 15th of June, and 15th of July. This dashed red line is the climatological onset isochrone from the IMD. So we can quite clearly see how the monsoon is progressing. Like on the 15th of May, the monsoon reaches Andaman and Nicobar Islands, and then it starts raining over different parts of India, and the onset was moving toward the northwest. Fine. What happens after a couple of months? The monsoon starts withdrawing. So mid-September is when it starts withdrawing, and you can see rainfall over India is decreasing, and the withdrawal isochrone is moving toward the north, toward the southeast. The main question that basically comes is, what is really driving the direction of the withdrawal of the monsoon and the onset of the monsoon? So for that, there was a paper in 2016 by Doug Parker et al., and that was published in QJ. So this paper tries to address why the monsoon is basically moving in a direction that's toward the northwest. And what happens is that before the monsoon onset is there during the summer, there is a wedge of dry air over India. So you can see India is here. You have got this monsoon winds developing in low levels that's shown in blue. And then you have a lot of dry air that comes from the mid-latitudes, and that's there at mid-levels. So that's there. And when you look at a cross-section, so something like this, so you have got northwest, you have got a lot of dry air over there. At the same time, there is no deep convection happening, but toward the southeast, that's over here, that's where you have got some deep convection going on. So this dry air is preventing the formation of deep convection over most of India in that. And that's what this paper, Parker et al., showed, that the environment favorable for deep convection occurs first over the southeast. What that does basically is that the dry air is then going to retreat toward the northwest. So there is detrainment that's happening from shallow congestus and deep cumulus cloud over here. And also what happens is that the monsoon wind strengthens. So there's a lot of moisture that comes into India. And then that can be understood from this particular picture. So you've got a post-onset scenario, that's 15th of July. And now the monsoon winds have strengthened, this dry air has retreated. And then when you look at the same cross-section, you can see that there is deep convection happening over different parts of India. So this is what we call as a Parker mechanism or a Parker hypothesis. And then that leads to some questions, which is basically, when does the climatological mid-level dry air come back? And does it play any prominent role in the withdrawal of the monsoon? Do the tropical and mid-latitude air masses behave in a reverse Parker mechanism or reverse Parker manner during the withdrawal? Or to put in other words, whatever we see during the onset, do we see the reverse of that during the withdrawal? And that's why we try to address this question in this work. And we are going to follow the research framework of Parker et al. To understand a couple of things, but mostly to uncover dynamic and thermodynamic aspects associated with the progression of the monsoon withdrawal. So I've got a figure here from the paper that was published a couple of months before. And what I would like you to do is that just keep in mind this particular transect that runs from Afghanistan, goes all the way to the Bay of Bengal, because I'm going to use that after a couple of slides to show us a couple of things. So what we did, we took, of course, RFI reanalysis and observations from the IMD. And this particular picture is showing different levels. So that's 600 hectopascal, 750, 850, 925. Then I've got relative humidity that's in shading. And this is a pentad main scenario. Again, I've got the withdrawal isochrone, which is in this dashed red. And what you can see here, which is quite clear, is that when you look at mid-levels, that's the 600 hectopascal, 15th of September, you can see the dry air is over there. But when you look at low levels, for instance, 925, it's quite moist. And we can see that the monsoon winds are quite active. Even at 850 hectopascal, you can see this classic C-shaped curve monsoon flow going on. But then subsequently, as we get to this 30th of September and into 15th of October, at mid-level, this dry air that's shown in this brown shading is just getting into India. When you look at what's happening at low levels, the impact is there, but it's not that robust when you compare it to mid-levels. For instance, if you compare this 850 hectopascal, this dry air is starting to appear, which is basically around this part. And the monsoon circulation is also weakening as we get into mid-September and the end of mid-October and end of September. So this climatological mid-level dry air is actually coming from the northwest, and it's re-emerging around mid-September. Over subsequent days, it's strengthening and getting into India. To confirm this, what we did is that we did a bit of a back trajectory analysis. So this picture is not that complicated. It looks like kind of complicated, but I'll explain what I've done. So we took two different levels, 600 hectopascal, 850 hectopascal. You might be able to see there is a very small box here that's over north central India. What we did, we just released back trajectories from this box, allowed these back trajectories to go back for 6 days. And then we just wanted to see how the air mass is behaving for different dates. So for instance, this particular picture, the back trajectories have been released on the 15th of September. They are going back for 6 days. Shading here is showing a kernel density estimate of different trajectory points. And some example trajectories are shown in blue. And the same thing could be done at low levels. That's in red. That's at 850 hectopascal. The key thing that comes out here is that when you look at mid-levels, there is a clear tendency that the flow is becoming more and more northwesterly as we approach into mid-October. And the same thing is happening at 850 hectopascal. Like on the 15th of September, you are getting this flow from the Arabian Sea. There is some flow from the northwest as well. But then subsequently, there is this tendency that even that flow is getting into this northwesterly pattern. And of course, that is descending in nature. I'm not showing a picture here because what we did that we also analyzed how the air property is behaving along the trajectory. So like how the specific humidity is changing, how the pressure is changing, but I'm not going to show that in the interest of time. So remember that figure where I showed a cross section. So what I've now done is that I've taken that cross section and I'm going to look at a couple of different fields. They tell you the same story. So for instance, this top panel is going to show you mixing ratio. This is related to humidity. That's theta E. And again, I've got 15th September, 30th of September, 15th of October. So there are two more things here. So I've got a dotted black line, which is showing the freezing level. And then there's the lifted condensation level, which is shown like this. So for simplicity, we could just focus on the result of theta E. So 15th of September, we can see that this part, which is over Afghanistan, because that's that end of the transect, there is this dry air, which is quite clearly seen over here. Compared to that, the air over India, like over the Bay of Bengal and India, you can see this red contour. So there's a high theta E air over there. But subsequently, you can see how this dark blue patch is getting into India. And it's also changing a couple of things. For example, if you focus on the lifted condensation level, that's going up. Not much is happening to the freezing level. So this tells us that the expanding and descending mid-level dry air is getting into India. It's affecting the tropospheric stability. It's making things more and more stable. And then that basically drives the monsoon withdrawal toward the southeast. To summarize this, I have created this cartoon, which is showing the scenario on the 15th of September and 15th of October. So that's when the monsoon withdrawal is beginning. So you can see that there is this mid-level dry air. It's raining a bit over that part of Northwest India. Elsewhere, it's raining because the monsoon is still active. But by 15th of October, the dry air intrudes, and there's not that much of a convective activity over there. So the monsoon has basically withdrawn. It leads to a couple of questions that we haven't addressed, and that could be something that you guys could pick up in future research. So the first thing, of course, is how steady is the monsoon withdrawal process? Because we know that every year there is this tendency that the withdrawal gets stalled for a couple of days and then it accelerates. So that's something that we don't know. What are the large-scale conditions that control the intra-annual variability of the withdrawal? That's also not that well known. And how well do NWP models simulate this interaction between mid-level dry air and moist convection? So that's another thing that we don't know. If you're interested to learn more about our work, I'll just come back to that. So there's this paper over here, was published in QJ. And I've got a couple of posters to showcase. So what I'll do is I'll just quickly tell you what is going to come up next. So there's a poster showcase going on. So I have a poster this afternoon at 4:30 to talk about the role of dry intrusions in breaks of the monsoon. And there is something that's going to come up on Wednesday afternoon, which is how does the soil moisture impact the inland penetration of monsoon low pressure systems? I'll stop there. Thank you.
Thank you very much. So due to shortage of time, we have to have only one question if it is very important, otherwise you can discuss during the lunch time, because we have to finish everything by another 40 minutes or so. So thank you very much. I think there is no question.
Yeah, we have, I think, a quick question there.
Action.
Hi.
Then presentation, just one quick question. So along the transect, once you are, the monsoon is in withdrawal phase, so the dry winds, actually they go until the Bay of Bengal where your transects are lying. And then if yes, then how do they interact with the northeast monsoon onset? I mean, after some time or so.
Yeah, so we haven't looked at how they interact with the northeast monsoon, because the northeast monsoon onset would typically happen around the mid of October. Yes. And in this picture, you can see that over this southeast India, even at mid levels, it's quite moist. And the same thing is happening at low levels as well. So there's going to be some interaction over things like eastern India, but not that much over southern India.
Thank you.
Thank you.
Thank you very much.
Yeah. Hello.
Next talk is.
Excuse me. I have one question here.
We can discuss that later on in the interest of time. Thank you.
Yeah, we have to finish by 1:15 and because of next session. Start on time.
Yeah.
So please come time to your time as much as possible.
Yeah. Good afternoon or good morning, whatever. My name is Bodo Ahrens from Germany, Goethe University. I'm the speaker. The work was done by Prashant Singh. within a larger project called TP Change, which is dealing or investigating the transport through the tropopause, mainly in the exotropics, but also in the tropics. This is why I'm here. The motivation for this talk is, or for our work in this project is, we are concerned with climate modeling, and of course we need to know how much water vapor there is in the lower stratosphere, in the upper troposphere, because this is very important for radiation balance of our models, of course. And there's this old nice paper or figure from Skerlak et al., which shows that there is a Tibetan pipe. No? Let me check here. In spring and also in summer, so pre-monsoon, monsoon periods, where the transport from the PBL up to the UTLS is quite intense. So we want to study the processes involved, but we have to keep in mind these analyses are done with ERA interim, based on ERA interim, which has a parameterized convection scheme. So how realistic is this? This is another question. Of course, this Tibetan pipe is linked to the Asian summer monsoon anticyclone, and we know from observations, here it's data from the microwave limb sounder, that there is an accumulation of water vapor close to the tropopause. Now, the Asian summer monsoon is somewhere here, so obviously in the TTLL we have infusion of water vapor by deep convection. What is our tool to study this? We participated in the convection permitting third pole, WCRP, Cortex FPS, and our model domain we used within this study is this bluish one here, which covers the Tibetan Plateau and the Himalaya ranges and so on. And the grid spacing we used is 3.3 kilometers. So we switched off the deep convection parameterization. We kept the shallow convection. We did a larger domain simulation with 12-kilometer grid spacing too, just for reference. A little bit of evaluation. Here we see a mesoscale convective system in terms of precipitation, as observed. Here, IMERGE and CMORPH, as seen by ERA 5, so not so much seen. ERA 5 underestimates this precipitation event. Also, the IMDA analysis underestimates this event a little bit. And below, you see the simulations we did with convection permitting simulations. So the intensity looks better, but also with 12 kilometers with the convection parameterized simulations, it looks quite nicely. What we also did during this event and others, we followed parcels. We initiated parcels, forward tracking them from the PBL up to the at least 300 hectopascal level. And we see on the left the parcel tracks as seen by ERA 5, and here as seen by our kilometer scale simulation. You see much more dots here, or it looks like much more dots, because we have a horizontal transport. Here it's going vertically, directly vertical upwards within this event, and here the parcels follow more horizontal direction. In both cases, we don't see an overshoot in the simulations. So a few into the TTL, but no through the tropopause. Another evaluation example, just quickly, ERA 5 doesn't see this convective event here along this path. Our simulations do see some convection over here, but more important even is that ERA 5 overestimates water vapor concentration in the upper troposphere. And this is linked to this figure. This is the event mean transport as simulated by blue ERA 5 and by two convection parameterized simulations with our model. And here the transport simulated by our kilometer scale simulations. So we see that we have a larger transport in the lower troposphere by the kilometer scale compared to the convection parameterized simulations, and an overestimation of transport in era 5 in the upper troposphere. A few more events. Yeah, just to summarize, era 5 always overestimates water vapor in the upper troposphere. And ICAN does, compared to the observations we used, a somewhat better job. But it's important to mention our simulations were directly nested into era 5. So what we inherit from the lateral boundaries as overestimation goes into the domain. And here we simulated 10 years with our simulations compared with era 5 and 2 satellite-based data sets. And we see era 5 substantially overestimates during the monsoon period the water vapor content. ICAN kilometer scale goes closer to the observations during these 10 years. So what is going on? A little bit deeper into the details, we focused on lightning events, lightning as seen as on the ISS, with high LPI simulations in our kilometer scale simulations, and by Cape times press as an indicator in era 5, plus additional events over the Tibetan Plateau. We initiated for each lightning event 100 parcels close to the surface in different layers. And what we see is, here on the left-hand side, all the parcels which reach actually the 300 hectopascal level. In the center, the time these parcels need, the time in hours these parcels need. And you see era 5 is more yellowish than ICAN. So era 5 parcels need up to 10 hours. In ICAN, it goes directly up. This directly up can also be seen here. The parcels reach their highest point within a 12-hour windows close to the initiation points. The era 5 parcels move to the north. So there's a strong lateral component. This is also seen here on the left, the parcels in era 5, and here the parcels in ICAN. So less parcels, of course, but also a smaller lateral component in ICAN than in era 5. ICAN means here the kilometer scale simulation, so the convection permitting simulation. So our conclusion is, not really a conclusion, but our hypothesis is right now that we have different processes in ERA and ICAN. Obviously, we have parameterized and resolved convection, but these might be important for the transport of water vapor up to the TL. We have a direct transport in the kilometer scale, and in era 5, it follows more the upslope flow along the Himalayas, which takes longer time and a strong horizontal component. And this is not what we really have in the real atmosphere. So this is a proof that Frankfurt is close to Italy. But my conclusion is lost somehow. So on top of this nice figure, there's a conclusion which says that we have different processes in era 5 and in the kilometer scale simulations. We should be very careful in interpreting era 5 with respect to water vapor concentration in the upper troposphere, lower stratosphere. And we have to do more with our kilometer scale simulations.
Thank you very much.
Thank you.
So what do you tell observations? What do you mean by observations? Era 5 versus observations and your simulation. And what type of observations you have taken? Station level?
Sorry?
Observations.
Observations. Yeah, satellite-based observations. Okay. The microwave limb sounder data and the AIRS data. So both observations, satellite-based.
Thank you. Thank you.
Bodo, thanks for the presentation. Nice work. How important is your shallow convection over that particular region? You mentioned that you switched on and switched off deep convection. So I was just wondering, so how important is that, and did you do any sensitivity tests? Because we are also planning for 2.5 kilometers, so we want to learn from you. We also use ICAN.
For these events, we evaluated it's not important. We did both. We switched it on, we switched it off. Also, we switched off a deep convection for the 12-kilometer simulation, which was a very interesting experiment because it worked very well, which was not expected. So no, the shallow convection is not so important for this upper troposphere.
Okay, we can have more discussion during lunch time. Thank you very much. Very much. We'll go shift to next one. I'm sorry for going to hurry to finish in time.
Yeah, I think it's me online. Okay, so I'm hoping that everybody can see that and you can hear me okay.
Yeah, not yet.
Okay.
Sana Mohammed, next.
Yes, hello. Can you see my presentation online?
Yeah, now it is okay. Please go ahead.
Okay, thank you very much. Okay, hello everybody. So yes, my name is Sana Mahmood, and today I want to talk about marine heat waves and some of the work that we've been doing in the regional coupled group at the Met Office. So first, I'd just like to acknowledge all my co-authors. This work is very much a contribution of many different people, from running the simulations to analysing the results, and of course, developing the complex models that we're using. So just to give a very brief outline of what I'm going to talk about, so kind of split into three sort of bits. So first, we began really by an interest in marine heat waves over the UK, and we used the regional environmental prediction system to look into this and understand marine heat waves better and the impact on their local weather. And then following on from that, we started to look at the influence of marine heat waves on storms in the UK. And then finally, we applied some of the methodology that we developed to look at impact of marine heat waves on tropical cyclones. And this last bit is very much new work, so it's not, it's by no means complete. So just to introduce what regional environmental prediction system is, so it's a very complex, high-resolution regional coupled system, and it consists of many different model components that we can run standalone or coupled together. So we've got the atmosphere model, which is currently the unified model, that's coupled to a land surface Joules model. And so we can run this alone, or we can couple it to an ocean model and a wave model, and also recently a biogeochemistry model as well over the UK. And then by doing that, we exchange many different variables as demonstrated by those arrows. So it's high resolution, as I said. So if we run over the UK, that's at 1.5 kilometers. But it's also a relocatable system too. So we do run it over other parts of the world, including India, which I'll show you at the end of this talk. So this work all began in June 2023, when the UK broke its mean temperature record for the month by 0.9 degrees. And that's quite big, because usually we only break these records by small amounts, 0.1 or 0.2. And then also at the time, there was a marine heat wave as well over the Northwest Shelf. So that's the kind of region northwest of the UK. And so we started asking questions like, how much is the marine heat wave contributing to that warm temperature on land? And to try to sort of answer that, we ran 2 month-long simulations. So these were atmosphere-only simulations in which we provided different SSTs. And maybe this is better explained by the time series that we've got here, the big plot. So this is a time series of sea surface temperature over the Northwest Shelf region. So this is over a year. The black line is the climatology, and the orange-yellow line is the SSTs for 2023. So you can see that in June, you've got this big bump, and that's the marine heat wave, so it's higher SSTs than usual. And so the month-long simulations that we ran one with the black SST, so the climatology, and then one with the orange. So essentially we've got a marine heat wave run and a no marine heat wave run. And the difference here is shown on the plot above. So you can see those warmer SSTs all the way around the UK. And what we discovered was that the marine heat wave contributed 0.6 degrees to that 0.9 heating over land. So that's quite a significant contribution. So this work is really nicely described in Segel and Bertou's paper from 2024. So it really explains this in more detail and explores the mechanisms by which this marine heat wave is impacting these land temperatures. And then we've also gone on to look at other marine heat waves as well. So the following year, 2024, is the red line on the plot. And again, we had a marine heat wave in May, and then we could run similar simulations and see how much that marine heat wave contributed to the local weather. So following on from that, we started to look at the impact of marine heat waves on extratropical cyclones, and in particular, Storm Babette. So Storm Babette was the most impactful extratropical cyclone for the UK in 2023. We had extensive rainfall that generated floods in the north of the UK, and it also generated intense waves of greater than 8 meters, significant wave height, and surge of 18 centimeters in the North Sea. We were also, a red weather warning was issued as well in the UK, which is quite rare. And Storm Babette came after 47 days of marine heat wave over the Northwest Shelf. So again, I've just got another time series on the left of the sea surface temperature, just like I showed a couple of slides ago. So again, the black line is the climatology, the SST, and then the orange line is again the SST for 2023. And so you can see there's this marine heat wave, sort of starting in September, and then the storm is in between these two dotted lines, and that sort of brought an end to the marine heat wave. Because of the nature of this storm, this study really was trying to focus on the impact of this autumn marine heat wave on the multi-hazard characteristics of the storm. So in this study, we really make use of the whole coupled system. So we have a regional atmosphere, the land, rivers, and wave and ocean models all coupled together. And the experimental setup consisted of rerunning 5 days of forecast with MOGREP's UK 18-member ensemble coupled to wave and ocean models. So it's a little bit different to the marine heat wave work, which was just an atmosphere-only model. And so our ocean model in this case was either initialized from what you see in the orange line on the left. So it would be on the 17th. So just prior to the storm, 2 days before the storm. And then the other simulation that we ran, we initialized with the blue line, which is 3 years and 2 days before the storm. So it's kind of the 2020 SSTs. And we chose this because this is fairly close to the black climatology. So the middle plot here shows you the SST anomaly from climatology from Ostia. So just, from observations, I guess, well, not from observations, sorry, this is just what the marine heat wave was looking compared to, Ostia SST. And then the right-hand plot is the SST difference between these orange and blue simulations. And so you can see that the marine heat wave, what we're using in this simulation, is slightly underestimated coupled to the observed anomaly, and especially over the North Sea. But we can maybe consider this coupled experiment as a lower estimate of the marine heat wave signal on the storm. So as I said, the idea of this study is to bring focus on the multi-hazard components. So we're really analysing changes here in the river flow, storm surge, and significant wave height and precipitation. So 2 rivers burst their banks during the storm. So that was the River Tay and the River South Esk. And you can see that in the marine heat wave runs, so these are the orange ones compared to the no marine heat wave, and the blue on the left-hand side, we had increased river flow in these marine heat wave coupled experiments by 12% compared to no marine heat wave. We also saw increased wind speed of 1% in the marine heat wave runs, and that sort of led to increased significant wave height by 3%, so that's about 15 centimetres. And finally, storm surge was also boosted by 20% in the marine heat wave runs compared to no marine heat wave. And also precipitation as well. So we saw precipitation in the east coast of Scotland in the marine heat wave runs, and it's diminished in the no marine heat wave runs as well. And of course, in observations, there was increased precipitation over East Scotland. And so finally, really want to try to apply some of this sort of experimental setup that we've developed to tropical cyclones. So just to reiterate, this is just work in progress. And I probably don't need to go into too much detail, but tropical cyclone Fanny was the test case that we decided to use. So this was a long-lived storm that formed on the 26th of April. I think it made landfall on the 3rd of May 2019 and then dissipated on the 5th of May, 9 days after it first formed. So in this case, we initialized on the 26th when the storm formed, and we ran a 9-day forecast. And in this setup, we just ran atmosphere only with the daily updated SST, so a run which has marine heat waves, so it sees that warm SST, and then another simulation where there is no marine heat wave, so we just use the climatological SST. We have in the past, so Juan Castillo in my team wrote a paper in 2022 where he does look at this tropical cyclone and another one and runs experiments with various flavors of coupling. So if you're interested, then the link to that paper is here. But in what I'm going to show you are just atmosphere only simulations. This is just showing you the difference in the sea surface temperature in the Bay of Bengal between the marine heat wave and no marine heat wave run. So you can see that you've got, yes, warmer SSTs in this marine heat wave run, especially around the coast. And then I've just put the track here on the right. So we've got observations in black, and then the 2 cyclone tracks for the marine heat wave and no marine heat wave run. And I think I'd say that they're fairly indistinguishable. They're quite close together. I've also compared quickly with some observations that we do have in the Bay of Bengal. So the top left-hand corner shows 3 observation points. So unfortunately, they're not in the cyclone path, but these are the only ones I could get hold of. And it's just to show really that the marine heat wave runs are doing a good job. They're probably closer to the observation in all 3 locations, and that there is like about a 1 degree difference at that point between the marine heat wave and no marine heat wave run. And then here I've again just got the track on the left, and then comparing the PMSL for the two runs as well, and you can see that there is a delta between the 2. It's about 25 hectopascal different, and we know already that our atmosphere only runs over predict the intensity of cyclones, and we can see that here. And we do reduce this when we use a coupled model, but I am just using an atmosphere only. And actually, in this case, I think, yeah, maybe I'd say that the no marine heat wave run is perhaps doing a better job. They're getting that PMS out. And then finally, this just started to look at air temperature differences as well. So this is kind of 7 days into the forecast, and you can see this big sort of dipole. And I don't know, I guess this may be due to the difference in the in the speed of the cyclone in the two runs, and one is maybe reaching landfall faster. There's also changes simultaneously in the precipitation, so maybe the extent of the precipitation is more over land here in the middle plot for the marine heatwave run compared to the no marine heatwave. But yeah, we'll be trying to explore these runs a little bit further. We may also try to run at different initialization dates as well, and look at changes in cloud cover as well, and perhaps extend this study to other cyclones too. And yes, that's me. So thank you. Happy to take any questions if you have any.
Thank you very much. Very interesting talk, though it is not on monsoon. So have you seen also coastal ocean eddies also along with the marine heat waves?
Sorry, what did you, didn't quite catch that.
Yeah, I want to know that, have you examined the eddies formed with that cyclone Honey in the coastal area?
Yeah, no, not yet. So as I said, it's just quite, we only ran these simulations a few weeks ago. So yeah, but I'm quite keen to look at it in a little bit more detail and unpick it.
Okay, thank you very much for the interesting talk. Any questions? Brief? No? Okay, thank you very much. We go to last presentation of today morning session. Let us Satyavan. Put up the slide. Go and presentation. Switch up the light.
Good afternoon, everyone. Now, in this talk, I am trying to explain this the combined influence of ENSO, IOD, and MJO on the Indian summer monsoon dynamics. And since morning, we have a couple of talks, and they introduced how these different time scales, the climate drivers that influencing monsoon. So as I'm working in the India Meteorological Department, which to representing the operational forecasting. So while dealing with the different stakeholders and the media, we just came across this idea to just explain how the best we can explain. Because the way they are thinking how the ENSO is influencing this monsoon and how the different teleconnections are also interacting. And here I am also representing this our Cliver GX monsoon panel and Cliver's climate dynamics panels. So I'll start with, I'm not going to spend this time. It is already known that India during the monsoon seasons, we are getting about 70 to 90% of rainfall on the different parts of India. But even though there is a lot of advancement has been made, we can see that the prediction of spatial temporal variation of Indian monsoon is still challenging. That is mainly due to the complex global teleconnections and intraseasonal variability, and as well as this regional land atmospheric interactions. This is one classical picture. We can see that Indian summer monsoon at a different time scale, for example, interannual and interdecennial time scales. But here I'm mostly focusing on the interannual variations. We can see that there are different teleconnections. That is we can say it is a climate diverse of the IMS variability. But many literatures and as well as our understanding that ENSO is the actually major drivers that has a stronger influence on the Indian monsoons. But understanding these which and how it is impacting for this monsoon rainfall specific year is always challenging. And we know that whenever there is a El Nino La Nina, we can know this is a classical fixture again that El Nino here is there is a deficient rainfall receives most part of India. And during the La Nina, we can see that there is a above rainfall over most part of India. We can see the year-to-year variability of these fixtures. But when we can see that there is a, for example, we can consider only La Nina, only El Nino La Nina with the there is a we can exclude the IOD years. Then we can see that there is a kind of we can see there is a symmetric rainfall anomaly associated with ENSO. But wherever we can consider without ENSO, if we can consider positive IOD and negative IOD, there is no such symmetric actually, because sometimes during the negative Indian Ocean dipole also we can experience above rainfall in some part of India regions. So as we can see, there is a, for example, whenever a season approaches, for example, we issue the long range forecast in the month of April. And whenever this, there is a many climate model indicates El Nino La Nina. For example, last 10 years, there is no such single month is a month in a year. There is a without El Nino La Nina. For 2014, we can see 2025, any month in a particular year, there is El Nino or La Nina. So when there is El Nino La Nina, people expect that there is should be predictability high. There should be a good observations of the rainfall, which is not always happening true. So what we do whenever there is Indian monsoons, we are try to see, because ENSO is a major climate driver, we try to see what will be the ENSO. Either we can see, try to model indicates that at that time of the particular 2023 monsoon, I can say it is a condition during 2023, observed model did not indicate any condition of La Nina. And again, model indicated that less probability of ENSO. But the model indicates high probability El Nino. Not only in El Nino, many models were indicating that there will be a super El Nino during 2023. Once there is El Nino, then is a major climate driver we are trying to consider is the Indian Ocean dipole. Because many times we can see when there is an ENSO, there is a contradictory rainfall anomaly is observing, then we try to see whether there is influence of IOD and how it is going to influence. So we can see at that time also we can see that there is no indication of during that period negative IOD and less probability of model indicating neutral IOD and high probability IOD. So then we'll think that there is a model is indicating high probability of El Nino, then high probability positive IOD. Then we'll try to know in the recent years how many such events are happened and how it is contributed to the spatial variability of rainfall over India. So there is such cases that there is 3 years, 1982, 97, 2015. We'll try to understand about that related. So when the model indicating the 2023, there will be a super El Nino, and we try to see during the last decade days when there is a super El Nino, we can see the 97 and 2015 is the similar what was the models are indicating that what is going to be in the 2023 monsoons. So, but when another challenges, we can see that out of these 2 super El Nino years, although it is a super El Nino associated with the positive Indian Ocean dipole, there is a rainfall actually, or there is on some part of abnormal, below normal rainfall, but 97-year monsoon is the actual normal area. Then the 2015 monsoon is actually deficient rainfall. So it is very difficult to explain to the stakeholders that even though El Nino is there, even though positive it is there, how it is going to explain the rainfall variance of variability within India. So we can try to see that in this 2 years, what happened, because of this 2015, July and August is considered as active monsoon months. We can see that this is the 2 active monsoon months. There is a strong rainfall deficit happened in the central India. But at the same time, 1997, it happened actually not so negative, although there is a positive, negative, no negative, right, compared to the 2015. So that is a contributor to the difference of the rainfall that was observed in India during 1917 and 2015. So we can see then SST rainfall, because we can try to see the large scale climate driver that is influencing the monsoon. We can see 1997 equal is a canonical kind of El Nino. But the 2015 is a kind of mixed one, Central Pacific El Nino plus canonical El Nino, which is also can see in the difference of the rainfall pattern. But in the period, some studies also mention there is a different kind of Central Pacific El Nino. In they call there is a sometime there is a Northeast Pacific, there is a extending to the Central Pacific one warm SST. There is a kind of ENSO Modaki, a different kind of ENSO. So in this way, how it is influencing the rainfall anomaly. For example, you can see on 2015 there is upper level strong divergence in the Eastern and Central Pacific is observed. And that is a canonical kind of rainfall or upper level convergence. It is observed in this monsoon, but in 2015 the spread is quite large. But when we can see that kind of, we can see the Walker circulation anomaly concluding the Indian landmass region. 2015 there is a strong subsidence over this Indian landmass region compared to the 1997. So, but not only that, it is a general picture what is happening with the ENSO if we can see kind of this analysis. But there is a, apart from this Pacific, there is also Indian Ocean SST anomaly is also impacting. For example, we can see the Indian Ocean SST anomaly. I could not see explain the previous picture. There is a east-west SST gradient is quite high in the 97, but in 2015 actually it is a basin-wide warming. Although we can considering it is a positive IOD. So apart from that, the monsoon that driving is okay, it is not displaying. So last 2-3 slides I will see before lunchtime. I am hurrying. Yeah, so what happened? 97, we can see that there is a SLP gradient over this Indian Ocean land mass. It's quite strong, which contributing to the bringing the strong low level of SST, bringing the monsoon over Indian region. But it is not happened the same in the 2015. We can see the difference of strong westerlies in 1917 compared to 2015. But what happened whenever we can see there is El Nino, there is a positive IOD. So apart from that general pattern of the SST modes, what are the other modes? Because in the morning also we are talking that the intra-seasonal oscillation, which is also driving the total seasonal rainfall, if it is accurately, we are discussing this morning that model is not representing accurately. But here in observational aspects, we try to understand how this MJO is contributed to this rainfall anomaly this way. In general, it's a climatological, it is known that phase 3, 4, 5, 6 is a very good for the summer monsoon rainfall over India. But phase 7, 8 and 2 is actually is that gives a below normal rainfall activities over India. So we try to compare in the 97, 2090, what is the MJO's phase and intensity. For example, you can see if we consider the favorable phases of MJO, 97 and 2015 that there are an equal number of active days MJO phases in favorable phases 27. Whereas MJO was actually about 30 days in the unfavorable phases in 97, but it was actually higher number, much quite near double in the unfavorable phases. That indicates that there is a high number of MJO in unfavorable phase is also bringing to the, contributing to the less rainfall over India. But it was also in a study by earlier, it indicates that channel that whenever there is a kind of Central Pacific warming is there is a moisture advections or the vertical as well horizontal that doesn't allow this, means that allows this further eastward propagates of MJO that is where the MJO is residing in the unfavorable phases that brings the less rainfall over India. So then because the objective of the 2023 monsoon, we analyzed all this work, just we quickly try to understand that the monsoon 2023 is actually 90% of the normal, which is 6% less than the normal. And but in this case, actually, Again, we can see that MJO is the many days compared to the favorable phases, unfavorable phases is also large number of days. And there is we can see India presence of Indian Ocean dipole, El Nino. So, but while understanding this complex interaction with ENSO and IOD and MJO is very difficult. Now, in the next phase of work, we're trying to understand more whether these such processes are accurately simulating or not, so that it will be helpful for the seasonal rainfall over India. So this is my summary in the last slide. So we can see that the 1997 is a kind of canonical ENSO, but 2015 is a kind of Central Pacific and canonical El Nino. But there is a, due to strong pressure gradient, north-south pressure gradient in Indian Ocean, there is a strong westerlies that contributed comparatively normal rainfall over India, but that didn't happen in 2025, the monsoons. So such complex interaction, whether it is accurately simulating them or we are trying to analyzing in the, for example, Copernicus seasonal forecast. So although due to sort of time, I'm not explaining here, but we are trying to understand whether this intra-seasonal oscillation and seasonal rainfall is accurately simulating or not. That's all from my side. Thank you very much.
Thank you. So actually, just one question from youngsters, if there is. We are not getting so much response from the youngsters, though actually, if we see presenters, there's maximum there are the youngsters. It's a good sign. You have?
Yes.
Yeah, please.
Shall I go ahead? Yeah, thanks for interesting presentation. So what you're basically trying to do, I think, is statistical forecasting of rainfall based on the large-scale modes. At the end, you said one question is how well the large-scale modes themselves are forecasted. That's obviously true. But another question that obviously springs to one's mind is, if you take the correct large-scale modes, so not the forecast, but the observed one, you do your basically composite-based rainfall forecasts. Are they better than the actual rainfall forecasts from, say, the seasonal forecasts? Yeah, because that's always the first question. Yeah, you're trying, basically what you're saying is maybe the models don't get it well from the large scale to the local scale. Therefore, you do your statistical stuff. But have you investigated whether that is really a good approach?
Yeah, that's because we cannot, at this advanced day, we cannot exclude the importance of coupled ocean atmosphere model, because this morning our monsoon panel co-chair Surya also introduced how these ENSO monsoons are overestimated in the climate model. For example, even all this triple dip La Nina or the 2023 El Nino, model is strongly responding to ENSO, because if La Nina it is giving above normal rainfall, it is El Nino, it is a below normal rainfall, which is not happening in the real sphere. That means the other climate drivers is influencing in the Indian monsoon, that is not actually correctly representing, but still we need to give some weight. But for similarly analysis, we also did for 2024 monsoon based upon some statistic analysis, but still we try to have a confidence on our climate models. Thank you very much.
Okay, Satyavan, actually this MGO you have calculated from the observations or from the models?
No, this is the from observation that our RMM index from Bureau of Meteorology.
Because have you seen that how it is in the models? Because if you want to predict, you cannot do the observation. It is post.
Yeah, that's that way. Because what happened, MJO means calculating MJO index is a little complex, because all the parameter that is required for RMMS. So then we need to take a long-term, for example, hindcast data or the model climatology. But we are trying to examine same case with all the ENSO IOD enzyme interactions.
Okay, thank you. Thank you very much. So with this, we come to the end of the session. We have very interesting talks. As I told, maximum presentations are from the youngsters, though we could not get so many questions from them. So I hope that they will be more energized after the lunch, and we'll have more questions from the youngsters. So with this, we conclude this session, and because we are already delayed. So I thank all the speakers, and we have a big clap to our young presenters.
Thank you, sir. Before we proceed further, I would request Dr. Nico Caltabiano to kindly come on the stage and felicitate our session chair, Professor UC Mohanty. There. Thank you. So before we break for lunch, I have few quick announcements for you. So lunch arrangements have been made at two places, one at the basement of this auditorium, and the next one is at IIT, this guest house adjacent to this building. And we have provided food coupons along with your tags. So you can find that behind your tags. So please make use of the food coupons. And participants who have not yet registered, kindly do so at the earliest at the registration desk in the reception hall. And we shall now break for the lunch and will resume back here at 14 IST. So we have got little less time, but we hope that we would be able to make it. Thank you.
नो इंटरनेट दिखा रहा है, लीव कर दूं क्या, वापस ज्वाइन कर लेंगे क्या वो लोग? वो अपने आप बातें कर रहे हैं, मैं अपना काम कर रही हूँ।
with me if you want to.
Good afternoon. We'll shortly begin with the next scientific session. Before that, is Dr. Titike available here? Dr. Titke, we have not received your presentation.
Good afternoon, everyone. I hope you had a nourishing lunch and ready for the next session. Hope everyone is ready. Shall we start the session? So welcome everyone. This session we are going to start now is simulation and prediction of monsoons, including extremes. I welcome everyone. I would like to know the reporters are here. Yeah, right. Thank you. So all the presentations are here. So I would like to, I'm pleased to introduce Dr. Kohli, Roop Kumar Kohli, who will chair this session on simulations and prediction of monsoons, including extremes. Dr. Kohli is a highly distinguished expert in climate services and monsoon research. He is a currently member of WMS Service Commission Standing Committee on Climate Services. I would like to request Kohli sir to lead this session and facilitate an insightful discussion on monsoon simulations and prediction.
Thank you for that introduction. And it's a privilege to help with this session 2 on simulation and prediction of the monsoons, including extremes. And we have a fairly long list of presentations. And after that, some to us lunch. So it can be a challenge to stay alert. But given that we have a wide range of topics that can actually shift your focus from one to the another. So that can probably help you in meeting that challenge effectively. We have 3 invited talks by a very eminent scientists who have played a leading role in monsoon research and allied disciplines. And followed by 6 contributor presentations. I understand out of the 6, only we have 5. And I hope we'll be able to finish in the allocated time. Each invited talk has 20 minutes and the contributed talks have 15 minutes each. And I request all the speakers to stick to the time and also leave a couple of minutes at the end of their presentations for discussion. To start with, we have Professor Bin Wang. To say a few words, I have actually I have known Bin for almost more than 2 decades. In fact, Bin and myself, we co-chaired the Clivar Asian Australian Monsoon Panel way back in 2004, 2005. And Bin has been one of the global leaders in monsoon research. And we really appreciate that in Hawaii, it's almost close to 11 o'clock now in the night. And he's still connected, and he's going to give us a presentation on changing ENSO properties, which can impede Asian monsoon climate prediction. So this is a very important topic. We have heard about the ENSO monsoon teleconnections, but we will see how ENSO itself is changing and how it can impact the predictive capabilities. Ben, the floor is yours.
Yeah. Thank you so much. Can you see the screen now?
Not yet.
Not yet? I thought I have a sharing this screen.
Now, make it full screen, please.
Okay. Thank you very much for the introductions. I really appreciate. Thank you for giving me this opportunity to discuss the changing ENSO properties and the Asian monsoon climate predictions. My talk will cover several published papers, so I want to acknowledge all co-authors, Luo Xiao, Yang Ming Yang, Marking, 温居蔡、宋武业、Tim Lee、包天象、Mark McFadden, Fei Jin, Fei Liu, Sun, Jin, and Liu. We know the changing property of ENSO can fundamentally affect monsoon climate forecasting. Actually, I would say without ENSO, we probably cannot predict monsoon. So this talk will discuss three aspects. The first is Asian precipitation-ENSO relationship and its historic change over the past 120 years. The second is the three types of El Nino events have distinct impact on the Asian monsoon rainfall. Last, I want to discuss historical change in the characteristics of El Nino and La Nina over the last century and what caused that. The Asian Pacific ENSO relationship was discussed in a paper in 2020, Journal Climate. First of all, I want to give a bigger pictures to look at the monsoon year rainfall. How does it relate to the Nino 3.4 SSE anomaly during the mature phase? In general, we know that during El Nino, the Asian monsoon area tends to be dry, except the southern China. This is the monsoon year from May 0 to April 1. And during La Nina is the opposite. So if we averaged the rainfall anomaly over the entire Asian land monsoon area, we see it correlated with the Nino 3 SSE anomaly pretty well, with a high correlation during the last 117 years, suggesting that the big picture is quite robust. And 1 degree of Nino 3 SSE warming will decrease the Asian Pacific average rainfall by 4.5%. However, the precipitation response to ENSO is highly regional and seasonal dependent. So we have identified the 6 major regions, sub-regions. For example, maritime continent, mainly from May to December, highly correlated with ENSO. And Southeast Asia is from September to May. India monsoon, the best correlation is from July to October. And the East Asian front zone from southern China to Korea, Japan, mainly in the winter time, November to next spring, April. And northern China is from July to October. And the May to July, next summer after El Nino, Yangtze River Valley was affected. So how does those relationship change with time? First, we look at the tropical Asia, maritime continent, Southeast Asia, and the Indian summer monsoon. This 31-year running mean correlation coefficient with ENSO has been basically stable and significant all the time. However, in the subtropical Asias, we see the break period in the 1920s, 1950s, 1940s. But in recent 50 years, both East Asia front zone or Northern China has significant correlations. So overall, it is the ONI, standard deviation, or the intensity of El Nino, the increase, especially from 1950s to now, that controls this monsoon precipitation and ENSO relationship, except the Indian summer monsoon. What is the mechanism by which ENSO affect Asian summer monsoon? We have to look at the 2 summers. One is El Nino development summer. And during that summer, if Eastern Pacific has a warming, then the equatorial central Pacific becomes convective active, and the maritime continent has suppressed convection. The change of these 2 precipitation heating source generate off-equatorial raspberry wave response. So this cyclonic response weakening West Pacific subtropical high. And over Indian Ocean, this anticyclonic ridge weakening Indian summer monsoon. And the decreased Indian summer monsoon heating can affect northern China, induce a dry weather through the teleconnections, the raspberry wave energy propagation, so-called circumglobal teleconnection over the Asian sectors. However, during the post-El Nino spring and summer, East Asian summer monsoon is severely affected by El Nino through different mechanisms. And this mechanism mainly due to the interaction between the Western Pacific anticyclonic anomalies interact with underlying Indo-Pacific warm pool, this SST anomaly dipole, plus the dry advections suppress convection in this area. The suppressed convective heating generate descending raspberry waves, further enhance this anticyclonic anomaly, so that this anomaly can maintain from the mature phase until next summer, mainly affect the East Asia monsoon. Next, I want to show that 3 types of El Nino impact Asian monsoon rainfall differently. The current classification El Nino, EPCP, is based on the boreal winter mature phase SST pattern. However, Asian summer monsoon is during its development or decaying phase, both in boreal summer. Therefore, whether this EPCP classification is relevant to the monsoon prediction is questionable. So we propose a new classification based upon El Nino evolution from the pre-onset to mature phase, rather than just look at the mature phase patterns. This was in the PNAS paper, discussed this. So this is the results of the El Nino diversity. They have a super El Nino, they have a EP El Nino, they have a CP El Nino. If you just look at mature phase, the SSE anomaly for moderate EP and super El Nino, they cannot distinguish. So the traditional EP type actually includes both of them. Okay? Now, we see that the CP El Nino and the super El Nino start from the Western Pacific. Due to the zonal advective feedback process. However, the difference is that super El Nino most involve this westerly wind burst, so triggering the thermocline and upwelling feedback in the Eastern Pacific. So the development is basin-wide, reach super intensity. On the other hand, the EP is started from far West Pacific, propagated eastward or westward, and different from the moderate CP. They involve different processes. That's why the evolution is different. The impact is also different because if we look at the evolution process during the developing summer, the SST gradient over the equatorial regions are different. And during the decaying summer is also very different. Therefore, we have to consider these 3 types of El Nino, how they affect the Asian precipitation. This figure shows how they affect the East Asian region, the rainfall, during the different super or EP or CP, during 3 developing stage, mature stage, and the decaying stage. And you see the super El Nino has the strongest impact for all 3 seasons. Phases. Okay. EP and the CP normally has the moderate impact. During the developing phase, because the CP and the super start from Western Pacific, so you see their patterns are similar, and the impact is stronger than EP. EP is different. However, during the mature phase and the decaying summer, the EP has a stronger impact than CP. And the pattern is also different. EP tends to be similar to the super El Nino. for multi-year La Ninas, we found that it has two types. One is following the super El Nino. Another is follow the CP El Nino. Following super El Nino, that has 3 cases. And for CP El Nino, they have 5 cases. And you can see that the development of cold event after super El Nino start from the Central Pacific, and the second year La Nina becomes stronger. Following CP El Nino, the development of La Nina is from Far Eastern Pacific, propagated West Pacific, Central Pacific. So the first year is strong, but the second year is weaker. They are quite different. So you expect they have different evolutions. However, what I want to emphasize is that the difference between single year La Nina and multi-year La Nina is their accumulated effect is different. The multi-year La Nina persists for 2 or 3 years, so their accumulated impact on the land monsoon rainfall is much stronger than single year. But if you look at the individual years, the intensity are about the same. You don't see much difference. Anyway, the last I want to discuss the historical change in the ENSO property and their causes, implication to the future change. This includes another paper recently published in the Nature of Climate Change, understanding the recent increase of multi-year La Ninas. First, we look at how the El Nino diversity changed. And this figure shows that the red bar is a CP El Nino, and the black bar is a super El Nino or strong basin-wide El Nino. And the yellow, the blue bars are the EP event. And those moderate EP event is the response on Carpenter's composite canonical event. After late 1970s, those EP events almost disappear, except the recent 2003. And instead, the Central Pacific event, CP event, and the super El Nino dominant. And simultaneously, we see that it's frozen. I don't know why. I can't move. Oh, there is a problem that I cannot move my presentations. Huh.
Yeah, maybe you can stop the presentation and restart from the same slide.
Restart. Yeah, let's go to this one. Oh, this is the next one.
Yeah, go ahead.
In the last 100 years, we have 10 multi-year La Nina red. Most of them occur in the later part of the century, especially in the last 25, 30 years. 5 multi-year La Nina, only 1 moderate single-year La Nina. So this is a phenomenal increase of multi-year La Ninas. And that has an impact on our prediction of the Asian monsoons. So the question is, what caused this observed change in the El Nino and the La Nina property? Okay. Now, there are many reasons, but we would like to think the background state, equatorial Central Pacific change, could directly affect the onset and evolution of the El Nino and the La Nina. So over the past century, the West Pacific SSC has been increasing. Correspondingly, the Central Pacific trade wind strength easterlies also increase. And as a result, the Central Pacific thermocline is raised up and the vertical gradient of ocean temperature increase. That means the thermocline feedback will be enhanced. And in the Western Pacific, this SSE gradient will enhance zonal advective feedback. So those could affect the onset of the El Nino and La Ninas. So in fact, if we look at the observed 33 El Nino event, pre-1970 blue and post-1970, the post-1970, this ordinate is the Western Pacific warming during the El Nino onset time. So you can see that those post-El Nino, mainly in the West Pacific, but not before. Before is even the negative. So that when equatorial West Pacific becomes warmer than equatorial Central Pacific, the El Nino events tends to onset in the West Pacific due to enhanced zonal advective feedback. So we can see that since 1970s, El Nino onset has shifted from the Eastern Pacific to the Western Pacific, leading to more frequent super and CP El Nino events. Therefore, we can hypothesize that historical regime change is probably rooted in the background warming in the West Pacific and the associated increases in zonal and vertical temperature gradient in the equatorial Central Pacific. These changes enhance zonal advective feedback in the equatorial Western Pacific and the thermocline feedback in the equatorial Central Pacific. Both led to more frequent super and CP El Nino event. And because multi-year La Nina is following super El Nino or CP event, so that increased the likelihood of multi-year La Nina occurrence. And we want to see what happened in the models. Of course, there are so many models you can look at. The model we look at is CSM2, large ensemble simulation in the CMIP6 experiment. And this model basically can reproduce the West Pacific warming in the historical area from 1901 to 2014. Okay, those warmer than the beginning. And in those models, we can identify this La Nina event. Okay, now in the first 30 years, the early 20th century, the single year and multi-year La Nina occur about the same frequency. However, in the last 30 years, in the beginning of the 21st century, single year La Nina is only 1/3 of the multi-year La Nina. So it tells us that the model really suggests that they can reproduce the historic West Pacific warming and increase multi-year La Nina. So very briefly summarize, how does West Pacific warming change El Nino La Nina? The West Pacific relative warming increase mean SS gradient in the equatorial Pacific. A direct impact is strengthening the zonal advective feedback in the West Pacific. Therefore, they shift El Nino onset from Eastern to West Pacific, favoring the more super El Nino and the CP El Nino, and also increase the odds for multi-year La Ninas. The increased SS gradient also strengthen equatorial easterlies. Therefore, the lifting thermocline and the increased upwelling and boosting the thermocline upwelling feedback. And that favors also for the super El Nino and the CP El Nino. And another process is that it enhances the upper ocean upwelling and poleward currents. That is in the meridional heat discharge, actually. They promoting meridional heat discharge so they can prolong this La Nina form, the multi-year La Ninas. What is the implication? The implication is if the Western Pacific continue to warm relative to the Central Pacific, what is going to happen? We expect more extreme ENSO events, such as Super El Nino and multi-year La Nina. And second, we expect the ENSO Asian monsoon relationship will be enhanced because the increased amplitude of ENSO and Asian monsoon may be more predictable. Of course, this is if the West Pacific continue to warm. Okay. Now, for future change, we should also pay attention to the equatorial Pacific mean state change. Okay, I want to stop here and listen to your comment. Thank you very much.
Thank you very much, Ben, for that excellent and new perspective on ENSO-monsoon relationship. So we can have a couple of questions. Yeah.
Thank you so much for that very interesting talk. So I want to ask you about when you were talking about the changes after 1980. So is it that something happening in the extratropical Pacific? Because few of our paper, we found that if the trade wind over the extratropical North Pacific can generate this ENSO event, and if the equatorial Pacific is already charged, it generate a strong East Pacific El Nino. But if it is not charged, it generate a CP El Nino. So anything regarding that kind of change is attributing this like a decadal variability in ENSO characteristics. Thank you so much.
Yeah, thank you. The different type of El Nino certainly has not only affect Asian monsoon rainfall differently, but affect the global monsoon differently, and mid-latitude teleconnections. Super El Nino is strong, and during the developing summer, Eastern EP type of warming in the Eastern Pacific and the CP type warming in the Central Pacific, they generate different teleconnection patterns. I'm sure they are different. Yeah, but I don't have any figures to show that. Yeah.
Yeah.
Thanks for the nice presentation. I'm just wondering, have you checked the sensitivity for these historical changes based on the different observational data sets used?
The data set we used is Hadley SST and ERS, the NOAA SST, merged SST data. For the rainfall, we have used the GPCP and the CRU data merged. And the recent years use GPCC from Germany and CRU the merged with CRU data. Recent years use the GPCP data update. I don't know. I think the long data set, land surface data set, is basically reflected by GPCC and CRU data.
Thank you. Ben, I have my own question to ask. Given the global warming situation, so the changes that you have highlighted, do you think there is a need for us to relook at the traditional indices that characterize the ENSO thresholds?
Characterize ENSO, you mean under a global warming situation, how do we look at ENSO signal? What is exactly your question? Sorry.
Yeah, we have, for example, the ONI or Southern Oscillation Index traditionally use ENSO thresholds to declare El Nino or La Nina. So do you think to relook at those indices and find some other better effective index that can capture the teleconnections in a better way?
I see. Okay, first of all, I should say that here we use the trend SS data on the equatorial Pacific, and there is no trend involved. Secondly, recent global warming affect ONI. So there is another index. I think Michelle has at all proposed this RONI, relative ONI. This is one idea trying to qualify, to quantity this ENSO index. I think that we should consider the global warming background effect. But the problems, if you look at the historical period, the global warming pattern is a La Nina-like pattern. Yeah. But the future projections, most models predict El Nino-like patterns. So we really don't understand how does the greenhouse gas warming will affect the mean state change in the Pacific. Because during the past 120 years, we have 1 degree global warming already. Why they show the La Nina-like mean state change, but in the future, there will be El Nino-like. Okay? Those are fundamental questions. I don't think we have an answer yet. Okay.
Thank you very much, Ben, for that excellent presentation and discussion. So we'll move on. The next presentation is by Dr. Andrew Robertson. So Andy will be speaking about subseasonal monsoon. As you all know, Andy led the S2S project of WWRP and WCRP for many years, which concluded recently, as Chris highlighted this morning. And I also have the privilege of working with Andy as part of an expert team under the Services Commission of WMO, where he is supporting the development of guidelines for operational subseasonal prediction. So Andy will tell us about improving subseasonal forecasts over India with machine learning.
Can you hear me? Okay. Thanks for the kind invitation and introduction, Rupa Kumar. I think that's 21 years since I first came here and visited you here at IITM. So simple concept here in this talk, can we improve subseasonal forecasts of Indian summer monsoon rainfall using machine learning? And I need it to be full screen. Let's do slideshow or something. Great. So this is a collaborative project with colleagues here at IITM, Susmita Joseph and Avijit Day, and with colleagues from the IRI. I'm from Columbia University, USA. I don't sound very American, but they couldn't prevent me from coming because this is actually a project that's funded by the Indian Ministry of Earth Sciences monsoon mission. So very grateful for that funding. I wouldn't be talking about machine learning if it weren't for the passion for machine learning from my colleagues here, Bohar Singh, who's now at NOAA CPC. And what I'm going to be presenting is really work done by Emil Esmail, a very capable student of ours at Columbia University. So, as I said, the goal is simple. Can we improve subseasonal forecasts? And here I'm really talking about weeks 3 and 4. So that means 15 to 28 days in advance using machine learning. And we're going to take a post-processing approach here. In the S2S project that Rupa Kumar just mentioned, we actually ran a machine learning competition 3-4 years ago to put it out there. Well, can you use the S2S database or any way you like, improve forecasts of subseasonal forecasts, generally of precip and temperature. And it turned out at that time that everyone took a post-processing approach. So they all took the outputs of ensemble prediction systems, subseasonal ensemble prediction systems in the S2S database as their input, and to see if they could use machine learning to improve them. The end result was they could do it a little bit globally. So here what I'm doing is I'm just looking over India at the at rainfall. And I'm going to use three ensemble prediction systems. There's the GEFS V12 from NCEP NOAA. There's the ECMWF model. And then there's the IITM ERP V2 model. So we're going to use the three of those. And we're going to use a convolutional neural network approach that was pioneered here by Horat and Lurch. And you want to be able to compare this against something, so we're going to benchmark it against existing post-processing that we use for sub-seasonal forecasting. And we've been doing this at the IRI for since 2018 now. That's quite a long time. That's like 7 or 8 years, using this extended logistic regression approach to post-process, calibrate, bias correct sub-seasonal forecasts. So these are our models. We have different hindcast periods for each of those. So that's a challenge that we face. So the idea is we're going to train these models using hindcasts. So it's like model output statistics, MOS concept here. And so we're going to use these periods. So they have different, the resolution of the data is different, but sometimes like the GES V12 and ECMWF models, they actually have much higher resolution than the data that we're using, which is from the sub-X sub-seasonal experiment, or now called the Sub-Seasonal Consortium database. It's archived at the IRI, and the S2S database for the ECMWF model. And within our Monsoon mission project, we have models from the IITM model also. Initialized more or less once a week, can be on different days. For our observational data set, so we want to calibrate based on an observational data set. We're using the IMD gridded data set, and we're going to upscale everything to the grids of the models available. Training season is June to September, and we're going to look at the other weeks as well, but we'll focus mostly on weeks 3 and 4. So that's like 14 to 28 days in advance. So what is this convolutional neural network? It's a pattern-based neural network. So as its input, we're going to give it the ensemble mean from the GCM. So we're not using any of the ensemble members here. And we're only going to use the precipitation field itself from the model. So I mean, you could use other fields here, but in this case, we're just going to use the precipitation. So you can think of it as being a bias correction or a calibration. So these patterns go in from the week 3 and 4 forecasts from these models, hindcasts over those periods. And then what comes out the other side is tercile probabilities, probability below normal, near normal, and above normal. And these categories, the cut points for those, they vary seasonally. So we do allow for seasonality here in doing this. Tercile edge is computed on a weekly basis, and we have probabilities that come out of this. So this sort of UNet architecture, what it does is this encoder, it basically upscales and reduces the resolution. There's a bottleneck node at the bottom, and then it downscales the result back to the resolution of the data. So you can think of it, if you're familiar with canonical correlation analysis, there's sort of an analogy there in terms of how this thing works. But we just use it as a black box. So we don't know what that's a thing. Typically with these machine learning approaches, we don't know what's going on inside. So our baseline, I mentioned extended logistic regression. Logistic regression basically is also based on the ensemble mean, and the other predictor here is the percentile, and in this case terciles. Training validation tests. So in machine learning, it's typical. You'll have you'll divide into a training data set here. These are 70% of the available data, 20% for validation, and we'll tune the hyperparameters of the model, sort of number of layers and various parameters here using the validation. And then we'll test it on independent data set of 10% of the hindcasts. We use in terms of how you make that split, you could use the first 70% of samples, things like that. But what we do is we do a bootstrapping here, kind of Monte Carlo cross-validation, where we do sort of many different choices of those. And in here there's 10 of those that we're using, but I mean, you could do more. if we had more GPU time. In terms of doing the test, we'll use the rank probability skill score, very standard for probabilistic forecasts. So cutting right to the results here, on the top is for each of the individual models, I'm showing the baseline skill that we get out of extended logistic regression, ELR. And so if there's no skill, or if the skill is equivalent to climatological forecasts, then it'll just be white, or blue if they're poorly calibrated and they're worse than climatology. So you want to be looking for sort of pink values, and it needs to be getting up into this sort of darker red here, sort of 0.1 up to 0.2 for it to be something that would actually be a useful forecast. So if you look across the top here of our three models that we're post-processing, you can see there's not a lot of pink, red. ECMWF is doing best. The IITM model is doing less well. It also has the shortest hindcast length. Let's look at the bottom. Well, how does our UNet convolutional neural network do? What we can see here is the GESS V12 is a big improvement here. This one also has the longest training data set compared to the others. ECMWF model in between, and in the IITM model here, we've got a mix of blues and reds. So with the short period that we have for doing the training, validation, and test, I think you could say, well, at least it's not really long enough to improve these forecasts much. But for the GESS V12, we've got a long hindcast set. You can see there's quite a big improvement here. So we were quite impressed with this. I mean, we went into it with some skepticism. Well, can these machine learning approaches really improve on, linear type regression? Because, unless there's really a non-linear relationship, we can't really expect to be doing much better. But you can see that it has made quite an appreciable difference. ECMWF model, maybe a slight improvement there, but it looks like it depends very much on the length of the training data set. If you just look at the anomaly correlation skill in a deterministic way here, just to see, well, what is that doing here? We can also see here on the GEFS is on the right here, and this based on weekly anomalies from those seasonally varying climatology here. That one is also the highest, and the IITM one is the lowest. So, I mean, you could say there's consistency here with what we're getting out of our UNet CNN. Okay, so that was using all the available data that we have, but it's not apples to apples, is it? Well, maybe we're getting a better result from GEFS because we got more training data. So let's make them all the same here. So we've used the same period here, which corresponds to what we have available from the IITM model, which is the shortest set of hindcasts. So you can see, if you can remember back to what I had before, the bottom row here, there's been a huge reduction here in the skill of the GESS V12 model if we constrain it to only using this amount of training data. So, I mean, that's something I think we know about machine learning, neural networks. You need a lot of data really to train these models. So we reduce it to only the set of around 15 years, not really enough. I mean, you think of the sample size, you've got like they're per week, so it's like, and you've got 4 months, so it's maybe, we've got 4 months times 4 weeks, that's 16 times 15 years. That's the sample size. So it is better than just, seasonal forecasting, for example. Okay, so those are the individual models on an equal basis. And here we've done that all at 1 degree, which is as a common spatial resolution too. So one thing we like to do also, we know that we make multi-model ensembles. It's a way to improve skill in general. We know this well from seasonal forecasting. We know it also from sub-seasonal forecasting. So can we make a multi-model ensemble of these? So we'll have 3 models in our ensemble. So we correct each one individually using our CNN UNet. We get probabilities of each of the 3 categories. below normal, near normal, above normal rainfall, and then we average together, simple unweighted average of the three models. How does the skill of that compare in terms of this? Again, we're looking rank probability skill scores, the thing we're looking at here. It's not trivial to line these things up, but we managed to somehow line these up, or Emil found a clever way to do that. If we do that, this is the result. So that's the bottom right, the average of the skill from the three individual models. And you see it's boosted quite a bit over any of the individual models. So it's sort of maybe matching a little bit the ECMWF1. But you notice that the blue is quite reduced, and that's important because you want to have, if there's blue areas, that means they're miscalibrated, there's overconfidence, and you don't want that. So you mustn't have any blue, and if you have red, that's helpful. So that's our result there. We can look at here's the other leads. I've got here week 1, week 2, week 3 and 4, the regression, logistic regression on the left, UNet on the right, and you can see there's a skill, we've got the individual models in different colors, and then the multi-model is in red. It's showing the distributions, all the grid points. It's over grid points here that we're showing distributions in these violin plots, if you're familiar with them. But you can see there's a reduction as we go to longer lead, but we get something from the biweekly average in weeks 3 and 4. And you can see that if you compare, if we just look at weeks 3 and 4, comparing on the left, the regression, logistic regression, linear regression, and on the right, the UNet. What you can see the distribution of grid points is that we are getting, we're getting more grid points with a positive, relatively sizable skill, but there are ones that are negative as well. So definitely we get sharper forecasts when we use the CNN UNet compared to the logistic regression, as if not too much of a price to pay in reliability. And we can see that here in these reliability diagrams for weeks 3 and 4. So you've got the 3 panels here, if you're familiar with these things: below normal category on the left, middle's normal, right's above normal. And what you want to have is these curves, you want to have them lining up on the diagonal. And what I've got is a neural net is in the blue color, and in the pink color is, sorry, yeah, that's right. The pink colors are baseline. You can see they're pretty in the below normal and above normal. They're pretty reliable, pretty along the diagonal here. And one thing you might be able to see slightly is that these histograms are the issued probabilities, and in the neural network, you've got a broader distribution, so there's sharper forecasts. There seems to be even some reliability in the near normal category, which you really don't see if you use logistic regression. How about a real-time forecast? So this is an example forecast from the year 2023. So it's a forecast that's issued on the 14th of July 2023 for the target period, the 28th to the 11th of August. These are the observed percentiles. So it was below normal in this red area and above normal where it's blue. And if we look at the forecast probabilities from the UNet in the middle and the regression on the left, you can see they look actually pretty similar. I said that UNet tend to be a bit sharper. Maybe we can see slightly larger probabilities. This is preliminary work. We haven't looked at this much yet. Of course, I'm showing you a good example of a forecast. I can find forecast busts as well, but I wanted to just give you a flavor here of what an actual forecast looks like. So to conclude, I think we can safely say that our UNet does outperform the logistic regression in terms of its calibration skill, despite challenges clearly related with the short hindcast data records that we have. Also, the multi-model is doing a good job here. It's enhancing the forecast skill compared to the individual models. And we can see an example here of a real-time forecast, which looks reasonable. So thank you very much. I'd be happy to try to answer any questions.
Thank you very much, Andy, for keeping to the time. Couple of quick questions.
Nice, thanks for a really interesting talk. Carry on talking. The standard spirit of EMOS is obviously old distribution in, new distribution out. You decided to not put the ensemble in, but the mean. Can you briefly comment on why you made that decision?
Yeah, I mean, that's it. We do that in our traditional method, and it's a signal to noise issue. That if you take the ensemble mean of the forecast, it's the thing that is reducing the noise. You've got your best guess from the ensemble mean. So that's what we've done here. But thanks for the question, because then within this context, we have actually tried using the individual ensemble members, and it didn't degrade things. It also didn't improve things.
Interesting, thanks.
And Andy, I have a similar question because we do this in the medium range. I don't know how well it would work, but instead of the ensemble mean, can you identify clusters and basically reduce the number of members into kind of means for individual clusters? And would that give you anything? Because it would prevent you from possibly canceling out certain signals, but I don't know whether it would gain you anything. So that's really my question.
Thanks very much. That's an interesting question. Great question. I think that's things that could be explored. I don't think I've seen anyone try that with subseasonal forecasting, but like you say, that's something that's done in the medium range, and I think those things would be great to explore. Again, we're really limited by hindcast data sets here, and let me just mention that ECMWF. If there's any machine learners here or online, listening online, there's a new competition that's been launched now by ECMWF, another machine learning competition for subseasonal forecasting. And this time they're expecting more people, or maybe most people, to use a purely empirical approach. So breakthroughs, obviously, in the last 2-3 years in weather forecasting using AI forecasting, and ECMWF have an operational version of their AIFS for weather forecast timescales up to 15 days. I hear from Frederick that they're also exploring on subseasonal timescales. They're getting encouraging results for the MJO. So I think in terms of machine learning, I don't know in the future how people are going to do this. In terms of using purely data-driven approaches versus using post-processing approaches versus using some combination of the two. But I think it's an exciting time for machine learning, certainly application in S2S forecasting.
Bipin.
Hi, it's a very nice talk. I have a small question regarding your data splitting. You have used the 10% data for the testing. Can you tell any specific region, or first question is any specific region to take only 10% data for testing purpose? And did you try the different splitting, like increasing the data around 20% for testing and reducing the validation data 10%, something like that?
So these are done in time, right? These sets. So it'll be a number of years that are taken for the training, validation, and test. But I mean, if I understood your question correctly, well, maybe you could actually take spatial grid points and do it actually like that. So you could train using different regions, test and validate using different regions also, if you might have been suggesting that. So doing it in time is one way to do it, but maybe it's not the only way.
No, that is another way. What I just asked, why did you choose only 10% for the testing? That was the main question.
Yeah, I mean, this was guided by the idea that you want to have the lion's share for training. So typically that's what will happen. Obviously there's some sampling variability in our the 10% that we've reserved for the test. But the idea is by using bootstrapping, we actually augment that so that over all the bootstraps, then you'll have the full data set for the testing. And just to mention that, there's only 10 here, and that you could do this 100 times or, even 1,000 times, and you would get some distributions coming out of the algorithm that then you could get some uncertainty in your RPS score from this too.
Okay, thanks.
Thank you. Thank you very much, Andy. So we'll move on. The next presentation is online.
I would like to request Dr. Roop Kumar Kohli sir to present a memento to Robert and to Robert.
Hi, can everybody hear me?
Yeah, the next presentation is online by Jill Martin from Met Office. Jill has been an active supporter of the Clive UX Monsoons panel, and also she supported the working group on Asian Australian monsoon. So she will be getting into understanding the development of errors in the Asian monsoon, summer monsoon simulation using some experiments. Jill, the floor is yours.
Thank you. Can you hear me okay?
Yeah.
Okay, and can you see my screen?
Screen?
And is it now full screen?
No, we are seeing the
Are you seeing the presenter mode?
yeah.
Is that better?
No. Maybe if you're having multiple monitors, probably you may have to select the one with full screen.
Okay, is that better?
No, otherwise you can just maximize the screen area and continue.
Okay, I'm just going to try that again. Seemed to work all right for Sana this morning, so I'm hoping it was going to work for me. Is that any better?
No, it's still the same, but you can go ahead. I think we can see it.
Okay, I'll just do it from here. I think it might be best. So I'll just minimize this bit. Okay, sorry about that. Don't know why that's not working. Okay, so hi everybody. So it's really nice to be able to speak. I'm really sorry I can't be there. Yeah, IITM is a really special place. I hope you're enjoying yourselves in Pune. It's the place I first visited when I started working on monsoons in 1997. So some of the people that I know are in the audience are people I met then and have met on my subsequent visits. So it is really nice to be able to present to you today. So I'm going to talk about regional relaxation experiments, which is part of understanding our development of errors in the monsoon. So those of you working in monsoon prediction using models will be aware that we've had systematic errors in these models for a long time. And we've been battling with those and trying to understand where they come from. I think we've made a lot of progress in understanding how the monsoon works and how to represent it, but we are still struggling with some quite robust systematic errors. What we found in our model, though, is that a lot of these errors do seem to arise in the first month or so of our seasonal hindcasts. We have the advantage in the Met Office of having a seamless prediction system, so we could use our similar model configurations for everything from NWP through seasonal and into climate. And so we were able to compare the errors that are arising in both the rainfall and the winds in our climate simulations and the SST errors with what we get in a month's worth of simulation from the seasonal hindcasts. And you can see they're quite similar in terms of the pattern. There are some differences, but the basic pattern of errors that we see in our model, both in terms of the rainfall and the SSTs, are quite similar just after a month's worth of running. And so we published a paper looking at this and looking at various techniques for unpicking this. And what we were wanting to do was to see if we can use this, this finding to say, well, where do these errors start from? What's driving them? What are the key regions that are involved? So we looked at what happens in our seasonal hindcasts in the first few days, or indeed pentads, so 5-day averages after initialization. So this is an example. And this is looking at the hindcast climatology. So there's 23 years of hindcasts here, initialized on the 25th of June. And that means that we can look without too much noise at how these errors develop from the start. So this is the first pentad after initialization, and then the next but one, and then the next but one. And what we can see in here is that the errors are pretty well establishing themselves within the first 10 to 30 days. And that's meaning that we can see if we plot different hindcasts. This is hindcasts starting at different times, and we pick different regions. We can see that actually these errors robustly develop in the same sort of way, really not depending very much on the start date. So, for instance, in this area of the West Pacific around the Philippines, where we get a positive bias in the rainfall, we can see that that starts right from the beginning in these different coloured lines, which are the different start dates, and it just increases as you go into the forecast. Similarly, we have a cold SST error in the eastern equatorial Indian Ocean, and we can see that not really depending very much on the start date, we just get a gradual cooling that happens in all of these from the start. So we know that it's a consistent and persistent development of these types of patterns of errors. What we can see, though, if we look at the first pentad and then the subsequent ones, is actually the maritime continent appears to be one of the key driving regions of these errors. So one of the first things that happens is that you start to get a decrease in rainfall and some anomalous divergence from the maritime continent. And this then pushes anomalous winds into the South China Sea and across the Philippines into this extending westerly error, which is promoting extra rainfall, and that's creating a positive feedback that keeps pulling the winds and the anomalous circulation into this region and gradually developing this positive rainfall bias and this excess strengthening and extension of the westerly jet out into the West Pacific. And we're also seeing a pushing of easterly winds, easterly anomalies, sorry, into the equatorial Indian Ocean, and a decrease in rainfall there. And that's promoting this gradually extending easterly anomaly right across the Indian Ocean. And there's also the initial fairly rapid development of our pretty characteristic anticyclonic bias at 850 over India and the associated decrease in rainfall. So it's looking as if there are certain regions where some of these biases start to develop right from the beginning. So then what we've done is we've used this regional relaxation technique. So this is something that Jose Rodriguez has worked hard looking at in NWP. And so he and I were working together looking at these initialized experiments where we basically apply relaxation back to reanalyses right from the start of initialized experiments, both in the coupled NWP model that Jose runs and in the glossy seasonal hindcast ensemble that I've been running. And so we picked some regions based on the areas that looked the most important in terms of starting those errors right from the beginning. So we've got the maritime continent either as a whole in this pink box or split into just Indonesia and then the Philippines region. We've got the equatorial Indian Ocean, and then we've got India itself. And we ran a set of experiments where we nudge each of these regions individually back to reanalyses from the start of the experiments for 2 or 3 start dates, but over the 23 years of the hindcast ensemble. And this is work that we published in a paper last year. And this shows some quite interesting results. So if I just go back to this slide for a second, if we assume that the response is linear, if we take a difference, so control minus the nudged simulation, then that will give us an indication of the role that the nudged region plays in the biases that occur. And we can also then plot what happens in the total errors in the nudge simulation. So that's telling us what happens if you don't allow errors to build up in the region that you've nudged or relaxed back to reanalyses. So in each of these plots, I've got 3 columns. So the right-hand side is the control error. So that's the total error in the hindcast that we were looking at before. And then in the middle, we've got the error that happens when you're nudging a region. So in this case, it's the maritime continent region, which is in this box here. And in the left panel, we've got the error that's contributed by the maritime continent region. So that's the control minus nudged simulation. So if we start by looking at the errors, so I've picked out the characteristic errors that we're interested in here. So our anticyclonic error over India, this extension of the westerly jet, and a cyclonic error over the Western Pacific subtropical high, and this pushing of the winds from this anomalous divergence over the maritime continent into that West Pacific region, and then this easterly wind here. So I talked about those a moment ago. So what you can see, if we look first at the errors contributed by the maritime continent region, that actually quite a lot of them appear to be driven by this region. So we can pick out those same patterns in both of these two plots. And so this plot here in the middle then shows what happens if you nudge that region back to reanalyses. And a lot of those errors just don't happen. Some of them do, but a lot of them don't. And so that's giving us an indication that actually if we were to get, if we weren't to allow errors to arise over the maritime continent region, then a lot of our more widespread errors would not arise. If we do the same with the equatorial Indian Ocean, again, so this plot on the right is the same, but we can see here now that the errors that are contributed by the equatorial Indian Ocean region are a little bit different from the maritime continent ones. It does seem to play a role in helping to drive or sustain this bias that happens over the Indian region, the anticyclonic error that we get, and also in pushing the winds into the West Pacific, joining up probably with the errors that are arising due to the maritime continent, and to some extent also promoting this cyclonic anomaly over the Western Pacific subtropical high. So there is also a role to be played by the equatorial Indian Ocean, and probably these two regions work together. And at some stage, had we enough time, we would have combined those two regions and looked at their combined effect on this using this same technique. So that's an experiment that it would be nice to do in the future. We also looked at the influence of other regions, which I'm not going to show for interests of time, but one thing that we do see is that there are definitely local drivers also to the errors arising over the Indian region, and they also help to promote this extra westerly flow. So just to look at the SSTs briefly, so we can see that the maritime continent region is also helping to drive this cooling. So we're immediately getting a decrease in the rainfall and a decrease in the convection, which is also associated with a cooling over that region. So we can see when we don't allow the errors to arise in the maritime continent region, then we get rid of quite a lot of this, this cold error. The equatorial Indian Ocean is also having a local effect. So we can see that this east-west dipole that we get in the SST errors is not arising to quite the same extent when we nudge that region. So there's obviously a contribution to that region. Obviously, this is looking at what's happening underneath the nudging region, but we're only nudging the atmosphere. So we're correcting the atmosphere, and we are getting rid of quite a lot of that error, although not all of it. I'll come back to that in a moment. So one of the things that we can do with this technique is we can use the nudging increments to give us an indication of what's actually happening, because what we really want to do is to get hold of what's going wrong here and how we might correct it. So if we look at the nudging increments themselves, what we're doing is we're nudging temperatures in the atmosphere and meridional winds, atmospheric winds. So what I've plotted is cross sections of the temperature nudging increments over the maritime continent region and the meridional wind increments as well from the nudging. So what the nudging is doing here is it's adding heating at mid-levels, around about the freezing level. That's the main thing it's doing here. And what the nudging is also doing is giving us a convergence, a north-south convergence in the meridional winds. And so what it's effectively doing is compensating for the fact that there isn't enough deep convection, that the deep convection is detraining too low down and it's not deep enough. And that's consistent with our finding in the first study that there's anomalous divergence in this region. There's not enough convergence. So what the nudging is doing is correcting for that. Now this is useful information because it suggests that what we need to do is to try and persuade our parameterizations, our convection schemes to give us more deep convection in that region. And what we have seen is that in some of our more are newer developments in convection, that you are tending to get changes in the heating increments that mirror some of these changes that the nudging is putting in here. So that's promising that might be an improvement over this region that might help to mitigate some of these errors. So there's a lot more that could be done with these, this analysis in looking more at these increments. This work is continuing to some extent in the coupled NWP model that Jose is running. So just very quickly to look at the equatorial Indian Ocean SST errors in more detail. So these are Hofmuller plots from the beginning of the season to the end of the season across the equatorial Indian Ocean, showing this development of this east-west SST bias. And we can see in the control that it gradually warms up in the west and cools down in the east. If we nudge the maritime continent, as we said, we actually do reduce that quite a lot, but it's still there. It's just in a reduced form. And if we look at what happens if we just nudge Indonesia, again, that's only getting rid of a bit of it. So we do need to kind of correct most of that region. But the most interesting plot here is what happens if you actually relax the whole global winds and temperatures in the atmosphere to the reanalyses. We still get some of this pattern arising. And that's interesting because it means that it's not fully and solely driven by the atmosphere. There's also potentially some ocean involved in this. So what I've done is look at what happens in the ocean. So this is cross sections of the ocean across the equatorial Indian Ocean. So you've got depth here on the left. And this is just looking at snapshots through the season of what the errors look like. So this in this case, this is a hindcast started in April, at the end of April. So this is sort of start of May, start of June, start of July, and start of August. So what you can see quite clearly is there's actually quite a lot going on below the surface. So soon after the start, we have already warmer temperatures at depth, around about 100 meters or so in the west, and colder in the east. And this develops through the season into quite large errors here, but they also get pulled towards the surface. So here are the ocean anomalous currents near the surface, which are related to what's happening in the winds, where we know we've got anomalous easterly winds. And so those, it appears to be pulling up the colder temperatures from depth, but also the warmer temperatures from depth in the western equatorial Indian Ocean are also coming to the surface as well. So if we look at the same plot, that's the control. If we look at the same plot where we nudge everything globally, so this is where we've corrected the atmosphere, so we shouldn't be having the atmospheric wind influence on this, but we can see those errors are still there. They're smaller and they don't develop as much, but they are still there, and they do seem to migrate towards the surface as you go through the season. So this is suggesting there's potentially an ocean component to this, and there's continued investigation on this in how that works and what the other drivers of this are. And Hannah Ellis, who is, I think, in the room, is giving a poster on her continued investigations of what's happening in the ocean, I think on Wednesday. So that'll be one to follow up if you're interested. I'm running out of time a little bit, so I'll just talk about this very briefly, this one. So this is looking at the coupled NWP runs for the Eastern Equatorial Indian Ocean just for the first 30 days. And the focus really, if you can just focus here on what happens with the relationship between the SST error, which warms first and then cools, and the winds, and also the mixed layer depth, which is this brown line here. So in the solid lines is what happens in the control, and the dashed lines is what happens when you nudge the maritime continent. So we can see that there is, for a start, there's an initial warming in the SSTs, which is related to a net positive downward heat flux anomaly, which is probably related to the fact that the cloud disappears and the rainfall isn't there at the beginning. But then as the zonal wind error increases, there's a direct relationship between that easterly wind and the SST. So this is showing the relationship with the atmosphere and the sea surface temperature. But it's also showing, if we look at the mixed layer, that there's potentially an impact also on the mixed layer depth that's related to those winds. And all of these disappear to a large extent when you nudge the maritime continent. So this is also an indication that the maritime continent is certainly helping to drive how these areas develop. So this is just a summary of what I've said. You can read that if you want in the slides that will be available. But I just wanted to go to some thoughts and questions. So just to say, as I'm sure you're aware, the circulation, rainfall and SST errors in this region have persisted for a long time through several generations of models, and certainly for the nearly 30 years that I've been looking at this. They've been quite robust and difficult to get rid of. But I do think it's important to look at how these errors develop after initialization, because then we can see really where they're coming from and where they start from. Often we look at these things once all the feedbacks have happened, and that makes it very difficult to then go back and say what we can do about them. And I think this technique, the relaxation technique, is quite powerful, can be used in lots of different ways. And as I say, Hannah's poster gives another usage of that technique. But as we know, it's really difficult to untangle and solve these robust systematic errors. It takes a long time, it's complicated. And I do wonder, and now we are starting to look at in the Met Office, and Andy's already mentioned this in the previous talk, can we use machine learning in different ways to maybe help us with this? It's being used on different timescales, but there's also people looking at employing machine learning components into global models. And it feels like this is an opportunity for us in the monsoon community to get involved in looking at whether we can actually make any difference to these robust errors that we've been dealing with for a long time using machine learning techniques. So that's really a sort of open question for the floor, and I'll be happy to take any comments on any of that. Thank you very much.
Thank you very much. Couple of quick questions. So I see no one asking for floor for questions. Thank you very much, Jill. It's an excellent presentation. We'll move on to the contributed presentation. The next presentation is by Khalif Tado on modeling and predicting the weather and climate of the maritime continent.
Okay. Good afternoon, everyone. I'm Khalif Tado. A bit of a change of scale. I'm going to talk about regional modeling and prediction for the maritime continent region. So roughly speaking, my interests are probably in three broad areas. One is regional NWP, both deterministic methods and also on ensemble prediction. The second one is, you would say, urban scale prediction, where you run regional models at very high resolution, say spatial resolution of 100 meters or so, just to give you high resolution over a particular area. And thirdly, regional climate change projections, where most of my interests are on the coupled modeling side. So for my group, the workhorse for all the applications in these different areas is the Met Office's unified model, which we run with their
regional atmosphere and land version 3, RAL3. So this gives us a very good, in many ways, regional prediction system. So on this plot here, you can see its performance for rainfall of different intensities compared to this benchmark, which is the sort of baseline from ECMWF. So you can see we are consistently adding value to ECMWF's global forecasts. And that's particularly true since this time here, a few years ago, when we upgraded the physics from a previous iteration of the regional atmosphere to this RAL3 package. And you can really see as well the impact that that's had over here on the right, where the red, which is the new physics packages in that model, are giving you much less bias, much better skill compared to the old ones. Where did that come from? So it turns out a lot of that is derived from changing the microphysics in that model. It's the first model from the Met Office, which included a double moment microphysics scheme. And we found for our region that had really noticeable benefits for the predictions of organized convection. So here on the left, you can see a squall line over our region in the sort of green colors there. That's the rainfall. And these are the predictions from those two modeling systems on the bottom. So you can see in the new one, the RAL3, the rainfall is much more coherent and joined up compared to the lack of spatial organization that we had in the previous iteration of this model. Although that's not to say it's always perfect. So on this side here, you can see an example of a recent forecast bust. This is a radar image of a flood causing MCS over Singapore and the surrounding area. And here's the model's attempt to predict that. And in this case, it got neither the timing nor the location, or even, you might argue, the existence of this rainfall feature. So this and similar cases was going to motivate a look for routes to improving those predictions. So one potential route that we're quite interested in is the prospect of coupled modeling. So that's an attractive prospect for the region because of the maritime nature of that part of the world, with strong, presumably strong air-sea interactions. This is a longitude time plot from a set of forecasts from a coupled prediction system. It couples that atmosphere model that I mentioned to the NEMO regional ocean model, and it's got a wave model in there as well. And then this is what you get if you do the same thing atmosphere only. So at first glance, you might say, okay, well, I can't see much difference there from the coupling. If you dig in a little bit more detail, you do find things that are different and are in some cases improved. So here you can see precipitation forecast skill for a range of different neighborhood sizes. The blue one is the coupled, and the green is uncoupled. So you can see there is a modest but systematic improvement in the rainfall skill coming from the coupling. Turns out that quite a lot of that comes from the diurnal cycle. So this is the diurnal cycle of rainfall over sea points within the domain. The black one is the satellite estimate of the true rainfall. The blue one is the couple model. So you can see the couple model doing a noticeably better at capturing this nocturnal rainfall peak over the oceans, which is one of the factors involved in this slight increase in the skill. So you can look in a bit more detail about exactly where that improved diurnal cycle is happening. It turns out it's happening in one or two regions here along the coast of Sumatra, and here, this blue one on the eastern coast of the Malay Peninsula, where there's a significant offshore propagation of rainfall at particular times of year. And you can see that if you look at these plots on the right, which are, well, this is time on the y-axis, and then distance to or from the coastline on the horizontal axis. So you can see in the GPM observations, offshore propagation of rainfall, resulting in nocturnal rainfall over the oceans. And that's better represented in the couple model on the middle row than it is in the atmosphere only one on the bottom. So that's nice. So the other route to maybe we can improve our predictions is maybe we can go for a higher spatial resolution and try and get things better that way. And that's an attractive prospect because with an increase in spatial resolution comes less dependence on the model's parameterizations, you might say, and some potential to increase the physical realism. So in terms of physical realism, that would be things like shown on the left here, where this is turbulence in the boundary layer in the high resolution 100-meter resolution model on the left, and then in a coarser resolution typical regional NWP scale model on the right there. So you can see the 100-meter model giving these much more chaotic, turbulent structures in the boundary layer, particularly over land, and that of course is going to be missing at lower resolution. However, when you take these models and you start to challenge them with data, what we've been finding is either the additional resolution doesn't really change results very much. So this is an example of that on the over here on the right. This is a 10-meter wind speed compared to weather stations, 2 resolutions of model, both of which are quite similar to the OBS, which is the black line. So sometimes it doesn't make much difference. Sometimes it actively makes things worse, which is a bit of a frustration. So this one here, this is net long wave downwards, measured from a flux tower in the black line, and then the models in the colors. The red line, which is the high resolution model, has actually degraded the performance. You can claw a bit of that back if you apply some averaging to that high resolution model, but you have to average it basically back to the scale of the much cheaper kilometer resolution model to get back closer to the observations. Having said that, it's perhaps not all about performance with these very high resolution models. They do enable you to do interesting things because of that extra physical realism, particularly realism in the resolution of the land surface. So, for example, we've been taking regional climate projections and then dynamically downscaling them again to 100-meter resolution just over Singapore. And then we can combine those future climate projections with this more detailed descriptions of the land surface and put in some plausible scenarios for land use mitigation. So there's one example shown here on the left. This is the urban greenery today in Singapore. And this is a thought experiment where we've made some plausible increases in that amount of urban greenery. And you can combine these scenarios and look at the effect of that on future extremes. This is an example of an extremely hot day at the end of century over here. And then on the far right here, you can see the effect that that mitigation, land use mitigation, more trees had on the temperature. So I wouldn't read too much into the actual details of this, but it's certainly interesting that you can use these models for this kind of investigation. So then finally, the other route to model improvement, I think that I haven't mentioned so far, would be, well, let's look at the atmosphere model itself. So this should be an animation over this side, but it's not, it isn't, because it's a PDF document, but there you go. If this was an animation, you'd be able to see simulation of rainfall from ELFRIC, which is the Met Office's replacement for the unified model, which the unified model is being retired over the next few years and replaced by this new modeling system. So we've been taking a look at this model and seeing how it performs in our region over this area here. Broadly speaking, its performance we find is quite similar to the unified model, which is reassuring. Here you can see a comparison of rainfall in the two models over land and over the oceans. And these panels are different climatological periods. So these are relatively dry days at the top and relatively wet days at the bottom. So you can see some differences in the diurnal cycles of rainfall that are shown here. but not major differences from its predecessor, the which is, as I say, quite reassuring for us. The other model that we've been looking at is the model for prediction across scales, MPAS, which is NCAR's next generation replacement for WRF, for the WRF model. So I guess you might say a strength of this model, or maybe that you can plug and play lots of different physics schemes, not quite as much as in WRF, but it's quite easy to try out different combinations or put in new physics schemes and so on into this framework. So we've been doing a bit of that. We put in a double moment microphysics and compared it to several of the single moment microphysics schemes in the MPAS system, and you do find very substantial impacts of changing the model physics in this system. These are plots of the outgoing long wave radiation simulated by that model with two different cloud microphysics schemes. Having said that, the ability to try out lots of different permutations doesn't really substitute for understanding when it comes to actually improving these models. So on the right here, this is histograms of the outgoing long wave radiation. Most of the lines on here are different flavors of the MPAS model, apart from the blue one, which is the observations from the broadband radiometer on Ceres. Sorry, it's the broadband radiometer called Ceres, which is on Aqua or Terra, I forget, one of the NASA satellites. So the observations are the blue line, and then this orange line is the ELFRIC model, and all the other ones are various flavors of MPAS. So you can, I guess the message here being plug and play physics can be quite useful in that it can help you sample a range of different outcomes from the model, but it can't really, you can't expect it to give you better modeling systems out of the box. So I'll stop there. So when I put together this talk, I realized, okay, what are you trying to say here? I think really what I'm trying to say from my perspective is there's various ways you can try and get from where you are now to a better model that we've historically looked at. For the maritime continent area, coupled modeling is an attractive one, but does improve some aspects like the diurnal cycle, but we haven't found huge benefits to our predictions coming from that. Spatial resolution, it does enable novel applications, but in terms of performance, the cost benefit may be not favorable. But there are substantial benefits that can continue to be derived from improving the physics in the atmosphere models, which I find interesting. There's a fourth point on here about the increasing use of AI, which I haven't touched on, but that we could discuss further. Okay, thank you very much.
Thank you very much, Kelly, for that rich collection of your efforts on multiple fronts. One quick question, if anyone has. No? Thank you. Thank you very much. So the next presentation is online by Wangxi Su from Nanjing University of Information and Technology, China, on the impacts of intraseasonal oscillations on humid heat wave occurrence over the Asian monsoon region.
Okay, thank you. Can you see my PowerPoint?
Can you make it full screen?
Okay. Yeah, okay. Good afternoon, everyone. I'm Wangxi Shi from, wait a minute. Okay, I'm Wangxi Shi from Nanjing University of Information Science and Technology. And today I will share our recent studies about the impacts of tropical intraseasonal oscillation, ISO, on humid heat wave occurrence and prediction over the Asian monsoon region. And my talk today will cover 5 parts. I will start by outlining why understanding the humid heat wave and their relationship with atmospheric variability is essential. Then I will go over the data and the methods we used, followed by a detailed analysis for the key mechanisms of ISO modulating humid heat waves. In addition, I would like to highlight some of the challenges in predicting the humid heat waves at the subseasonal time scale. Finally, a summary. The motivation. And with global warming, the extreme weather events are becoming more complex. In the past, we often look at the high temperature or a heavy rainfall event as a separate event. But now we are seeing more situations where the temperature and the moisture interact, forming what we call the compound extreme events. For example, a very dry condition combined with a hot weather or a high humidity during the cold temperature with a heavy rainfall condition or a high humidity during hot period. And all these compound events have higher risk than a single extreme event. A humid heat wave happens when high temperature combined with high humidity, producing very dangerous condition for human health. And we generally use the weight-bound temperature, TW, to measure how severe the humid heat is. When the TW is higher, the air holds more moisture, and that will make it harder for our body to cool down. So understanding what causes TW to rise and how to predict the condition in advance are important for reducing the heat stress and the preventing deaths. And several research have identified the factors that lead to dry heat waves. However, fewer studies have explained the mechanisms of the humid heat wave occurrence. And when it comes to predicting the extreme events, earlier studies found that the current operational models have capability in predicting some heat wave events at the subseasonal time scale. However, we have little understanding and that regarding how the operational models handle the compound extreme events. Considering that the Asian monsoon regions are densely populated and that often experience hot and humid conditions in boreal summer, so we aim to address the 2 questions. The first one is how ISO modulates the occurrence of humid heat wave, and how well the current operational models can predict them. And I will quickly go over the data we used. And we define the humid heat wave event when the TW greater than the 90 percentile for more than 3 days. And to diagnose the relative contributions of temperature and moisture to the humid heat wave events, we calculate the daily TW using the different components. And since the TW depends on the temperature T and the actual vapor pressure EA, so we first derive TW from the raw daily data from the temperature and the EA, and to isolate the effect of subseasonal moisture variations, we compute the TW using raw daily data of EA, but with the climatological temperature. So that can remove the subseasonal variability in temperature. In a similar way, to focus on the effect of temperature, we use the raw daily temperature data with climatological EA to suppress the subseasonal variability in moisture. And the key process responsible for the warming and moistening anomalies associated with humid heat waves are analyzed using the temperature budget equation. surface energy equation, and also the moisture budget equation. And to assess the model capability in predicting the humid heat wave event, we use the heat deck scale score that measures the accuracy of a forecast compared to a random chance. Okay, now I will show you the results on how ISO modulates the humid heat waves. And in the Asian tropical monsoon regions, and TW tends to be high during the boreal summer. And the power spectrum of the daily TW in the 3 key regions in the Indian monsoon region, the Indochina Peninsula, and in southern China. And you can see from the power spectrum analysis, all the TW in all 3 regions show significantly 10 to 30 day variabilities. So that suggests the modulation of TW by the quasi-biweekly oscillation, QBWO. And to examine how the QBWO modulates the weather condition, we analyze the convection shown in shading and the circulation anomalies shown in vector during the entire life cycle of the QBWO from phase 1 to phase 8. And the QBWO shows a wave chain pattern with a cyclonic and anticyclonic that propagating from the tropical ocean toward land areas. So when the convection and circulation anomalies approach land area, they can affect the near surface temperature and moisture, and that will cause the TW anomalies in the tropical monsoon region. Then we focus on the probability changes in the humid heat wave occurrence during the individual QBWO phases relative to the climatology. So we use the equation to quantify the effect of QBWO for the humid heat wave occurrence. And from the results, you can see that in the South and in the Southeast Asia, we can see an increased probability of humid heat wave occurrence in phase 2, 3, and 4 of the QBWO. But in southern China, that you can see the more humid heat waves tend to occur during phases 4 and 5. We also quantify the changes of the humid heat wave in the 3 key regions. So we analyze the area average, the probability anomalies, and we also calculate the ratio of green points with a positive and a significant anomaly, so that we can know the frequency change affected by the QBW over the spatial extent changes of the humid heat waves. And the result shows that during phase 2, 3, and 5, that provide the most favorable condition for humid heat wave in central India and in northern Indochina Peninsula and in southern China. So the next question we would like to address is why the humid heat waves in central India favors phase 2 of the QBWO. So we first identify the dominant factors by comparing the humid heat wave patterns that are driven by the TW from the EA variability showing panel B and from the temperature variability showing C. So the results shows that the humid heat wave occurrence have higher correlation with TW driven by the daily moisture variability than the temperature variability. So this suggests that the QBW modulated moisture anomaly plays a dominant role in humid heat wave occurrence. Then focusing on near surface layer, and that is shown in the gray shaded areas. And we found that the main source of the moisture comes from the horizontal moisture advection shown in blue curve. And In contrast, the temperature anomalies near the surface are all quite very small, while we can still see a little bit positive anomaly from the diabatic heating process. So we further identified the key process of the horizontal moisture advection, and we analyzed the individual terms related to the interaction between the background conditions and the QBW time scale and the high frequency perturbations. So there are totally 9 terms related to the scale interaction, and that can induce the horizontal moisture advection. And the result shows that the dominant term is related to the QBW circulation that transport the background moisture. So you can see a cyclonic anomaly in Bay of Bengal and combined with an anti-cyclonic anomaly over northern India. So that can enhance the easterly anomaly, and that helps transport the background moisture from the Bay of Bengal towards central India. And the secondary contributor is the cross-equatorial flows that transporting the moisture perturbation from the Arabian Sea toward the central India. And for the humid heat waves in the northern Indochina Peninsula, the moisture anomaly caused by the QBW plays a major role in humid heat wave occurrence, while the temperature anomaly also shows a comparable contribution. And during phase 3, when an anticyclonic anomaly dominates the region, the descending anomaly that can help to moisten the lower troposphere through the evaporation, and that can also heat the near surface through a diabatic process. Then we come to the southern China. The humid heat wave in southern China also show a closer connection with moisture variability. And during the phase 5, the southern China experienced the cyclonic and ascending anomalies, and that can induce the low-level moisture convergence and enhance the vertical moisture transport. And the near surface warming is mainly driven by the horizontal advection process. And both the moisture conversion and the temperature advection process are tied to the QBW circulation anomalies. And you can see that the southwesterly anomaly related to the QBW that can transport the moisture from the oceans and then lead to moisture conversion in southern China. And they also bring the warm air from the tropics. The next important question is that how well can we predict the humid heat wave events at the subseasonal time scale? And here we show the assessments of prediction in the 3 key regions in central India, in the northern Indochina Peninsula, and also in southern China. And the black curves show the predicted results of the ensemble mean from the ECMWF in the upper panel and from the NCEP prediction systems in the lower panel. While the green shadings show the range of individual members, and our finding reveal that the ensemble mean performs better than the individual members, and the ECMWF model reveals superior scale than the NCEP, and that with the skillful predictions at the forecast lead time of 5 to 6 pandas. And our further assessments suggest that the moisture prediction is a major source of the biases in the current operational model. And the black curve shows the original prediction based on the model predicted temperature and moisture. And when we use a perfect EA, and that means we use the observed moisture condition replace the predicted ones. So the forecast scale shown in blue curves, and they all increase greatly. And the red curves shows the improvement when we use the perfect temperature. They show a little, they also show some improvement, but compared to the blue curves, they are still a little bit lower. And the results are consistent in both the ECMWF and NCEP. And now let me quickly summarize the key findings. The probability of the regional humid heat waves in the Asian monsoon region are QBW phase dependent, and they are influenced by the diverse process. In terms of the subseasonal prediction, the ECMWF shows skillful humid heat wave prediction at 5 to 6 panda forecast leads, and the accuracy in EA prediction is the key to increase the humid heat wave prediction skill. Okay, I will stop here. Thank you for your attention.
Thank you very much, Pangshi.
Yeah, thank you.
We are very short of time, but we can take one quick question if anyone has. No? Thank you, Pangshi.
Okay, thank you so much.
We'll move on. So the next presentation is by Hugh Lewis from Met Office on the WCSSP program.
Hey, good afternoon all. Can you hear me okay? Yep, great. So I'm Hugh Lewis from the Met Office in the UK, and it's a privilege to be with you this afternoon to give a slightly different talk, but to hopefully give an introduction and a celebration of some of the work that's been delivered through the Weather and Climate Science for Service Partnership, WCSSP, project that's been focused on India for a number of years now. And this presentation is really on behalf of a much broader project team, a number of whom are sat right across the audience online and in the room today. So WCSSP is a multi-year bilateral program of work between the Indian and UK governments, focused on enhancing understanding, methods and predictions for improving risk-based forecasting of natural hazards. And you can see illustrations of a number of the sort of hazards that have been driving our research over a number of years on the slide. But critically, these outputs of our work provide pathways for the Indian Ministry of Earth Sciences to deliver improved weather and seasonal climate services, and of course enhance the research and prediction capabilities that apply right across timescales. There's a lot on this slide in terms of text. We're going to sort of pop it up a few times, so don't worry about reading it. But what I really want to try and highlight is an approach that tries to gather together a number of different project activities and research strands that you'll hear sort of peppered through. We've already had a number of talks today and through this afternoon, and across a number of posters and talks through the week. We'll sort of see illustrations of these various project activities spanning research from global to regional to urban scales across a range of observation and modelling studies. And looking to develop our impact-based forecasting methods and the research that sits behind those across the UK and India. We organise ourselves across 4 different work packages that really sort of bring together all of those various activities. And I think one of the reasons for highlighting this slide to you is really to acknowledge and thank the work of the UK and India work package leads, a number of faces on here are hopefully familiar to people and will be with us through the meeting this week. So please do reach out to these people to talk about the WCSSP project in more depth and to understand how your work might align and engage. Also, I couldn't possibly do this kind of array of activity justice, but to highlight, and you can kind of pick your favorites across these 4 work packages of a variety of oral and poster presentations through the week. I think I've probably missed a few, but I think I've made it 16 talks and 15 posters sat right across this sort of interdependent set of work packages that go from developing seamless ensemble coupled systems through into work package 4 and the risk-based forecasting of high impact weather events. So I'm really here just to advertise that there's a lot more of this project outputs coming through the week, and I hope you enjoy it. At a sort of slightly different level, we've pulled together from this variety of research to a number of project outputs, and I'll just pause for a moment to highlight examples of some of these. So a driver is to improve the understanding of the processes that drive extreme weather and their impacts. And clearly in the Indian context, then the monsoon is a key large-scale driver of those and sort of sets the scene for a number of the high-impact weather conditions that we're interested in. I thought I'd just pick up an example that wasn't going to be showcased through the rest of the week here, which is in the context of predicting fog in the Indo-Gangetic Plain. And the panel on the left-hand side here is showing the impact of representing irrigation in our prediction models, and which is typically an unrepresented process, and really seems to be a key to trying to improve our predictability of fog in this region. And this is a nice example, I think, of that alignment between process level studies and understanding, improving our models, and the use together with observations here from the WIFEX campaign that was run by and supported by our IITM at Delhi Airport, and pulling together UK and India partners to look at this kind of study. And this was then brought together in this paper by Dan Smith in Nature Comms last year, if you want to go and read more. For strengthening the scientific, technical and modelling capabilities, we span the scales in this work. And in fact, Callie gave quite a nice introduction to a number of the different scales of interest here. So if we start on the left-hand side of what I call urban scale or hectometric modelling, this is really getting to sub-kilometre scale processes, and really to acknowledge the work both here at IITM and at NCMRWF to extend the what we'd call complexity of these very high resolution models to be able to address problems like air quality and development. There's a nice paper here from Jaya Kumar in BAMS on the development of the DM-Chem simulation system focused on visibility and air quality for Delhi. In the middle, we've heard both Callie gave a showcase and Sana earlier this morning talked about the kilometre scale regional coupled prediction, both as again as a sort of way of driving some process studies, looking at air-sea interactions at these kilometre scales. And you can see there's a paper here from Juan Castillo with a documentation paper of that system. And in terms of the impacts, we can see first order feedbacks from the air-sea coupling on things like tropical cyclone predictions. And then on the right-hand side, clearly a strong element around development of global coupled ensembles. And the thing I'd highlight here is the connection to trying to make good use of the variety of Earth observations for data assimilation and initialization, and exploring new techniques or new opportunities such as the microsat work highlighted here, for example. And I think an important thread that's running through the WCSSP is that research really has to deliver into application and to support MOES in delivering to their mission. So just 3 examples here of how new research then can underpin the development of prototype tools and serve as a basis for improvement of the services that then that go to society. So on the left-hand side here is an illustration of the flood hazard impact model. This is developed by partners in the UK from the UK Centre of Ecology and Hydrology as an ensemble-driven sector-specific fluvial flood risk forecast capability. I'll refer you to a talk on Friday morning by Seshu to look at this in more detail. In the middle is an illustration of using Earth observation to develop satellite-based impact and vulnerability assessments. And this was part of a SEVA project run by HR Wallingford and developing a web app focused on flooding and windstorm impacts on agriculture. And on the right-hand side is an illustration of observation-based product development and use of satellite observations to develop diagnostics linked to severe convection and lightning hazard. And this, as well as sort of a data set in its own right, has been really well connected to IITM microphysics development, and the sharing of data across this project has really led to some new insights and new work. This is probably my favorite slide of the whole talk. Looking at it again, it did at least confirm to me that we're very well practiced at standing in lines and looking at cameras together. But more importantly, I think this is illustrative of a number of different sorts of and levels of interactions that take place across the project, and you'll hopefully spot a few familiar faces on this slide as well. So across a number of sort of subject-specific focused video conferences, visiting scientists, we tend to run a series of annual meetings, and a variety of other interactions are really the sort of glue that keeps these kind of programs together. And I'd commend those too. These as ways of doing research across international groups. In terms of the UK, partner contributions beyond the work that the Met Office is delivering into WCSSP, just want to acknowledge a series of UK academic partner projects. Again, without going into any depth, but to at least highlight that we've got a project with the University of Birmingham called HEPI-ML, which is really a first specific example of developing machine learning for post-processing ensemble forecasts. And I'll just refer you to Martin Widman talking about this in more detail on Wednesday. Akshay earlier this morning described some previous work at the University of Reading under WCSSP, but there's an ongoing project called Outbreak with a slightly dubious acronym, which is focused on process understanding and predictability of monsoon breaks. And again, is a really nice illustration, I think, of going from very broad scale research, understanding, looking at sort of global drivers of these systems, and then paring down into exploring the impacts, including, for example, focus on heat waves as described just in the previous talk. And then thirdly, there's another project with HR Wallingford called MIDAS, which is focused on improving understanding of multi-risk assessment. So going beyond the development of impact-based forecasting, focused on just a single hazard area, into looking across cascading and compounding risks. And again, I'll just refer you to a talk from Darren, forgive me, Darren Lambrosco on Friday morning. It's even written on the slide. Okay, pulling things all together, we then try and keep a focus on project outcomes. And again, just to reiterate, the driver to enhance the capacity for the ministry to develop and implement improved services, framed in the provision of impact-based forecasting. I think the sort of fourth line on here is important though as well, is that the importance of not just doing this in isolation as sort of UK-India bilateral work, but really as a part of the wider glue and leveraging opportunities and the sort of wider research ecosystem. So particularly trying to tie into activities like the WWRP and WCRP initiatives that we talked about, we heard about this morning. And it's in that kind of context, I guess I'm really excited to be able to encourage people who are eligible to look at a new MOES call that's just been launched, inviting Indian academic proposals to come and join this activity. So the deadline is the end of April, and please take a look at the MOES website. With pulling out the key line here, I think, is that the new project proposals should really articulate how they're going to enhance this collaboration with MOES institutions, so working right across the MOES grouping and with UK partners across these research themes. If I can just try and wrap up with a few thoughts around future directions or future areas we're looking to grow into WCSSP. Three areas kind of particularly come out to me, and the first is around really exploiting the world-class research observations for process understanding and model improvement that sit here, not least really driven through IITM and this atmospheric research testbed, is something that we're really wanting to exploit right across the work packages. On the top right-hand side is an illustration, I think, of a question that came up earlier about development of convective scale global models. And we've seen, I think, in a few talks of the power of some of our modeling systems now to be able to go from global right down into sort of large continental scale and down into local scale, using the same modeling infrastructure and being able to explore this resolution question. And then, of course, on the bottom is the need to assess the benefits and limitations of machine learning right across that end-to-end chain that WCSSP India encapsulates. Again, I guess, both on the sort of global scales, but an illustration here of machine learning development focused on London as it happens, illustrating the need to get down right to local scales for some of this application. So with that, that's a sort of high-level run through some of WCSSP India. Again, just to emphasize, I think, I hope you'll have opportunities to discuss with a number of people leading work on India and UK side through the week. I'll leave these numbers up just to reflect on, and we'll finish there. Thank you very much.
Thank you for that excellent overview. I think this is probably one of the most successful and sustained bilateral collaborations that we have seen in this area. So I think we really appreciate the spirit of collaboration between the two countries. Any quick questions? I have one. Is there any focus on annual to decadal climate prediction in WCSSP? I know that IITM has been contributing to the WMO Lead Center on annual to decadal climate prediction hosted by Met Office. So is there any activity focused on that?
So strictly, there isn't a focus beyond seasonal timescale applications. However, and I think we get a sense of this through this morning already as well, the relevance of model, some of the underpinning biases and some of the model development tasks are common really across timescales, and Jill really nicely illustrated, I think, the value of looking at some of these from an initial value initialization perspective, and then we expect that work to follow through into improved decadal and longer term timescales. So there, while the scope we try and focus somewhere, so we focus from days through to seasons ahead, but I think the work is highly relevant to cross timescales. Yeah.
Thank you. Thank you very much. So we'll move on. The next presentation is by Aarti Menon, also from Met Office, on the diurnal cycles of monsoon rainfall over northern India, over western coast.
Good afternoon, all. I will show some preliminary analysis from a study on the mechanisms driving the diurnal cycle of monsoon rainfall in northern India and the rainfall modes over the west coast of India in the Met Office model. This work is done with Jill Martin, Hugh Lewis, and Andy Turner. So Hugh already gave an overview of the WCSSP India project, and this work also falls under the WCSSP India project. To give a quick background on this study, Fletcher et al. Identified two regimes of precipitation near the Western Ghats, the offshore mode and the coastal modes of precipitation. So if you look at this figure on the left, this shows the rainfall Hofmuller near the Western Ghats averaged between 12 to 14 north from 21st June 2016 to 28 June 2016. Here the black solid lines show the extent of the Ghats. So from 21st June to 24th June, we can see that the rainfall is mostly accumulated over the ocean. But then from 25 to 28 June, the rainfall is mostly aligned along the coast. So the coast is around 75 east. So these are the offshore and the coastal modes of the Western Ghats precipitation. Then Fletcher and Hunt later looked at this in climatology and identified that these offshore and coastal phases of Western Ghats precipitation are also present climatologically. Later, Fattare et al. Looked at the diurnal variability during these phases and found that there is strong diurnal variability during the coastal phase. The figure here shows the potential temperature and winds near the Western Ghats at different times of the day. So each panel represents a different time of the day. And you can see that there is strong diurnal variability in potential temperature and winds during the coastal mode of this precipitation. Now, a quick look at the importance of irrigation over India. Over 325 million hectares of land are equipped with irrigation, and 42% of that falls over India and China. The figure on the right here shows the hotspots of land-atmosphere coupling from Koester et al. And you can see that the central and northern parts of India, especially along the Indo-Gangetic Plain, is one such hotspot for land-atmosphere coupling. Coming to the simulations used in the study, we used the nested suite setup of the Met-Office unified model, regional model. The figure on the right side shows the limited area model domain. The limited area model has a resolution of 4 kilometers, and this is nested inside the global model at 17 kilometers resolution. The simulations were done for the period 30th May to 29th August of 2016. We are mainly interested in 2016 because that was the Encompass field campaign period from where we have lots of aircraft and ground-based measurements. So it was an intensive observing period. So we did the simulations for the 2016 case studies. We did both atmosphere only and atmosphere ocean wave couple simulations. The atmosphere only simulations had SST updated daily using the OST analysis. We did some experiments with the different land ancillaries, the IGBP and the CCI land ancillaries, and also tested the model with different sign settings. So Kelly has mentioned some of these sign settings in his talk. Then some of the experiments were also repeated with and without irrigation coupling. So coming to irrigation in the land surface model Joules, irrigation is implemented in such a way that the top 2 layers of the soil are topped up to critical point if the irrigation water is available. Now some initial results from this. In this figure, we are looking at the diurnal cycle of heat and radiation fluxes near the Western Ghats. So the first and the third column shows the diurnal cycle on the windward side of the Ghats, which is shown by these 2 red lines, this E1 area. And the second and the fourth columns show the diurnal cycle of heat and radiation fluxes on the leeward side of the Ghats, shown by these 2 yellow lines. The red lines here shows the diurnal cycle during the offshore modes from the models. And the blue line shows the diurnal cycle during coastal modes from the models. And then the purple and the green lines show the offshore and coastal modes from ERA 5. So if you look at, especially like if you look at the leeward side of the Ghats, you can see that the red lines have higher values than the blue lines. So that's applicable for both the heat fluxes and the radiation fluxes. So the heat and the radiation fluxes are stronger during the offshore phase compared to the coastal phase in these models. And the diurnal cycle is peaking at around 7 UTC, which is around 12:30 Indian Standard Time. Then this is again looking at the rainfall Hofmüller from these models. So on the left-hand side is the figure from Fletcher et al. And the other panels show the rainfall Hofmüller from the models. So if you compare A and B, these 2 are the simulations that use different sign settings. One uses RAL 1T sign setting and the other one uses SINGV 2.1 sign settings, but they use the same land ancillaries, which is IGBP. And if you look at B and C, they have the same sign settings, but uses different land ancillaries. And we can see that B and C look similar, but A and B looks different. And panel D is for coupled model, which looks different from all the other three. So the conclusion here is that like the sign settings in the model have a stronger influence on the diurnal variability near Western Ghats compared to the land surface initializations in this context. But when you go to the boundary layer, the land surface initialization has strong effects. Now looking at the irrigation runs. So the figure on the left here shows the irrigated fraction from the model. You can see that strongly heavily irrigated region in the Indo-Gangetic plains and some over the leeward side of the Ghats. The figure on the top panel shows the offshore sensible heat flux for irrigation minus no irrigation. And the bottom panel shows the sensible heat flux during the coastal phase for irrigation minus no irrigation. So this is a difference in the sensible heat flux between the irrigation and no irrigation runs. And we can see that especially during the offshore phase, there is an increase in sensible heat flux on the leeward side of the Ghats during the in the irrigation run compared to the non-irrigation run. So we have to look into more details of this to understand this. And you can see the sensible heat flux differences over the Indo-Gangetic plain is consistent with the surface forcing. Now, this figure shows the vertical structure of theta W during the offshore and the coastal phases. So the left side column is for the offshore phase and the right column is for coastal phase. And the top row is for the simulations without irrigation and the bottom one is for the simulations with irrigation. So if you compare the offshore and the coastal modes in both these simulations, we can see that the there is in all these figures, you can see this dry layer at around 600 hectopascal. So this is the mid-tropospheric dry air intrusion that Akshay was also mentioning about. This is coming from the west towards the Ghats region. And we can see that the dry air intrusion is stronger during the coastal phase compared to the offshore phase. So Fletcher et al. Has also identified this. And we can also see a slight upward shift in the core of this dry air intrusion during the coastal phase compared to the offshore phase. When you compare the no irrigation and the irrigation runs, we can see that the differences are mostly over the land, which is like towards the east of 75 east and at the lower levels. This is again the vertical structure, but of relative humidity. So here I'm also showing the figures from the coupled runs. So atmosphere only and coupled runs with and without irrigation. And what is shown here is the difference between the coastal and offshore phases. So coastal minus offshore relative humidity. Again, we see this dry air intrusion in the mid-troposphere around 600 hectopascal. But we also see like moistening in the upper troposphere during the coastal phase compared to the offshore phase. So there is stronger moisture content at around 200 hectopascal, and this might be pointing towards a strengthening of the easterly jet during the coastal phase compared to the offshore phase. So we talked about the diurnal cycles near the Western Ghats. Now we will have a quick look at the North India region where the irrigation is quite prominent. This is a box over North India near the Indo-Gangetic plain. And what is plotted here are the 925 hectopascal theta W and winds. So the left side is from the simulation without irrigation and the right side is for the simulation with irrigation. And we can see that they look quite different. And the right-hand figure shows a strong gradient between these wet and dry regions. And this was observed by Barton et al. From satellite data. So the irrigation runs is capturing that this sharp boundary here better than the no irrigation runs. And the winds are also stronger in the irrigation run compared to the no irrigation runs. And these winds change direction once it enters this boundary of wet and dry soils. The green contours here shows the low clouds at 5Z, which is like 10:30 IST, the convective initiation period. And we can see that the clouds are mostly formed near these boundaries between the wet and dry surfaces. This black box shows the region which was shown in the previous figure. And these lines here show the diurnal cycle of 2-meter temperature, mean sea level pressure, and sensible and latent heat for no irrigation minus irrigation cases over this region in this black box. We can see that the 2-meter temperature is higher and the pressure is lower in the no irrigation runs. So the diurnal cycles of temperature and pressure are consistent with the surface forcing. And this figure is made by Emma Barton from CEH. So to conclude, the diurnal cycles of heat and radiation fluxes are stronger during the offshore phase compared to the coastal phase. Then we see that the metropospheric dry air intrusion from the west is stronger during the coastal phase, as well as maybe the tropical easterly jet is also stronger during the coastal phase. The Akshay has already shown the effect of the dry air intrusions in the withdrawal of the monsoon. So we see the effect of dry air intrusion in the coastal and offshore phases. Fletcher et al. Has also seen that. If you want to know more about the dry air intrusions, Akshay has a poster in the evening that looks at the effect of dry air intrusion in the monsoon breaks. Then we saw that we compared the irrigation and no irrigation cases and found that the irrigation modifies the heat fluxes over the leeward side of the card. So it might be having some large scale influence there. Then over North India, we see that the low clouds form over these areas of strong soil moisture gradients. So the overall message from this is that we need detailed information of the spatial distribution, types of irrigation, etc., so that the weather forecast models can better predict the boundary layer processes. And this also includes the convective initiation. Yeah, that's all. Thank you. I'm happy to take any questions.
Thank you very much, Aarti. Yeah.
Oh yeah. Do you have an idea for whether it's better to have bad irrigation in a model or no irrigation in a model? Because it's clearly important, right, to have something in there to get those gradients in and to change the thermodynamic environment. So is it do you really need all of that extra data, or is it okay if you just kind of put a wet blob up in the northwest?
In some cases, like it's just okay to have just at least have some irrigation, but then currently Heather Rumbaud, who is working on irrigation scheme, she's trying to improve the irrigation scheme by adding like different types of irrigation, drip irrigation, and including some seasonality into the irrigation. For example, like in the fog case studies, also irrigation plays a major role. For some of them, we need the seasonality because it's mostly the winter time that is important. So we need to introduce those. But I think, yeah, it's better to have some form of irrigation as a starting point.
Very nice talk.
Thank you.
See, over Northwest India, you showed irrigation. You showed a sensible heat flux is decreasing.
Yeah.
I would have been in. Hello. So can you show latent heat flux over North India? That is because if irrigation thing, there should be more latent heat flux. Yeah. And also why this theta is increasing in the place where you are irrigating. I didn't understand that.
So I also have looked at the latent heat fluxes, which I'm not showing here. And in so it's overall, if we take the average over this box, we see that the latent heat is increasing and sensible heat is decreasing. But there are these.
Yeah, but this is no irrigation minus irrigation.
Yeah. Yeah, this is no irrigation minus irrigation. Yeah, but in the absolute values also we see that latent heat is increasing and sensible heat is decreasing. But it has the,
But I didn't see the latent heat flux.
yeah, it's
You
the
are there.
bottom. Yeah, bottom one. Yeah, but it has some spatial gradients. Yeah.
Thank you.
Okay, thank you. I think we should move on. We're already delayed. Thank you very much. The next is the last but not the least presentation. It's online by Aviator Bosch from University of Reading, UK, on subseasonal prediction of the South Asian monsoon rainfall using data-driven forecasts.
Hello.
Hello. Can you share
Okay.
your...
I'm not able to share the screen. Just a second. Is it enabled?
Let's see.
Sorry, I'm having some problems sharing the screen. Can you share the presentation from there?
Can you share it from here? Did you send the presentation here?
Yes.
Can you check in the folder if it is there?
Sorry about that.
I think they are trying to locate the file.
Okay.
Did you upload it or sent it by email?
Oh, I sent it by email.
Okay. Got it now. Can you see it?
No. Sorry. Oh, there we go. Yes. Okay, now I can see. Okay, sorry about that. Okay, so should I just say next to go to the next slide? Okay, so thank you for having me. So this is work based on 2 papers, and this is joint work with Eugenia Kalnay and Surjalal Sharma, who very sadly passed away last year. But this is based on a paper published in PNAS, and it's also joined with Jagadesh Shukla, V. Krishnamurti, and Michael Gill. And this was actually work funded by the Monsoon Mission too. Next, please. Next. Yes, so the basic idea here is that we know that there are oscillatory modes in the climate system that are important on subseasonal to seasonal timescales. So of course, for the monsoon, we're interested in the monsoon interseasonal oscillation, MISO, which I'm sure there'll be a lot of presentations about. And we know that these are often predictable from data beyond what current dynamical models can do. Next, please. And the idea is we want to use data-driven forecasts of these modes to improve our overall forecasts. Next, please. So we know that monsoon interseasonal oscillation is a northward propagating rainfall mode with a period of about 45 days. Next, please. Okay, so there is a video. I don't know if it's going to work, but this controls the active and break phases of the monsoon and a lot of the regional distribution of rainfall. And it's important for S2S prediction. Of course, has relevance to agriculture, flooding prediction, and water availability. So the idea here is that we know that we can decompose the full field into multiple modes. So here we'll use singular spectrum analysis, but you could use other methods. So let's say we have the precipitation field, that's a spatiotemporal field, and it's a sum of multiple modes. Among those, we'll have the interseasonal oscillations, and those will be a subset of those modes. And this will define a reduced subspace of the dynamics. And the idea here is that the dynamics in this subspace are effectively low dimensional and can be learned well by machine learning or data-driven methods. And this has been shown in several papers. However, we don't really care just about predicting these oscillations because, of course, we're interested in the full dynamical field of interest, such as the precipitation field. And these only represent a portion of the variance of the total field. So the idea is that we have, next please, we have a projection from the full space. So in this case, we have the full rainfall field over India. And we have the MISO mode, and we can define a projection from the full phase space to the reduced subspace. But the problem is that this is not invertible. So we can't go from a forecast of the interseasonal oscillation to a forecast of the full precipitation field. But the idea of this work is that we can bring in tools from data assimilation to inform the forecast in the full phase space using the forecast in this reduced subspace. Next, please. So the idea here is quite simple. We're going to take an ensemble in the full physical space. So here I'm just showing two ensemble members. And these are predicting the full rainfall field. And we can project these into this MISO subspace. We can also do a data-driven forecast in the MISO subspace. And then we'll weight the ensemble members in full space according to how well they're capturing the data-driven MISO forecast. So in this case, we'll have this purple ensemble member is closer to the data-driven MISO forecast, and so we'll give it a higher weight in the average. Next, please. So this is similar to the idea of importance sampling in particle filters. So we're giving more weight to ensemble members that are more likely to result in the MISO pattern that we want. Next, please. So we extracted MISO from IMD data, so the gridded rainfall observations since 1901, and we applied multi-channel singular spectrum analysis, which is a kind of extended empirical orthogonal functions. Then we approximate the projection into the meso subspace using a neural network. Next, please. And we'll do analog forecasts in this reduced subspace. So this is actually a very simple data-driven model. We're just doing analog forecasts in the meso subspace. And those work very well. And then we'll weight the full dynamical ensemble members by the method I described. Next, please. In terms of our dynamical model, we'll use the IFS with bias correction. So this is DCMWF model, and we'll use July, August, and September, the years 2008 to 2016. Next, please. So this is a coupled model with 25 ensemble members, resolution about 36 kilometers, and 91 vertical levels. And this is a good benchmark because we know that IFS is state-of-the-art in subseasonal monsoon prediction, at least as of 2017. It's outperformed other models that it's been compared to. Next, thank you. So here I'm showing the skill of just the data-driven meso forecasts. So you can see, so this is comparing the correlation between the predicted meso mode and the one extracted from observations. This is for July, August, and September. And you can see that these have quite a bit of skill depending on when they're initialized, but you can get over a month of skill if you set the threshold as 0.5 in these 3 months. Next, please. Okay, so now I'll show the this combination process where we weight the dynamical ensemble using the data-driven forecasts, and we'll look at the skill of precipitation forecasts. Next, please. So this is the, so here I'm just showing the IFS skill. So this is going to be our baseline. And I'm showing the temporal correlation over India and then also over the broader monsoon region. So the temporal correlation with lead time. Next, please. And this is when we apply our method, we can see a substantial increase in the temporal correlation of the rainfall over both India and the wider monsoon region. Yeah, so we have a pretty substantial up to 0.2 or 0.27 increase in the temporal correlation. Next, please. And this is over the different homogeneous monsoon regions over India. Days 14 to 20 and day 21 to 27. And we see, and this is showing the increase in the temporal correlation in these over the baseline IFS forecasts. So we see a pretty significant increase in the skill in some places more than others. And the asterisks show places where we found a statistically significant increase in the skill. So you can see it really improves everywhere, but you know, is more significant in some regions and at certain at different lead times. Next, please. So to conclude, we applied this method to the South Asian monsoon and showed that we can outperform state-of-the-art forecasts, dynamical forecasts on 10 to 30-day lead times. Next, please. So this is really a demonstration that by combining data-driven forecasts with dynamical models, we can achieve an improvement in skill. And we want to do this with the MJO in future work. Next, please. And more generally, this is a way of like I said, combining dynamical and data-driven forecasts. And we can generalize this using other methods from data assimilation, in particular we have this method called the multi-model ensemble common filter, where you can take ensembles of multiple models, including dynamical and machine learning models, and incorporate them into the data assimilation and forecasting process. Next, please. Yes, and this is the paper if you're interested. My email and website if you'd like to get in touch. And thank you very much. Sorry about the technical problems, but thank you very much.
No problem. I think it worked out well.
Yes.
Yeah, Andy.
Oh, yes.
Hi, thanks for the interesting talk. I think if I understood correctly, you said that what you do is you project the ECMWF ensemble members onto these MSSA modes. And using a neural network. So I was wondering conceptually, if you do that just linearly, how much are you gaining by the neural network? What's it actually doing?
Yes, that's a good question. So the problem with MSSA is that it's not real time because it involves both forward and backward filtering in time. And so, you know, to actually, I mean, it is a linear projection if you have that future information. But of course, we don't want to do that because that's cheating if we look at the future. So we had to approximate this projection with a neural network using just the past information. So that's why we use the neural network. But there's certainly something that we're looking at is there are other ways to do this in real time, including some papers that have looked at trying to do a conditional Gaussian approximation, and maybe using something that's not SSA would work better. But yeah, so that was the reason we use a neural network.
Okay, gotcha. Thank you.
Thank you.
Thank you very much, Peter, for that excellent presentation. I think we come to the close. A very interesting session with a wide range of issues on all aspects of simulation and extremes. And let us thank all the speakers for their presentations. And I thank the organizers for the opportunity to support this session. Thank you.
I would like to thank Dr. Kohli, and I would like to request Dr. Rajagopal to present a memento to Dr. Kohli. Thank you, sir. Thank you all. Now let's proceed for the poster session. Let's proceed for the poster session and tea arranged at the first floor of Rudrang complex. Before that, I would like to inform you that a red folder is missing from the registration table. So if anyone get it, please inform or give it in the backstage. And so as you step out of this building, take a right, then the next turn you take another right, so you will reach the Rudrang building, and volunteers will be there for your help. So good evening. Thank you. About dinner, everyone have to assemble in front of IITM, in front of this auditorium by 6:45 p.m.